So, a very good morning to all of you, and welcome back. Back to day 2 of ACS TOXI India 2024. I'm sure all of you guys had some time to rest because yesterday was really very exhaustive and a long day for all of you. But great talks and a lot of discussion, a poster session, and then I think we did some poster session judgments as well, and then finally 5 posters were shortlisted. So it was quite a happening day yesterday. So welcome back all of you guys, and a very good morning to you. So day 2, actually, this is all what we covered in day 1. So yesterday we focused around environmental toxicology and very interesting plenary talks. So today we are going to shift gear, and now we'll get into actually AI and ML tools for toxicity prediction, and followed by that we will also be talking about tools like from 3D cell culture tools, how do we use in initial drug discovery mode. So again, quite an interesting talks are lined up today also. So I think all of you guys are going to really have a great time. Just only one request is let's try and make it more interactive, right? So all of you are students, so feel free to ask any questions you may have, and as a student nobody is going to judge you, so feel free to ask whatever comes in your mind, okay? And just to motivate you, Dr. Grover has come up with a very novel thing. He has bought some, so he has come from University of Arkansas, and he bought some pins. So he belongs to a place called Little Rock, so he has got these pins from Little Rock. Maybe he would like to show it to all of you. So Little Rock from a Little Rock. The place name is Little Rock, and the pin is also signifying the Little Rock. So every person who is going to ask a question, he will earn one of this. All right. So this is your chance to earn as many Little Rocks you can earn. So whosoever is asking questions today, he is going to give it to you. All right. So I think he's bought sufficient stock with him. In case if there are more questions, then he doesn't mind investing some dollars and buying a few more for you guys. So try and let's make sure that he should actually give away all his pins, and we have more questions, and we'll make him pay by his credit card and buy some new ones for you guys. Okay, so let him invest something here while he's here. So with that, I think let's start our session. So first of all, would like to welcome all our distinguished speakers for today, and let us welcome them. I would request Director of the Institute, Dr. Gopal Natesan, sir, to welcome all our distinguished speakers. So to start with, may I request Dr. Sailesh Bhavsar, sir. He is Dean PG Research and PG Research at Kamdenu University. Welcome, sir. May I now request Dr. Shilendra Pratap Singh to please come to the dais, and would request Dr. Gopal to offer a bouquet to him. Dr. Shilendra is from Indian Institute of Toxicology Research. He is flown in today morning all the way from Lucknow, take an early morning flight. So thank you, Dr. Shilendra. May I now request Dr. Krishna Iyer. Dr. Krishna is from Bombay Pharmacy College, and a veteran, and even our mentor, and I have studied my metabolism and DMPK basics from him. So welcome, sir. May I now request Dr. Senthil Natesan. Dr. Senthil is from QRL Bioscience into cell therapy. Welcome. Thank you, Dr. Gopal. So I think with that, let us get started. I would request the moderator for today, Dr. H.B. Patel, to take the proceedings further.
So good morning to all. Our 4th session that is focused on the artificial intelligence and machine learning tools in the toxicology. We have speaker from Kamdenu University Director of Research, Dr. S.K. Bhavsar. He has very vast experience of teaching and research in the College of Veterinary Science and Animal Husbandry at the Anand, and his major area of the research is the pharmacokinetic and toxicology. He has published more than 85 publications in the nationals and international journals of the high repute. He has been awarded the Fellow of the Indian Society of the Veterinary Pharmacology and Toxicology, as well as the Professor J.P. Trivedi Awards of the Association of the Agriculture Scientist. He has very vast experience in the identifications and characterizations of the polymorphism in the drug metabolism in the different domestic species of the animal. He is heading the two council-sponsored research project in the department, and apart from this, presently he is as a Director of Research and Dean Postgraduate Study, Kamdeni University. So may I now invite Dr. Shailesh Bhavsar sir to present the today's talk. And I am proud to say we both, Deepak and myself, are the students of Dr. S.K. Bhavsar sir. Sir, please.
Sir, this is laser to point out. This is how you go front and back. 1 second, sir.
So good morning to everyone. Before start with the today's my topic, at the outset, I am thankful to the Indian branch of the American Society of Toxicology for organizing this wonderful event at Ahmedabad. I am also thankful to Dr. Deepak and his team for such a nice conference. Now, as introduced by Dr. Hitesh, I am an academician largely involved in classical toxicological studies, and this is being a new area for me also. We are little bit being involved, so we are also learning as the area of artificial intelligence and machine learning. This is again combining the biology with informatics or bioinformatics or chemoinformatics. So it requires a amalgamation of many things. So the topic of my today's discussion is harnessing machine learning and artificial intelligence in preclinical toxicology. So everybody knows preclinical toxicology. It's a part of drug discovery process where we do the all type of safety studies where the chemicals are being tested and then goes to the further development. So these are the points I will be discussing, making introduction to the topic. Then we'll understand very briefly what is artificial intelligence, what is machine learning, what is the workflow of the machine learning, and some of the key developments that has taken place in the area of AI and machine learning used in the area of toxicology. So machine learning and artificial intelligence, these are the transformative technologies in the field of toxicology. So it is going to transform what we are doing today. In coming future, it will definitely transform the toxicology. It enhances data analysis and predictive modeling, aiding researchers in understanding the chemical study, especially the safety of the chemicals. Our understanding will going to improve at a very early stage using these technologies. And advancement in the area of these technologies are reshaping the research methodologies in the preclinical as well as clinical toxicology. And integration of these technologies into toxicological studies promises for, say, faster and more accurate results rather than what we are getting today. We all know those who are not the students of toxicology, or maybe say what is the importance of chemical safety, because each and every chemical which is under the process of drug discovery and development need to be safe. So what is chemical safety? It is a crucial factor in protecting public health and the environment, which is also the theme of this conference, that through drug safety, through chemical safety, we need to safeguard the health of the human beings. Understanding this toxicity of the chemicals, it helps prevent harmful exposures and environmental disasters. This many times we read in the newspaper, many disaster happens. So this can be reduced, or this can be stopped if you understand the chemical safety. Traditional toxicology relies on extensive animal testing and laboratory experiments. Many of you pharmacy students and other students, we are all doing this animal experimentation. So that can be improved, or that can be minimized with the use of these newer technologies. And the approach is often time consuming, expensive, and ethically controversial. That is the animal testing. Many times we hear, and many times we in IACs, CCACS, we hear the controversies that they don't allow the animal to use, or say they do not allow the sufficient number of animals to be used, and there are many controversies. So all this is part of chemical safety or drug safety. So how can we predict toxicity? We can use the appropriate machine learning models, and it can contribute to the accurate prediction of toxicity. It enables early identification of potential hazards associated with the chemical compound. So this at a very early stage, with using this computer science or artificial intelligence, we can, at a very early stage, we can predict the potential hazard of the chemical. And it appears to be applications in almost every area of toxicology, like drug discovery and development, oncology, drug efficacy and toxicity, and human health hazard, especially due to the rise. Now this technology, these are very, they give good result, but it requires a good data. If the input data, or the data from where the conclusions are drawn or the predictions are being done, but if the sufficient data is not available, then it will be difficult for the models to determine and give the accurate results. So it's a data-driven toxicology or data-driven techniques. The integration of machine learning into the toxicology represents a shift towards data-driven approach. By utilizing vast data sets from various sources, researchers can better utilize or analyze the chemical analysis. Data-driven methodologies lead to more reliable predictions and conclusions, and this shift is essential for modern toxicological practice. So this is a required thing, that based on the vast data available, we can predict the toxicity at the early stage. Now let us understand in one slide what is artificial intelligence. So I am not an expert of a computer science, I am a pharmacologist, toxicologist. So just I have also learned what is artificial intelligence. It is a rapidly developing subdiscipline of computer science with the goal of designing and creating machines or computational models that can perform a variety of cognitive tasks at a level comparable to the human intelligence. So this can compare. So it's a science under the computer science, and where we can create a environment where the artificial creation can say compare to the human intelligence and it can take the decisions. In toxicological context, it refers to the applications of various machine learning methods in the prediction of and evaluation of toxicological properties, including the toxicokinetics of the chemicals. Let us understand what is machine learning. It's a sub area of artificial intelligence. So as we have discussed, main area is computer science. Under the computer science we have artificial intelligence. Under the artificial intelligence we have the machine learning. So it's a sub area of artificial intelligence, and it refers to the mathematical or computer algorithms designed to teach or train a computational models to solve a problem or perform complex tasks based on some input parameters. And this machine learning, it can be categorized into three types, that is supervised learning, unsupervised learning, and reinforced learning. So it's a computer science. A computer scientist can understand it in a better way. Now, what are the applications of machine learning in toxicology? In a very simple terminologies, especially for the students, that it can help in predictive modeling, that it predicts toxicity based on chemical structure and its properties. Then data analysis, it analyzes the large data sets from various sources. It also helps in silico testing, that is simulation can replace the animal testing. Then toxicity profiling, it generates comprehensive toxicity profiles of the chemicals, and it also helps in literature mining. So these are broad applications of machine learning in the area of toxicology. It also includes the applications in the area of especially preclinical toxicology, the risk assessment, toxicity prediction, and biomarker discovery, especially in areas of pharmacology, that it can be useful. So researchers, they use the ML to predict the toxicity of new compounds based on the whatever the existing data is available. I have discussed, the data availability of the data is more if data is available, large number of data is available, then it's better, or it gives a good result as compared to the narrow data. Machine learning provides an excellent opportunity to bridge the gap between bioinformatics and chemoinformatics and quantitative structural toxicity relationship modeling. So ML and AI, it can have several, it is being used now in several sub-disciplines of the toxicology, and there are several good papers are available, and that includes in the areas like neurotoxicity, cardiovascular toxicology, nanotoxicology, toxicokinetics, dermal toxicity, and carcinogenesis. This you can refer, and good number of data and the papers are available. This all specifies the use of this technology in the various sub-disciplines of toxicology. This is the showing a timeline of the applications of machine learning, artificial intelligence, and PBPK models. So as you know, the blue line you can see the first one, that is this one. So you can, this is a development of PBPK models, or its timeline, how it started developing from 1930s, and then slowly it has integrated from 1900 to the onwards. It has also integrated with the AI and machine learning, and now today the PBPK models, there also we are using the AI and ML. Similarly, say QSAR also, where there is along with its development, we have used these technologies in development of the QSAR over the timeline. So this shows that these three are the important areas, that is PBPK models, then QSAR, and along with it the AI and ML. These are hand in hand, has developed over a time, and we have reached today that it is going to give the good results. What are the machine learning techniques which can be used in the areas of toxicology? There are various techniques, as I have discussed earlier also. That is supervised, unsupervised, and reinforced techniques. And these techniques, they analyze large data sets and uncover the patterns which are not previously noticed. So they give us a prediction that this is based on the available data, this chemical may give this type of result, and it may lead to the such type of the toxicity. So that can be we can get from such type of the data using the machine learning techniques. It can improve the outcomes through the predictive modeling, and understanding this technique is key to the applying it into the toxicology. So these are some of the computer science students techniques. They can know it better. Like say machine learning, there they use the random forest and support vector machines techniques which are being used. Then in deep learning, the computer science students, they use the convolution neural networks and recurrent neural network. This is like networks which are there in our central nervous system. These type of the neural networks, they are being developed, and it can be useful in predicting the outcome. Then we have a QSAR modeling, which everybody knows. How the machine learning works, or what is the workflow of the machine learning, how can we use it? So first and the foremost step is, first we have to define the problem, define a machine learning problem, and then propose a solution. So this is like what we do in the thesis, that you propose a problem and we have to find out a solution. So this is like you propose a problem, and then we also want what type of result, or what we want to have as a hypothesis, what we want. Then most important, as the data collection or availability of the data set is very important. Then this data which is available, it should be transformed, and then for a selected features, then choose a train a model, then test the model, and then apply the model to make the prediction. So this is in general the workflow of the machine learning, where it can be applied for the toxicity prediction. There are several models, or successful applications have been developed in certain areas. So I'll be discussing few of them. Several studies have been successfully are available, or certain softwares are also available free of cost, and one can also test it. So these models, they are available in the area of neurotoxicity. They are also available in the area of skin sensitization. These are some of the models which are available, which we can use, and that can be tested. So one of the important area where usually in toxicity we first do is median lethal dose or median tolerated dose studies. So this can be predicted by using certain machine learning techniques, and this is we know that this is a primary requirement for any toxicity studies. So this can be done, and several in silico methods, they provide reliable information. And today there are many acute oral toxicity study models are available which can be used, and we can predict the toxicity of the compounds, like say multitask deep neural networks to predict the LC50 and LD50. Then deep acute oral toxicity model and ETOX prediction model. So these are all models developed by industry in collaboration with others, and these are available. This can be used, although complete features are not available, but this can be used to predict the LC50 or LD50 of the compounds. Then some models, say scientist Mirrelli in 2020 published a paper where he proposed a model for rats acute oral toxicity prediction, and he used some data sets developed by the Center for the Evaluation of Alternative Toxicological Methods and Environmental Protection Agency, National Center for Computational Toxicology, and in collaboration with all these, the scientists has evolved a model which can be used for the prediction of the acute oral toxicity in rat models. Then importantly also, as we all know, drug-induced liver injury is a major problem that can, if it is predicted at a very early stage, then we can save a lot of money, and we can save a lot of time also in developing the drugs. So this is one of the endpoint of high concern, since it has been a leading cause and clinical trial failures and drug withdrawal from the market. So this is a major reason for the drug withdrawal from the market, and as of today, more than 700 drugs have been reported to be associated with hepatotoxicity since many years. And in silico drug-induced liver injury models, prediction models are also required to estimate the potential drug candidates which can produce such type of the hepatotoxicity, which we can predict at a very early stage, and that can be put to use, and chemicals can be withdrawn at a very early stage so that we can prevent the hepatotoxicity. So some of the models which are developed and they are being available in the domain of machine learning, that includes the liver toxicity knowledge base, then liver tox and hepatox. These are some of the models proposed by scientists in collaboration with the data sets, and these are models available for testing. Then one of the important area in preclinical toxicology also skin sensitization. As we all know, student of pharmacology toxicology, that we use the rabbits and guinea pigs and other animals for skin sensitization test. So physicochemical properties have been used as an important parameter to predict the drug sensitization of chemical substances, and approaches to evaluate the relationship between the physicochemical properties of the drugs or the chemicals and skin sensitization can be correlated, and certain models can be developed which, based on the physicochemical properties of the compound, it can also predict the skin sensitization of the compound, and that can be predicted at an early stage. So there are certain such type of the tools or softwares are available, like OECD QSAR Fulldocs and ChemTunes or TOX GPS. These are some of the early stage models available for skin sensitization. Then carcinogenicity testing. This is also a very important area. If we predict a chemical to be a carcinogen at a very early stage, then that compound can be dropped at a very early stage so that we can save the money. And there are many machine learning models, they are under test. So one of the model, that is deep Kirk model, has been found to be little bit success, and it predicts carcinogenicity of small molecule using the deep learning based model level, and it has been developed with data set of 692 chemicals and evaluated with a test set consisting of 107 chemicals. So this is one of the machine learning model which is available to predict the carcinogenicity. Then neurotoxicity is also one of the early prediction can be done, and in preclinical testing it requires a lot of time, budget and resources to explore the neurotoxicity of the chemicals, but with the use of the computational modeling for drug induced neurotoxicity with machine learning methods and the insight into the structural characteristic of neurotoxic chemicals, and these are some of have been attempted, and some of the based on the clinical drug data with neurotoxicity effects, researchers have developed 35 different classifiers by combining 5 different machine learning methods and 7 fingerprinting packages. And these models, they are freely available on net, and this can be assessed on the web server, that is DiNeuro T Predictor. This can be tried, and one can use this to predict the toxicity or especially the neurotoxicity. Then one of the important one is acetylcholine esterase. As we all know, it's a neurotransmitter, and it terminates neurotransmission by hydrolyzing the acetylcholine. And so this Pulikal and co-workers in 2022, they developed certain models. So using this, they can develop certain analogues of this, and several enzymes can be identified, or certain can be identified, and then they may target this enzyme. So this toxicity that can also be prevented if we use this model developed by the scientists. Then there are adverse effects of chemicals on the gut microbiomes. So this can also be predicted. Then we can have a early prediction. So this can be so scientists, based on the data set consisting of the effects of 197 drugs on the in vitro growth of 40 representative strains of gut bacteria, a machine learning model to predict whether the drug impairs the growth of 40 gut bacterial strains based on chemical structure features was being developed, and it is being tested, but still it is under the developmental phase. So this is again a model which may in future comes, that we can predict the effect of the chemicals on the gut microbiome. So they have used different models further in detail, like extra tree model and random forest model. These scientists have used, and they make the prediction of the effect of chemicals on gut microbiome. Then as I've discussed earlier, the skin sensitization, there are many scientists, they are working on developing these models for skin sensitization, and one of such model developed and reported by Wilm in 2020, that is a skin Dr. CP, that is a machine learning model has been developed, and it has been put to test, and this is being also this is simulating the local lymph node assay, where this model can predict the skin sensitization, or the it can predict the skin sensitization in early stage. So this model has an advantage that it assigns compounds to actively classes only if a defined minimum level of confidence is reached for the individual prediction, and this eliminates the need for applicability domain criteria. that often are arbitrary in their nature and less flexible. So this is a good model, but still under development. And what is the limitation of this skin sensitization machine learning model? That it did not obtain satisfying class-wise results. It validates obtained from non-sensitizers also, and it is weak to moderate sensitizer and strong sensitizer to extreme sensitizer. So still it is not completely satisfying the criteria which is a minimum required, and this model is in consequence unable to reliably identify strong to extreme sensitizers and suggests that other tertiary models derived from the currently available LLNA data might suffer from same problem. So still this model is under development and it is having some say lacuna, and this is also available under the net for free say applications. Now coming to the say end towards my presentation, I'll be discussing some of the challenges in implementing the machine learning in toxicology. As I have discussed earlier, most important one is availability of the data. If the sufficient data is not available, then any model that cannot predict accurately what is happening. So data quality, data availability, and the complexity of the toxicological information can hinder the progress of the machine learning models. The interpretability of the machine learning models is crucial for regulatory acceptance, and researchers must strike a balance between the innovation and compliance with the safety standards. Addressing these challenges, it is vital for broader acceptance. So slowly it is being accepted by the industry. Still it is in academia, or it is still interacting between academia and industry, and it is in future going to be there. Then what are the regulatory perspectives of the ML in toxicology? Regulatory bodies are beginning to recognize the potential of machine learning in toxicological assessment. Guidelines are evolving to accommodate data-driven methodologies and alternative testing strategies. So world over, the regulatory agencies, they are now adopting these technologies, and they are developing the guidelines, SOPs for including this into the regulatory umbrella. Establishing standardized approaches for machine learning applications is crucial for consistent evaluation. Collaboration with researchers can help create robust frameworks for the implementation, and understanding regulatory perspectives is vital for successful integration of the AI and ML in toxicology. What are the ethical considerations for in using the machine learning? Adopting machine learning in toxicology raises the essential ethical consideration, because there are issues with the people that they do not want this to be introduced into the toxicology. Researchers must ensure data privacy and protection, especially involving the human data. This is a very big issue, and the researchers must be ethical in providing or having this data. Then transparency in machine learning algorithms is crucial for maintaining public trust. Ongoing dialogues about ethics will be necessary as technology is advancing, and the ethical implications must be addressed alongside the technological progress. So this is this can progress along with the technology, that ethical issues should also be considered or should be discussed along with the development of the AI and machine learning, along with the advancement in the toxicological science. So at last I would conclude with few lines. That is, only one line can conclude my talk. That is, AI and machine learning is a transformative techniques in the domain of toxicology. The integration of ML and AI signals a transformative era in toxicology. artificial intelligence and machine learning offers unprecedented opportunities for improving chemical safety assessments. It promises to enhance efficiency, reduce cost, and minimize animal testing. As the field evolves, collaboration and ethical considerations will remain paramount, and the future of toxicology is intertwined with the innovation. So both should go hand in hand so that these technologies can help to improve the chemical safety for the benefit of the human beings as well as the animals. Thank you everyone for your attention. So now it's time to earn the stones.
AI can provide accurate predictions, but it doesn't offer a clear explanation. So if we talk about neural networks, so there is input, the hidden data, and output. So is it okay to rely on that output?
Not 100% we can rely. Ultimately, people say that we need to test the chemicals in biological system. But this is early predictions can we do that based on the past data, what is available, based on the chemical properties of the chemical and other properties of the data sets available, we can predict at an early stage that this chemical is going to be producing a hepatotoxicity. Then why to test it? Why to go ahead with its testing? Let us drop it from that point. So that is where the artificial intelligence will help us to reduce the cost of the testing, and it will reduce the further investment of the time also.
Yesterday, there was a publication that came out from Inspiro, which is a company, Switzerland-based company, but they are doing a lot of these 3D organoid models, spheroid models, etc. They collaborated with the National Center for Toxicology Research in the Arkansas in the USA, and they probably screened about 155 compounds that are actually clinically either successful or failed due to the hepatotoxicity.
Yeah.
And now they have a database. This kind of database is not there in artificial intelligence yet. So how do you build the artificial intelligence database without any clinical data? This is my question to Dr. Miller also yesterday. The thing is, we don't have enough data. This is the databases we need to create, human data.
Yeah.
That data is now coming with the spheroid models and organoid models. I'm also building 3D bioprinted models. So these kind of models are required to retrospectively evaluate, create a database, then you can put them into the artificial intelligence database. So this is where I'm saying it's too mature to say that I can predict with the artificial intelligence model. That's my comment.
You are right.
You want to comment? I agree with that. So that's my opinion, but
No, I agree with the point. And that's where I know, at least in the U.S., NIH is really trying to address the issue. One of the problems is that clinical studies were never designed to actually generate data to be used for modeling. That's a big problem with all the modeling, is that we do experiments without the idea of how the information is going to be used. And the only way to try to develop standards is actually through a government saying, if you want money from us, you're going to have the data publicly accessible and presented a certain way. And those are kind of standards that are coming into the fore now. There's a lot of data that's really ugly and messy, and data structure is the big problem. So one of the NIH is trying to do is actually they have grants out to have people give them money and figure out how can they extract data from all the clinical studies and structure it so that you can actually use for modeling. But the big problem is that either the data is not accessible or it's not structured right, and building a database is extremely hard, and it's not very exciting. So that's where you need the government to come in and say, well, I don't care. I'm going to pay you to do it anyway. But until we get that data, I agree with you, there's going to be a lot of either challenges in terms of the practicability to make the models work, but two is belief. You can make all the models you want, and people don't believe the outputs, which kind of goes to the question, it doesn't matter. And so that's where people are going to have to believe in it, but it's going to have useful information and trust those outcomes. So to me, I believe the field is moving in that direction, and mainly because enough government money in the U.S. and I know in the EU, they're investing in it to make that kind of happen.
Right next to NCTR, so.
Oh, wait, that's where, yeah, a lot of the, all these models out there, that's where they're aware of it too. They're reconstructing their whole database and how people can report adverse effects to the FDA. They're formatting and standardizing it with a specific purpose to develop models. And they develop their own. That actually the deep CARC is developed by the FDA. There's also Deep DILI and a lot of other deep neural networks made by the FDA. My question to them is that they're making all these models, but they don't accept the data for regulatory purposes. So my question is, why are you doing that? It's interesting. But yeah, the big problem is the data structure is a huge challenge. But that's where it needs to be international, because people doing research everywhere. But we need to do it some kind of systematic way that makes it conducive to AI work.
My opinion is do the prospective spheroid organoid models and then take that data into the AML model. This is my vision of really structuring the database.
Yeah, it's a problem. That's right. I think it's moving in that direction.
Yeah.
I just have a quick question. It's a good talk, but what is the role of AI, in particular in orphan drug development, and what are the ethical issues? Because you know that now the rare disease is all over. Orphan disease, orphan drug development, I think all over the world is because the focus is on because of the advancement in the technology. So how do you see the role of the AI in development of the orphan drugs, and what are the ethical issues that are going to emerge from that? Can you just point on ethical issues? Come on.
Still, I'm also learning this, so I don't have much idea. If you have some, I know.
Well, those issues have gotten up with discussions, and the meetings have gone to the FDA's there. And the issue is that in terms of liability, what is the difference of relying on a model versus an animal? Neither one are going to be 100% accurate for a person, especially on the individual basis. So that's where the government's dealing with it, because the only one who can accept responsibility is more of the government. Because the company can quickly go bankrupt, and that's why we have a regulatory process to normalize everything. But in the regulatory process, basically the government's saying is that we're responsible for everything, and we're going to take it on the chin, and we're going to have everybody do it this way, and it may be imperfect. But that's the issue that's getting discussed now, is the methods we're using now to approve drug safety don't work. I mean, how many drugs get withdrawn once they're in the market? Because even clinical studies don't reflect the diversity in the population, the challenges. So the system doesn't work now. So worrying about AI not being perfect, I think, is missing the point. It's never going to be good. The question is, can it actually do what we're doing now, but do it even a little better? Doesn't have to be a lot better, but a little better, because it has a lot of other benefits that you don't get from other studies. But I know at least in the U.S., on the regulatory level, that discussion's been going on, and they're trying to more formalize it. So I know it's moving that direction. I know the EU's kind of moving that direction as well, based on their policies of trying to eliminate animal studies and replace them with AI and other kind of approaches.
So I think just to add up here, I completely agree. And the way forward is just to generate more and more data. So I think as much as data you have, I think that the predictability would be better. So that's what we need to work on. So as Mani mentioned, it's true. But still, we just have to keep doing it. Like we used to do it in silico, right? I mean, you have a lot of compound libraries. You just try to learn from that. Still, you can't predict it correctly, but at least it helps you somewhere. So the way forward is just keep generating data and implement in our AI modeling so that those predictions would be much better.
Yeah, in 1993, when I was a senior scientist at American Cyanamide Company, LASA came there. They had the fresh direct model, but that was completely environmental toxins. There was no drug or pharmaceutical database at that time. If we evaluated it from our own perspective with the failed compounds, but what happened was that data is proprietary to American Cyanamide Company. It cannot go into the database of the private databases like the LASA. And then they came up with, FDA worked on multi-case, another toxicology, especially these are genotox models. And then somebody else came up with TopCat. And at J&J, we analyzed all these three models with failed about 80 compounds which are mutagenic, which never went into the clinical trials, and about 800 compounds which went into the clinical trials. They failed for other reasons anyway. We don't want to talk about it. So we looked at all the database, and these 80 compounds, when we put into direct, multi-case, and TopCat, we got 30%, 30%, 30% predictive value. None of them gave 100% predictive value. So you need to add more robust data into it, actual, to create these models to be predictive rather than half predictive. 1/3 predictive data doesn't mean anything for the clinical, for progressing into the clinical trial.
No, absolutely right. And as we had discussed yesterday, now there's a lot of pressure not to use animals.
Right.
So what are our options available? You still need to now depend more on such tools like AI tools, which can give you some better data predictability. So, and as he mentioned, for the regulatory acceptance also increases. I think that will further boost to generate more of such data.
Yeah.
So, yeah.
Okay.
All right. So thank you, Mani, and maybe hand it over to you.
Yes.
In interest of time, we will take the question after the other talk because we'll try to catch up with the time. But you won't miss on your little rock. So just mark him. You need to give one rock to him. So after this talk, we'll take your question. Yeah. Thank you.
Very much thankful to Dr. S.K. Bhavsar for delivering a wonderful talk, especially the core and basic concept of the AI and ML in the preclinical toxicology. And I think most of the students and researchers have cleared the concept of the AI and ML in the preclinical toxicology. May I now request Mr. Grover to present a memento to Dr. S.K. Bhavsar, Director of Research, Dean PG Studies, Kamdenu University. Thank you, sir, for joining our conference and sparing the valuable time with us for your lecture. Now we have a second speaker, Dr. Shailendra Pratap Singh. He will deliver the talk on the utility of the internal exposure and physiologically based toxicokinetic modeling in advancing the health risk assessment of the chemical. Before I invite, I would like to have to summarize his biography. Dr. Singh obtained the MPharm from the Manipal College of the Pharmaceutical Science. After completing the MPharm, he worked as a scientist at the Metabolism and Pharmacokinetic Division of Dr. Reddy's laboratories. He joined the PhD at Pharmacokinetic and Metabolism Division, CDRI, Lucknow. In the year 2011, he completed his PhD and joined the Biocon Bristol Mayer and Squibbs R&D Center. He joined as a scientist in 2014 in the Regulatory Toxicology Group at CSIR, Indian Institute of Toxicology Research, Lucknow. Presently, he is principal scientist and scientist in charge of the toxicokinetic laboratory at CSRI, IITR, Lucknow. He is also in charge of the NABL facility for the pesticide residues analysis in low-fat food committees, proteomics and metabolism facility at the CSRI, IITR, Lucknow. He is doing contributing in the area of the physiologically based toxicokinetic modeling, proteomics analysis for the disease biomarker identification, bioanalytical method, development and validations for the chemicals, exposure analysis, pesticide residues and contaminant analysis in the food commodities for the intake assessment. He has published more than 85 papers and several book chapters. He is the recipient of the Young Mass Spectrometric Award by the Indian Society of the Mass Spectrometry. He is a national assessor for the NABL ISO 17023. Apart from this, he is the member of the sectional committees for the fragrance and flavor, for the environmental services, pesticide as well as food safety and standard authority of the India. There is it is very tough to summarize Mr. Singh in 2 or 3 minutes. I humbly invite Dr. Shailendra Pratap Singh for his talk. Please, sir.
Thank you so much, sir, for the kind introduction. So, you can hear me, right? Okay. So, first of all, I would like to thank the ACS, this particular Indian chapter first meeting, and it's my privilege to be part of this first meeting, and I would like to thank Dr. Deepak especially for that. Okay. This is for pointer.
You can use this yellow button for the pointer.
Okay.
And then you can change from here forward and backwards.
Okay. 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 Thank you. So, generally, whenever you will see that most of the time the conferences or the workshop which we attend generally focus more on the pharmaceuticals, right? So, very few conferences you will find which really focus on the xenobiotics as such, the whole category of xenobiotics, covering the environmental hazards as well. So, I think I must appreciate that taking up this particular topic and covering the environmental chemical, pharmaceuticals, the metals, other kind of chemicals, and especially I am going to focus on that how we can use that internal exposure, okay, because most of the time when we talk about any kind of toxicity, so it is the internal exposure which matters rather than the external exposure, because everything, whatever we take, either it's a drug or any chemical, so whatever amount or the concentration of the any chemical reaching to the site of action is the matter of concern, right, in terms of the toxicity angle. And you must be knowing very well this particular physiological based toxicokinetic modeling. This is now being used I mean too much I would say in the area of let's say the drug discovery as well in the area of toxicology. If you will see that the drugs are like a very small number of chemicals, whatever we are exposed to and whatever chemicals we see in the environment. So if you look at that, what are the different sources for these chemicals, right? It can come from everywhere, like it's from the air, start from the soil, water, and different kind of products which we are using. Let's say that kind of the wood material which is here and different kind of painting is there, right? These all are like made of the chemicals. Similarly, the different kind of foods which we eat also contain different chemicals which could be some beneficial, but there are several chemicals which are unintentional, or even the intentional also you can find, because different kind of colors, food additives, these are intentionally added into the different kind of food products. So we are exposed to multiple of chemicals. When we talk about the drug, very systematic studies are done, starting preclinical and clinical. We have the very robust data. But when we talk about the chemicals, I think I would say that we have very limited data related to the toxicity, or even let's say from their occurrence, or there from the regulatory evaluation perspective. So whatever effect we see for any chemical, let's say it depend on the type of chemical which we are exposed to and amount. As I said, that amount will matter, okay. At the same time, how long and how often we are exposed, because there are several chemicals we might be exposed for, there could be acute exposure, but there could be several chemicals which are slowly we are exposed to for, let's say, our entire life, okay. So to evaluate this chronic effect as well as the acute effect, different kind of toxicity studies are being done, and even in India also now a lot of efforts are being given to that, like how we can reduce the animal uses, as we are talking, we are listening about the AI and modeling simulation. So if you see that there are the different chemicals, you can find the different source of these chemicals, and I have listed certain chemical class so that you can understand what different kind of chemicals we are exposed to. Pesticides, these are intentionally added, right? Because we know that we have to grow the crops, right? And for that we have to use these pesticides. So there could be some residues of these pesticides in the food. That is there, definitely, because We are also part of one monitoring program where we are monitoring the pesticide residue in food. So we know that what is the exact status of in our country, whether what are different kind of pesticides which are present in the food. So these pesticides are there, but they are within the limits. So every chemical has certain limit, right? Like a drug. Even if you take the drug molecules like in excess, it could be a toxic. Similarly for the chemicals. So we need to understand how much is the exposure to the individual and what is the toxicological threshold for that particular chemical. If we understand these two terminology, we can really control, we can form the mitigation strategies, and we can do the risk characterization for any chemical. So if you see that the pesticide, food colorant, mycotoxins, these are very common. You will find that corn and all these are rice samples. These are commonly contaminated with different kind of fungal toxins. So these are called the mycotoxins. Phthalates, which are used in different kind of plastics. Similarly, polychlorinated biphenyls, and you can take the phthalates, triclosan, which is primarily used in the as an antibacterial in the detergent and the soap or shampoo. Pharmaceutical agent we know very well, but when we talk about the environmental chemical, this pharmaceutical agent is really coming from as a, let's say, the outflow of different hospitals or the medicine which are discarded. Those come into the water bodies. Similarly, the bisphenols, which is one of the very, very major class which is present in the different kind of plastic material or even the canned food which we take. So the epoxy resin coating, whatever is there in the different canned product, it is made of the bisphenols. So these chemicals have the different kind of effect in our body, and so because I am talking about the physiologically based toxicokinetic modeling, so just I have included few slides to give you the basic idea. So you all must be understanding very well what is the toxicokinetics, right? So toxicokinetics help us to understand how the any compound is absorbed, distributed, metabolized, and excreted from the body. And from the perspective of drug discovery, if you see this particular toxicokinetics is being used in dose and species selection toxicological studies, especially if you focus on the pharmaceuticals. But and even the interpretation of toxicological studies, we do the toxicological study very well for all the pharmaceuticals. But especially when we focus on the chemicals, the two additional category comes, which is the refinement of default uncertainty factor. Okay, I will talk about this in coming slide, and interpretation of biomonitoring data. So coming to now to the physiologically based toxicokinetic modeling. So you understood the toxicokinetics. Then what is the physiologically based toxicokinetic modeling? So this is the interconnected compartment. So the body organs are connected in. Sorry. Okay. Can you please put it? Yeah. Okay. So yeah. So our body is connected into different compartments. Okay. Different organs are being connected through the blood flow. So these all there are different kind of software which are already have these all defined parameters. All physiological volume, blood flow, tissue composition, everything is well defined in the different models. But we have to generate the chemical specific data. Okay, if suppose I wanted to simulate the profile for different chemicals, then in addition to this particular all data related to the body weight, flow, blood flow, GI transit time, we have to generate the ADME data, which could be the in vitro or in vivo, or even we can use the in silico models or AI modeling tool we can use for predict different kind of parameter which are required to make these kind of models. So advantage of these model is that you can simulate the dynamic simulations can be done. You can predict the concentration of any compound into different organs, even blood and the other organs. Now coming to the concept of hazard and risk. Remember that anything whatever is present on this earth in terms of chemical is hazardous in nature. Okay. Even if you see that any chemical, if I am taking very less amount, it may not be the hazardous. Okay. But if I am taking the more amount, it could be hazardous in nature, right? So when we talk about the risk is proportional to both hazard and the extent of exposure. So when we talk about the chemicals, the chemical risk assessment become more important. Then we have to differentiate what is the hazard and what is the risk. So any chemical can have the hazard, can produce the harm, but it is the actually dose which will decide whether it will be harmful or not, right? So for that, important component is the exposure. So we need to understand what is the exposure, and if we combine together, we know the risk. So similarly, for each and every chemical, we have to understand what is the hazard, and we have to estimate what is the intake for us. Let's say if any chemical pesticide is present in the food, I have to know that how much amount I can consume in a particular food, and if suppose X concentration is present in that food, how much will be the exposure to me for that particular chemical, and then we can assesses risk to the human body. So, coming to the risk assessment process, so now we understood hazard and the risk relationship. If suppose I wanted to carry out the complete risk assessment for any given chemical, so it is different from the drug. I mean, if we wanted to understand what is the particular risk to a particular chemical, then we have to understand, we have to first identify the hazard. Okay, we can carry out the in vitro studies or in vivo animal studies, just like a preclinical toxicological studies. We can generate a lot of data in terms of hazard identification. Next is hazard characterization. It means whatever data we have generated from the in vitro or in vivo experiment, we have to develop a dose response relationship, and we have to drive certain terminology which is called the NOEL, ADI, TDI. NOEL is nothing but very common terminology in the field of toxicology, which is no observed adverse effect level. It means the dose where we will not see any kind of adverse effect. Okay, so we have to understand this particular NOEL for each and every chemical. Then only we can predict the risk for the human being. And ADI is the acceptable daily intake. It means that if I am exposed to a chemical enter my life, that is called the ADI for that particular. Let's say this could be the X dose. ADI, acceptable daily intake. It will produce no harm. Okay. So when you have the toxicological data, you can calculate the acceptable daily intake. Similarly, the tolerable daily intake, TDI. This terminology is used for the contaminants, TDI, because we cannot say the acceptable word for them. But things which we are adding intentionally, like the pesticide which are being used in the different crops, for them we use the terminology ADI, because for those chemicals we generate the systematic data. Just like a pharmaceutical, pesticide data also generated very systematically. All the trials are being done in the fields, and based on that certain limits are fixed for different crops, and if anything exceeds beyond that, then it could be harmful for the human being as well. Okay. So once you have done the hazard characterization, next is the exposure assessment. Okay, now I wanted to know if suppose this particular chemical is having this particular X number of NOEL and the ADI, how much is the exposure to the human being? Okay, so exposure to the human being will be decided by quantifying the hazard exposure level. So what we have to do, we have to understand, let's say if I wanted to know how much will be the pesticide exposure to an individual, then I should know how much of the chemical could be present in that particular food. Okay, and how much amount of that food is consumed by a person in a daily basis. Okay, so then you can calculate the amount of that particular chemical. So then you can compare that amount from this step with this particular data, acceptable daily intake or NOEL data, and then you can assess the risk. So this is called the risk characterization. So based on this, all the information, we can do the risk characterization to the human population, and this will tell you how does the estimated exposure is this one, compare with the health-based guidance value. Health-based guidance value is nothing but the acceptable daily intake or tolerable daily intake. This value we will find for most of the chemicals. So coming to the current practice of the risk assessment for these particular chemicals. Okay, so when any kind of toxicological study is done, so people derive this NOEL value from those toxicological studies, and then they apply certain kind of safety factor. Because these studies are being done in the animals, and this data has to translate it for the human being. So we have to overcome this particular this differences in the system. Okay, so for that reason, safety factor is being used, because there could be a lot of uncertainty from translating data from animals to the human being, and the human itself can have different kind of variability. Okay, so this safety factor is generally of 100. Okay, this 100-fold safety factor in general is applied. And then we calculate the ADI, which is called the acceptable daily intake. So NOEL is coming from the toxicological studies, then safety factor is applied, then we are calculating the ADI for a particular chemical. And how this 100-fold safety factor came, this takes two components into the picture here, the toxicokinetics and toxicodynamics. Remember, for any chemical, these are the two fundamental parameters which will determine the effect. Either it's drug or it's any chemical. Toxicokinetics and toxicodynamics. So there could be a difference in these two parameters interspecies in the toxicokinetics as well as in the toxicodynamics. Similarly, this human variability could also be there for toxicokinetics as well as toxicodynamics. A person could be more sensitive and another person could be less sensitive to that particular chemical. So these are the default factors which based on certain pharmaceutical data analysis, where we have the data for animals as well as for the human being. Because particular for the pharmaceuticals, we conduct the clinical trial. But for these chemicals, we cannot conduct the clinical trials, right? So this learning from the pharmaceutical field is applied here for this 100-fold safety factor. So generally it was seen that, okay, this much safety factor is good enough to cover these kind of variability and to derive the safe dose for the human being for these kind of environmental chemicals. But nowadays, this kind of practice was being started, let's say 1980s until 2005 or 2007. Still, it is going on. But now the people are focusing more on the chemical specific adjustment factor, okay, which is called the chemical specific information we have to generate, rather than going with the uncertainty 100-fold safety factor without knowing that whether the 4-fold safety factor was good enough for toxicokinetics in the animal versus human being. We really do not know. Okay. So can we generate the chemical specific information? Can we predict the kinetics profile in human being for the chemical? Can we predict the kinetic profile in the animals, and then we can compare the kinetics of both the molecule in animal as well as a human being, and we can use the real data for the deriving the acceptable daily intake. So we can modify the safety factor by having the toxicokinetics and toxicodynamic data for each and every chemical. But it is very impossible job, I would say, because there are thousands of chemicals for which it is impossible to generate so much data, and especially if we wanted to conduct the animal studies, right? So that for that reason, the 21st century risk assessment is moving towards the alternatives. So I think I think sir was also talking about that he's also working on some 3D models, and in fact I also got some opportunity to hear to him, I think in one of the institute where they were presenting their model system for, I think for cancer, sir, you were developing, right? So there are different people who are working in the 3D model development. So reason is to move to the alternatives to the animal approaches. So we can use the in vitro model, we can use the 3D based model system, more realistic you can say. So the how this particular phenomena is like related to the adverse outcome pathway, okay? This is called the bottom up approach 21st century toxicity evaluation. It means we have to understand what, based on the in vitro studies, what particular target is being affected. Because remember that whatever effect we see, either it's a dynamic or toxicodynamic effect, toxicity, is always initiated with certain molecular events, right? So we have to identify those key events from the in vitro experiments. And then probability of outcome in terms of the phenotype we can predict. Okay, so for that reason we have to have the in vitro test system for different kind of endpoints, because there could be n number of endpoints for different kind of toxicity. So based on this particular aspect we can understand the adverse outcome pathway from the in vitro test system. But if you see, normally the current approach is, this is the top down approach we do at the organism level, tissue organ and then cellular level, and then we understand the adverse outcome pathway. So this approach is different, top down, which is primarily the animal based, and this bottom up approach is primarily the cell based, system based or in vitro test system based. And you will find that US EPA has generated the data for more than 4,000 chemicals in battery of in vitro tests, where they have used different kind of in vitro test systems, where this data is already available in the public domain. And in fact, we are using that data because this is the data which is systematically generated with the standardized protocol, so that there is a minimum variability across from the different laboratories the data is coming, right? So from the single source, 4,000 molecules, data is being generated in more than 100 or 200 different kind of in vitro assays. So now the major challenge is with the in vitro test system is that how to translate this in vitro data to the in vivo context. Because finally our aim is to understand the toxicity in the human being, right? Or the safe exposure level for the human being. So again here the PBTK based reverse dosimetry approach will be very useful. Remember the terminology, reverse dosimetry. What we are doing here is we are translating the concentration effect into the dose effect based on the PBTK modeling approaches. So we are converting that at what dose, this particular concentration at what dose it will be achieved in the human being or in the animal models. Because only in vitro test system will give you only the concentration and response data. Okay. So this is the challenge, and another aspect is that how we can use this PBTK modeling or reverse dosimetry approaches for interpretation of the biomonitoring data. Let's say if today we collect the sample from this particular hall, the blood sample, or let's say the urine sample, and we do certain chemical analysis. We found certain level of chemicals in our blood. Let's say some pesticide levels was found in my blood. So can I say this is toxic? Because we are intentionally permitting to use this particular pesticide in different food items, right? So then definitely some residue could be in my blood. Okay, it is quite possible. But whether it is harmful or not, how you will know? Because it's only concentration. But what we have derived from the toxicological study is the dose. Acceptable daily intake, that was the dose. We were not having the concentration relationship. We were not having the dose versus concentration relationship exist because we were not having the data for the human being. At what particular dose, how much will be the blood exposure. If I know that at NOEL level or acceptable daily intake level, how much blood concentration could be there in the human being, then I can say that, okay, up to this blood concentration, this chemical is not going to produce any harm, right? So based on concentration also you can tell. But for that, you have to have understanding of the clinical kinetics data. So again, we cannot do the clinical trial for these chemicals, so we have to again rely on the different kind of modeling approaches. And this is the physiologically based toxicokinetic modeling, again will help you to predict the concentration time profile in human being for different doses. And then you can easily interpret the biomonitoring concentration data which is coming from different kind of toxicology biomonitoring program in different country. Another aspect which I was talking about, amount. If I wanted to know that how much amount is present in my food. So this is the approach which is being used. So which substance are present in what amount in a given food diet, how much of these food containing these substances are consumed. Okay, so let's say the rice. Okay, we consume around 200 to 250 gram of rice every day. Okay, in general, if you take rural versus urban, and if suppose X amount of chemical is present, then I can multiply that concentration with this particular amount of food consumed. Then I can calculate how much of the pesticide I am consuming in a day. So this is how the simply calculation is being done for the amount of any particular chemicals which is being consumed by everyone in day-to-day life. This is a very simple aspect, especially focusing on the food additives or colorant or even contaminants or the residues which are from the pesticide or veterinary drug. So based on these all background, now coming to some of the key experimental data which we have generated in our lab, where what we did, we are trying to actually predict the developmental toxicity for different chemicals from the in vitro data. Okay, and why we have chosen particularly the developmental toxicity, because most number of animals are being consumed in particularly developmental toxicity studies, because first generation studies, second generation studies, so lot of animals are being consumed in this particular kind of studies. So we have generated data for certain class of chemicals. We have generated data for pesticide class of chemicals. This phenerimol is a pesticide. Okay. So what is our approach is, here is we take the in vitro toxicity assay data which is from the literature or we can generate. We take the activity concentration, 10% activity concentration. I mean, you have to differentiate the response from the control, right? So 10% difference we have considered as a minimum threshold, and we call it the point of departure. Point of departure means from this particular concentration you are going to see some effect. Because I am using this terminology because these are used in the chemical risk assessment field, the point of departure. Okay, so based on this particular this particular AC10 data and using this toxicokinetic modeling tool, we are able to predict the human equivalent doses. Okay, so at what dose this particular concentration will be achieved for the human being. So we can calculate based on the concentration, we can calculate the dose for human being. And then we, by considering the variability, human population variability, this can also be predicted from the models. So we can take the upper level of human exposure because we wanted to have the worst case scenario, and then you can compare this in vitro derived versus in vivo derived. So what is the meaning here is, because when we wanted to use some new technologies to particular area of risk assessment or certain kind of model acceptability, first we have to validate those models in terms of predictability with the existing data. So for these particular chemicals which I am going to show, we have the in vivo animal data already existing. So we have predicted the human equivalent doses from the in vitro data as well as from the animal data. So in vivo derived is nothing but we have taken the animal data and that we have translated to the human equivalent doses, and we have translated the in vitro data into the human equivalent doses, and then we have compared together whether these in vitro test systems are able to predict the toxicological outcome in the human being or accurately or not. So this is our approach is very simple. I would say those who knows of the modeling aspect, they will found that we generate some in vitro data for these chemicals, and we generate in vivo toxicokinetic data. If available, it is fine. If not, we generate for those chemicals, and then we build this particular rat PBTK model, and by using the in vitro data as an input, we compare with the in vivo data which we have generated in-house. So this gives us the confidence, okay, our model is able to predict accurately the animal data, at least from the kinetic angle, because human data we do not have. So this particular kind of validation helps us to really give some confidence in our model. And that model, then we use some in vitro data as an input point, and then we calculate the human plasma concentration time profile. So this is how workflow is there, and this is the data which we have generated for the phenerimol. This is the rat observed versus predicted data. You can see there is a very good correlation. So based on simple input parameters, in vitro test parameters, we were able to predict the rat kinetics. So this gave us some confidence, okay, our model system is, nothing is too much off in this particular model, and we are able to predict. Then we predicted the human profile, and the model which we have used is a minimal PBTK model. This model requires very simple modeling aspect, because we are not dividing whole body in different compartments. Rather than we have just put it into the two kind of compartments. One is the peripheral and one is the central compartment. That's it. So then what we did, this is the reported in vitro lowest observed effect concentration, LOEC. This we got from the in vitro data. And this was the this data came from the ESD3. This is the embryonic stem cell data, which is like the beating cardiomyocytes data. So where this chemical is already been studied for the developmental toxicity. And by using the PBTK modeling approach, we have calculated the human equivalent oral dose from this data, and we have also calculated the equivalent rat oral dose, because already we know that from the in vivo experiment what is the lowest observed effect level in the animals. So at the dose at which we are seeing the effect in the animals. So this was the developmental toxicity endpoint in the in vivo hydronephrosis, and this is from the in vitro data, and then we have compared the in vivo data derived human equivalent dose and with the in vitro derived. So you can see that this particular outcome is here. That fold difference was only 1.6 fold. So the in vitro derived and the in vivo derived human equivalent doses were very similar with this particular model system, the embryonic stem cell model. Coming to the biomonitoring equivalent, so because we have developed the PBTK model, so then we thought of predicting its biomonitoring equivalent. So biomonitoring equivalent is nothing but to know that at what will be the concentration in the human blood at a given ADI values or tolerable daily intake values or NOEL values, because these doses will be the dose where there will be no harmful effect to the human being. So for deriving the biomonitoring equivalent, what we did, just similarly, we took the plasma concentration time profile at the acceptable daily intake level, and we predicted the kinetic profile in the human being. And from there, we have calculated the Cmax and C average concentration, and then we put this concentration as a biomonitoring equivalent. If the concentration is going beyond this particular Cmax or C average concentration in our blood, then we can say that, okay, this chemical might be already at the higher concentration in our body and can produce a harmful effect. So this is how simply the data can be interpreted, the human biomonitoring data. Otherwise, if you will see that mostly the epidemiological studies which are being done from different countries, you will find certain chemicals in the blood, and we start saying that we are exposed to so much chemicals. We know that we must be exposing ourselves to the different chemicals, but whether that levels is really high enough to cause toxicity or not, that we have to know. Similarly, coming to the another data is for the endocrine activity for bisphenols. You must be hearing a lot about the endocrine disruptors, right? This is another very big class of chemicals which produce the long-term exposure at very low doses can produce several kinds of toxicity. So what we did in this particular case, already some human pharmacokinetic data was also available. So these are the two molecules, bisphenol S or bisphenol E. So for this particular molecule, we were having the human data as well. So we have verified our human model also with this chemical, and we have predicted for the bisphenol E, which is also being used as a replacement for bisphenol A, which is primarily being used in the plastic bottles as well as in the epoxy resin coating of the different can. And again, we did the same kind of validation, and we found that the rat and human PB model was successfully developed and verified. This is, you can see that predicted data, and this is the reported data, and observed versus predicted difference were within the twofold. So we were very accurately able to predict the kinetic profile. And then what we did, we took the toxicological data, especially for the estrogen receptor related pathways, because the endocrine receptor generally interfere with this particular pathway. So these particular around 5 to 6 model we found from the Toxicast database. As I said, the Toxicast database is already having 100 of different kind of assays. Data is already existing there. So we used that data set, and then we predicted the human equivalent dose. And this for the BPE and BPS, this is the human in vitro data derived human equivalent dose, and these are the in vivo derived human equivalent dose. You can see that the doses which were derived from the in vitro assays were within the within the limits of whatever had been derived from the in vivo equivalent doses. So the endocrine activity assay derived human equivalent dose were in line with the human equivalent dose derived from the in vivo endocrine effect for these particular chemicals. So by having the battery of assays, it is quite possible that we can predict some with more accuracy these in vitro data. We can convert it to the in vivo data, and then we can compare. So this is how we are trying to validate our model system, different in vitro test system, with the already existing animal data. Coming to the another molecule, which is the hexaconazole, which is again azole fungicides class. And why I have taken this particular class of chemical? Because this is one of the major class of pesticide which is being used as a fungicides in our country. So you can see that again we developed the model for this is IV data and the oral data. Both the data we have fitted into our model system, and we were able to predict this pretty well, this data. And the rat model was successfully verified and then extended to the human being for predicting the kinetics. And then the approach which we have followed, this is the simple formula I have listed here, that how the human equivalent dose from in vitro assays was calculated, the activity concentration from in vitro test system. This is the dose at which particular I wanted to make the predictions, and this is the Cmax which came from the human PBTK model. And this is the data came from the in vivo data, where human equivalent dose was derived from the animal point of departure. Again, this is the NOAEL value or the lowest observed effect level values from the animal data, and multiplied with the dosimetry adjustment factor. So we can convert the animal data to the human being, which is normal practice. When we do not have the human kinetics, people generally convert the animal data to the human data just by using some default factors. Okay. And then again we took different test system. I would say here we have taken 3 test system which is most commonly used for the developmental toxicity. So far, whatever developmental toxicity model we have, there's alternatives. These are the 3 model system: embryonic stem cell, rat whole embryo culture, and the zebrafish. Okay, so these 3 different model have certain limitation, and one model is have some advantage over another model, because zebrafish is having the advantage over these 2 models because it will provide the complete span like the human being is going through for the developmental phases. So we did the prediction from these 3 different assays, and the human equivalent dose derived from the in vitro and in vivo, there was a huge difference. So we were not able to predict actually the outcome similar to the animals from these test system, which are most commonly used for developmental toxicity studies as alternatives. And people have validated these models for a number of chemicals by showing that there is a good correlation. Then what we did, again we took the several assays from the Toxicast assays. They have listed around 16 assays which can be used as a developmental toxicological endpoints model assay. And out of those, the test system where it was found positive, 5 was the assays which were found positive. We took the data from that, and then we again predicted the human equivalent dose. So you can see that the prediction from these in vitro test system was very much similar to the what we have observed from the in vivo test, from the in vivo animal data. So this I would say overall here is that the in vitro test data, whatever we are generating from the different kind of in vitro test system, quite useful. And I think we have to validate with more and more number of chemicals so that we can successfully predict the outcomes in the human being, because certainly in coming years the animal will not be going to be used for toxicological testing. So another important class of chemical is the mycotoxins. As I told you that the emerging mycotoxins class are there. So this is the N18 class, which is emerging mycotoxins. So far there is no limit has been set for this particular mycotoxin in either in India or even the abroad. Okay, in any other country, no levels has been fixed so far, because very limited toxicological data exists for this particular chemical. But certain provisional tolerable daily intake values has been fixed for this particular chemical. It means this is the provisional data because we do not have the complete toxicological data. We also did the predictions for this particular chemical at what is the existing scenario. So this was the human biomonitoring concentration data is already been reported for this particular chemical in the human blood, and then we have converted into the dose by using the PBTK modeling approach, and then we have compared this extrapolated dose with the provisional tolerable daily intake. You can see it is already exceeding this provisional tolerable daily intake. It means the people who are like this particular, the blood concentration is greater than the already the tolerable daily intake value. So there is this chemical is of high concern, and certain mitigation strategy has to be formulated by the countries to lower down these levels of this particular chemical. So this is from my side, and at last I would say thanks to the SimSip Certera UK, because for this all modeling work I have used the SimSip software, which is the academic free license I am using, and my funders, because I am having the funding from most of the government funding organization, which is Department of Health Research, ICMR, and the SERB, Science Engineering Research Board. So I would like to thank all of them. Thank you.
So any questions from the participants? Yes.
Sir, very nice talk. Sir, I have two questions. In the case of environmental toxins, there are multiple exposure.
Yes.
So in that case, finding the exposure concentration, and it is also regional, there is a variation. So in that case, how these models can solve that? And another question I have, that in most of the physiological based pharmacokinetics, so mainly concentration or amount dependent. But when it comes to the non-linear kinetics, when their relationship with the dynamics also comes into the place, then how this modeling will work?
Okay. So especially when we talk about the multiple class of chemicals, presently I would say that whatever kind of testing is being done in the animals for the environmental chemical, it is done individually. Okay, we do not have the mixture toxicological data. I was talking to Dr. Grover even in fact on this particular direction, that mixture toxicity assessment is still lacking across the globe, but there are certain strategies people are following in terms of risk assessment, simply by adding the concentration together and then comparing with the TDI values or acceptable daily intake values. So this is a certain strategy people are following without really doing the complete assessment. Another, I would say, especially let's say the flavor and fragrance, we are exposed to multiple flavor and fragrance, right, in different kind of products. So people are even following the approach of the toxicological threshold concern, TTC approach. Okay, so that approach is nothing but you take the worst case scenario, most potent chemical which is toxic, let's say the genotoxic. Okay, there should be some concentration for that chemical which is genotoxic. If my exposure from and other different sources is less than that threshold, it means this chemical is not going to produce any harm until unless this chemical become even the wonder molecule in terms of the toxicity, which is going beyond that the positive control kind of chemical. So this is the different approaches. When we do not have the data, we can use a TTC approach. We can classify whether our chemical is of concern or not, and we can simply then take up those chemicals for further data development. Coming to the PBTK modeling, the best thing is PBTK modeling is that you can even predict the nonlinear kinetics. If suppose I am putting enzyme kinetical data into that particular model system, I can predict the nonlinear kinetics also. And I can also use this PBTK model for mixture toxicity assessment, because in the pharmaceutical drug-drug interaction studies are being done, right? So the same kind of model system can be made for the chemical mixtures, and we can predict the toxicokinetics for the mixtures. And then if we can predict the toxicological outcome also, but again toxicological data is not there, then we can use the approach of additivity, synergistivity, those kind of models we can combine. Similar pathway data we can combine. Okay, let's say the pesticide, organophosphate class of pesticides, they all really target the acetylcholinesterase enzyme. So I know that these all are going to behave in the same pathway, so I can add up those, and I can take the advantage of additivity model, and then I can combine the PK and the PD, and then I can do the risk assessment.
And I think time also is very important, the exposure time. Like you're talking about reproductive tox, so we are talking somewhere from 6 months to 2 years is what we do reproductive toxicity. So when we are looking for those effects, because it's not always instantaneous toxicity, many times you see accumulation and then effect comes much later. Yeah. So in such scenario, how accurate it could be? I could see that slide where you mentioned like zebrafish and all. The life cycle itself is short, so that's generally used for screening. But you cannot really predict something very accurately about the duration if it's a longer duration. But when you add more and more endpoints, I think it helps. But still, it's a challenge for a long-term prediction for a long-term toxicity effects.
Because in fact, the advantage is that if suppose I am validating the data for more and more number of chemicals. So let's say I am doing for the Azure class of pesticide. So at least I know that for Azure class of pesticide, these endpoints were pretty sensitive. So then if I later on I have the other class of chemicals, so then I can use the read across approach and then I can predict the toxicity. So this has to be validated with more and more number of data. And even it is quite possible that these in vitro test system could be oversensitive in terms of the predictability of the toxicological outcome. But that should be fine. It should not be false negative.
Yeah, wonderful presentation. I mean, nothing new in this, in the sense, in 1990s, 80s, if you go back and look at Inhalation Toxicology Research Center, they have done numerous studies to do the PBPK models for compounds which are inhaled, like benzene, bromobenzene, toluene, and many other compounds. We actually did a lot of data generation for PBPK models, and the amount of in vitro data I need to generate, that cannot be generated in pharmaceutical industries today. I mean, because it takes about 2 years for me to generate. Because I even needed a KM Vmax values for the cytochrome P450 metabolism, because without which I cannot do it. The other problem is that yesterday he talked about reactive metabolites and bioactivation. These you cannot monitor in the biological systems. You cannot get toxicokinetic data that produced in the liver or kidney or some other organ due to the metabolism. So that's another black box we had in building the models. So the question is that I wanted to apply PBPK models in pharmaceutical industry, but when I propose these are the amount of data I need to generate, I won't get to funding from the pharma company that my bosses will say, no, I can't do it. Same here, you are stuck only with the government funding here. I mean, I can help you a lot of these things in generating in my 3D models, the data that you need in vitro, maybe the rat model and in vitro human model as well together to get the actual concentrations in the liver. You know, you don't need the blood concentrations. I want the actual concentrations in the liver. Those are the things that are still missing in these models for the accurate predictions. Okay, that's my thought process.
In fact, people are moving to the organochip model system, and this is the reason actually so that
I
we
can
have the
generate
complete system.
This is the way I can generate the actual tissue concentration data for humans, which is not existent. I mean, even in clinical trials, I cannot get that data because I cannot open up the human like I open up the rat, right?
Yes.
Just requesting opinions on two matters. When we talk about PBPK modeling as applied to what is called as PBTK modeling, when we do PBPK modeling, one of the assumptions that we make is that all the organ functions are normal as you give the drug.
Yes, sir.
And those values are input, and the model uses those values to do all the calculations.
Correct.
But if I'm going to do that for a toxin, where the expectation is that organ function may be compromised, then how does the model adjust for the compromised organ function when you try to do modeling? That's one question.
Okay.
The second question is, we do microdosing.
Yes.
Can we do microdosing for a lot of toxins to generate that valuable kinetic data without having to worry about observing any effects, and then build that database which you are all looking for? Has anybody tried to do that?
Yes, sir,
Microdosing of toxins.
So in fact, sir, in that I would say the bisphenol S data which I have shown for the human kinetics data. So that data was existing for that bisphenol S. So it is quite possible that we can generate some data from this kinetics angle once we have that understanding of the ADI value of a particular chemical or TDI value, because at least if I am exposing that person below that level, then at least I can get easily permission for the conducting the clinical kinetics. But the molecule numbers are so much that it is impossible to really take up the molecule for the clinical trial, because the class, if I am talking about the bisphenol, there are more than 20 different kinds of bisphenol chemicals, more than, even in our country, more than 300 different pesticides are being registered. So, I mean, the class is very big class of chemicals, so it is very difficult to really generate the human data. So, that is why we have to rely on the alternative approaches and these modeling approaches. And as you said, sir, the toxins which are toxic itself and can be harmful, and then how these models will work. I would say that whatever risk assessment being done at present is generally the people are predicting all the outcomes for the healthy people only. Currently, in this particular area, I would say the disease modeling kind of, particularly for the environmental chemicals, is not being done. That is completely, that area is lacking. Especially for the children, it is being done, child it is done, that intake assessment for the elderly population is being done. But the modeling aspect in the disease conditions for the environmental chemicals is not being done.
I would just add up here that actually, sir, on a daily basis, microdosing is already happening. So we are already getting exposed to all the pesticides, so that microdosing is already happening.
No, I totally understand.
Yeah.
The only issue is, do we systematically use that knowledge that we are exposed many times to microdoses to actually get at the values by using suitably labeled toxins and using your classic AMS to generate that data? Because that will be very, very useful. That's
Krishna, your point is well taken. I mean, pharmaceutical companies actually gave up microdosing, but for a different reason. At microdoses, the metabolism is non-existent. But actually at therapeutic doses, huge metabolism. That's because of the KMV max value. Especially if you have a drug below KM concentrations, cytochrome P50 won't touch it. Whereas at high concentrations, cytochrome P50 will take over and metabolize and chew up the compound. So we had those kind of problems when we went to therapeutic doses. Here in this case, the problem is not just getting the single dose, right? You have to have a dose that is chronic. I mean, if I say a benzene exposed over 6 months at tiny minute concentrations cause leukemia, that TK-TD data is hard to generate, right? I mean, leukemia takes 6 months later, but a single dose cannot tell you what happens at 6 months later. Yeah. PK. Okay.
No, that's a good suggestion. I think we can start with just a normal PK data to start with, yeah. And don't have to even reach to toxicokinetics thing, yeah. All right, great. So any other questions from, I think there were a few hands and then later on they changed their mind. The guy, you had question earlier? Yeah, no worries, you can ask now. Okay.
Sir, you mentioned training and testing of model machine learning model during this development flowchart. So how could we test that model like it is giving actual predictions or not?
It's what I talked is a workflow of the machine learning, how the models are developed. So that models are developed and then they are being tested. That is what I was explaining.
Sir, we use available data for the development. Okay. So how could we test that model is particularly giving accurate result or like predictable result for our choice or not?
So it's all like it's a software ultimately. So you have to generate certain queries. Once you put your data, and you have to generate certain queries that what will happen if these are the situations. Then based on the data analysis, it will give certain predictions. So it's nothing is we are not going to do anything. There is already data available. You put your data and generate queries that will give you the predictions.
So if there is no questions, then we will go.
I just want to add on to that. So the issue of validation is really critical modeling. And two things to bring up. One is that any model you get, don't trust it, test it. So that's one thing I was kind of touching on yesterday is that get some examples that would test, put in a test compound that has published data and see if a prediction matches. usually model development, they'll break up their data sets into what's going to be training and testing data sets. And so they'll look at performance. Okay, so if I randomly take out these testing data sets, can I predict what the model trained on this data? And what they'll do is do iterations where they'll take out different sets of testing data and training data and see if they keep getting the same predicted outcomes. But the important thing to bring up too is this whole model, the whole development and testing is based on one data set. So that is actually defines what would be the applicability domain. So the only usefulness of that model in terms of testing is on the data it has. That doesn't mean your data is part of it and is good at predicting it. So that's why you always want to test it, because the idea of a model is that if you put an unknown in there, you're going to get data you trust. But you don't know if the model's even seen anything like it, which means you're hoping the model can extrapolate with accuracy with this unknown compound. And to be honest, you don't know. I mean, the only way to do that is to do an experiment, then you know for sure, which defeats the whole purpose of modeling. So that is an important issue that goes into that I kind of alluded to before, is confidence in modeling. Do you really believe what it generates? And so that's where, if using any kind of modeling, always try it out to make sure you trust it. Find some controls out there and stick some unknowns in it and see if it matches what's published data to get some kind of confidence in it. Knowing that the fact that you're never going to be 100% pure, but sure about the data. But also keep in mind that all the risk assessments and safety assessments, they're all best guesses. Nothing's 100%. You're never going to have a good model to give you data, and especially when you consider the diversity in humans, because most of this stuff is based on an average person, which doesn't exist. So that's where confidence is something that's always going to be challenged at AI. But again, that's where I say traditional methods aren't really that good either. But if y'all trying the models out, because we've seen some good examples in some of the talks, test them out and see if you actually replicate, something that's been published before. Does that answer your question? Okay.
So just a question here that the ultimate aim is to really predict, right? So if I understand initially you want to test just to make sure that it is predicting correct, but eventually we really want this thing to apply to a huge set of molecules or even environmental toxicants. So that's what we want, that this prediction has to be 100%, or at least some confidence level it should give that without even testing, we can trust that.
Well, confidence, one thing you can do it statistically, and one you can do it from a personal perspective. And so I'm saying those are different things. Experimentally, we can have certain confidence. Even in p-values you never get a p-value, you're completely sure. You're very sure, but maybe you won't be 100%. But I always want to distinguish that from people believing in it, because you may have some stats that say it looks really good, people don't believe it. But the thing is also that is actually a growing area in the field now with AI to build confidence models, is how do you actually define the applicability domain? So then you can actually score that relative confidence, because you have this unknown compound. So how much does it look like what's in the data set? And using that to kind of scale the confidence in it, because the model's just going to give you value. So that is a bigger discussion, and people are developing models to define that applicability domain, and that's to help build confidence to address that kind of issue.
So, in my opinion, prediction should never be the outcome you should look for, because you'll never get that data, because 90% of the molecules that we do preclinical in discovery will never enter the clinical trial. So what we use it for screening purposes at the earliest stage, and see they don't have that liabilities on the molecules, so you choose those molecules only and test them out. Okay, my model predicted in a biological system to be accurate, but when you go to the clinical trial you may find something new. The question here is that it's not prediction. For me, for drug discovery, how do you design your clinical trial? Do I have enough data to be able to get an optimal clinical trial? For example, pharmacokinetics, right? I've done mouse, rat, dog, and monkey pharmacokinetic studies, did an allometric scaling with the same factors, and had the 1-month toxicology data with rat and dog, and then you try to extrapolate with the factors that we put in with FDA approved. we still were only 30% predictive of the human pharmacokinetics. So the question comes is, why are we so poor in predicting that? So don't use the prediction. Try to enhance your model better. See what are the things that you still don't have in your model. You need to put them inside so that it will improve, but it's not going to be 100% predictive. Okay? My goal is to be able to design an optimal clinical trial, not predict whether it's going to cause toxicity or not going to have efficacy.
Yeah, because this takes us to the withdrawal things, right? Even with everything in place, how many withdrawals of the drugs we are seeing, and then your toxicity and lack of efficacy, both the things are still the major reason for not withdrawal, for failure of the drug. After launching also, after 1 year or 2 years, how many drugs are still being withdrawn? For this?
Each case is different. Each case is different. You cannot compare one case to another case. I mean, when you go back and look at all the withdrawn drugs, well, one is for heart valve problems, another one is for bone marrow toxicity, another one hepatotoxicity, another one for cardiotoxicity. So you have different mechanisms. You have to choose a model that can predict everything. This is where I'm saying human on a chip would do it. Okay.
Yep, absolutely. So, thank you, Shailendra, for delivering the. Yes, anybody? Yes, please. Okay.
Yeah. No, I'll just add some comment on that. I think we are talking again the accuracy of the modeling and prediction, right? So whenever we are trying to translate some data from the animal to human, always there is a rate of inaccuracy is there. But nowadays, given the fact that we can sequence the whole genome in the patients on the clinical trials, and when we see the toxicity, even within the human beings, we can see our genetic makeup is completely different. We differently react to the different drugs. So are we including that data into the prediction? So whether the genomic data and the toxicity, what we see within the human population, are we integrating that into the AI models? And if you do so, I think that will be more accurate in terms of prediction if you tie these genetic factors and metabolism within the human being and their toxicity outcome in the trial settings, and that could be a more accurate way of predicting the drug toxicity. Are we? Is it in practice? Is it in the AI models now? I just want to know.
I would say that definitely certain already in this particular SimShift software itself for different disease conditions, they have the different enzyme expression profile different. So they have already did the expression studies for, let's say, the liver cirrhosis. You can find that expression pattern, how it changes to the liver cirrhosis conditions. They have that data and they have built it into the model. So we have to choose that instead of healthy population, we have to choose that particular disease population, and then we can do. So there is a data is being generated, but I would say still a lot data needs to be generated. Some of the data I can say is that UGTs, isoforms which are involved in the metabolism, even the CYP ontogeny data is already existing. People for the infants or children's predictions, people are using that data. The ontogeny data is also being integrated in this model system. But definitely from the disease angle, as you said, let's say from the cancer angle, we can see that lot of heterogeneity you will find in the data itself. And that is why I always say that that only the 2.5-fold or 3.16-fold difference which is being taken as a default to understand the human variability in the kinetics is very less. And we have to really have the real data. And this all the chemicals, whatever we have, this is all the data, and whatever ADI, whatever in the present scenario is based on those default factors. So still a lot of data has to be generated, and we have to refine those factors to really predict or to understand the actual risk in the human being.
Yeah, I mean, I would say here, I mean, there is data. Is it in the public domain? No. You go to pharmaceutical companies, they have generated toxicogenomics data from 500 compounds, and they got no idea what that meant, and that was shoved under the shelf, saying that we don't need to do toxicogenomics to predict toxicity in animals. So that data exists. A lot of people in public domain doesn't know, and they still keep doing it. Oh, I'll use the clinical genomics, I'll do the toxicogenomics. But the data is there, and you go to pharma company and ask them, I'm doing toxicogenomics. Okay, good luck. That's what they'll say. They'll not even entertain you to discuss with them. So we have to know whether the data exists or not. There is data that exists, and people don't want to go after them. Genomics is a mess right now. You don't want to even touch it because 250,000 people having 300 million variants is going to be too complex data that you want to touch genomics.
Thank you, sir.
Thank you, Dr. Sailendra, for nice talk and very good interactions. May I now request Dr. Deepak Barok to present the memento to our speaker, Dr. Sailendra Pratap Singh, for delivering talk on the physiological based toxicokinetic modeling in the risk assessment of the chemical exposure. Thank you very much.
So I think we had a lot of interactions and very interesting talks. So thank you to both the speakers. And before I invite the moderator for the next session, we have our two speakers also out here. So let me request maybe Mani, if you can just come and offer, let's welcome our speakers who have come. So maybe Dr. Jayesh can come, and would request Mani to offer them a bouquet. Or you can Mani be there just for a minute. I would also invite Dr. Senthil Natation. He is our speaker for the next session, and would request Mani to welcome him with a bouquet. And thank you, Mani. Maybe now request Dr. Bausa sir to come and welcome our speaker from the last session, Dr. Poonam Giri from Zydus. Thank you. So I think it's been a long session, so I would just say that let's take a break for just 5 minutes. And then let's reconvene here and immediately start our next session. We are running slightly late, so just try to be back within 5 minutes, okay? Thank you.
We'll check it, sir. Okay, it is the one you want. Fine, sir. This one only, sir. Okay. Okay. I have keep it loaded, so you can. Yeah, sir. One second. Yes, I'll load. Yes, sir, give it to me, sir. So this is the laser. You can use it for laser, and then again you can go forward and backward. Okay, sir. So you can operate from anywhere. If you want the yeah, okay. Sir, pen drive.
Okay, thank you.
Thank you, sir. कनेक्टर का भी क्या करना है अपने पास कनेक्टर हाँ डोंट वरी It is not detecting, sir. One second. आ गया sir. So there are two PPTs. No, sir, only one PPT. Yes, sir. Okay, sir. My copy. Sir, can I know your good name, sir? Okay, sir. So you are from Bombay College, right? Yes. Yes, sir. Thank you so much. हाँ, पाइए.
identified the problem. So, all right, guys, I think let's take our seats and let's get started with our second session. Again, it's like novel therapies and so a few talks on lifestyle disease management and all. So, again, interesting talks are lined up. Let me invite the moderator, Dr. Jignasha, to continue the proceedings. Over to you, Dr. Ji.
Okay, welcome back. So I think the tea has again rejuvenated you, and now we are starting our next session. So the first speaker for next session is Dr. Jayesh Sheth. Dr. Jayesh Sheth is a founding member and director at Foundation for Research in Genetics and Endocrinology and the Institute of Human Genetics in Ahmedabad. He serves as the Vice President of Indian Society of Human Genetics and is the National Task Force member for lysosomal storage disorders from ICMR. He is also a founding member of the Indian Society of Fetal Medicine and the Indian Society of Inborn Error of Metabolism, and a board member of both the Indian Organization for Rare Disease and Jivraj Mehta Hospital, Ahmedabad. He holds various academic roles, including affiliation with our university, that is Nirma University, Maharaja Sayajirao University, Vadodara. Mainly his research focuses are on lysosomal storage disorders, diabetes, rare diseases. With numerous research grants he has received from CSIR, DBT, ICMR, and he has got more than 138 published papers to his credit. He is also recognized with UICC and WHO fellowships, the Future India Award by CNBC 18, and 1000 Petals. He also has authored a book, Genetics in Clinical Practice, Symptoms, Diagnosis and Therapy. Dr. Sheth has trained over 450 students and holds a patent on eye cell signaling screening and the SM-MIP assay for 23 common lysosomal storage disease. So I'm really honored to welcome you, sir, for this ACS TOXI India Chapter 2024 event, and I really thank you for accepting our invitation and gracing this occasion and sparing your valuable time. Thank you, sir. The stage is yours, sir. Thank you.
Give a talk in the toxicology. And I said, I'm not working in the area of toxicology. I have a couple of things which I would like to share with the pharmacologist people, what to keep, because I saw that a lot of the exchange of ideas were going on where for the genomics data. The genomics going to be messed. But yes, sometimes messed, but sometimes it's. I would like to give a simple example. In 1999, in Toxicology, Kansas, James Gill published first paper. Of the paper. And the effect is the dark silver, because the particularly MPS for C777 C2C polymorphism, that leads to the meiotic error is a cause for the down silver. And same year then, okay, then I just begin the study. And then we found, we have the case and control, we have the polymorphism equally same. That is not the problem area. Story in Western country, this is from Kansas. And we did a third study also, and then we had to facilitate one part. So she gave me the FedEx address, and I sent all the samples here to Kansas. We did the third, we published the first paper in 2003. Hey, so in India, how does this polymorphism exist in case and control? So that is not a cause for the meiotic error in India. In India, is the folic acid and visual deficiency is likely to be the cause. So this is just a story I have just given. So how I enter in the area of how this lifetime and element of this factor is a problem. I think it's very interesting because we are entering the plastic. That is the end of practice. So I think I will see. this way. Okay. My talk is going to the key point environment and how because you get how changing the life range is obesity are we finished prototype to that right we are not eliminating or we are not cured the disease. We are just taking the symptoms for that. Why? We have not cured the root cause of it. Reactive oxygen species and oxygen stress because we produce oxygen stress all the time. When you talk, when you get angry, when you get stressed. Genoprotective factors, some of the drugs which we did with the study when Dr. Musaika was there in ACS and the part of mimicking project with Dr. Ashok Vaidya, who is the father of the reverse pharmacology. I was a part of that. Vitamin D deficiency, vitamin B12 deficiency. Vitamin D, I think we were the first one, we were the first one to say in 2015 that vitamin D, 90% Indian people have vitamin D deficiency. Nobody was able to believe in government also. So I communicate to that. So that in urban area, you don't have that. They have pure depressive something there. And we know the reason. B12, again, microplastics. Very interesting, I have said that. So endocrine disrupting chemicals, machine learning and AI. And gene expression changes with meditation and prayer. That is solution. You all know, I think you all know very well the region of the DNA world that has whatever the drug is when we do, whatever drug we make, ultimate effect, how it affects on our genome. That's, I think, going to be seen in our talk also. I think it's needless to say that the legs of the DNA, one cell contains about 2 meters long of the DNA. How the nature has packed it. Only the nature has done, we don't know. So we need to understand this, how nature has done, how we have to protect it, how can that be by the lifestyles, by our food, by our behavior, by our knowledge. So this I am going to talk several points in my talk. So first thing now, environmental. The environment can mean things like climate, location, food we eat, the drugs we take, toxins that are around us, really any non-genetic contributions, or the gene-environmental interactions that describe how the genotype and the environment conditions surrounding an individual can influence the phenotype. When two different genotypes respond to environmental variations in different ways, some parties are low risk, just give the example for the same line. So some parties are low risk for developing a disease to an environmental insult, while others are much more vulnerable. So this is just a So what are the epigenetic and epigenomic, the environment epigenomic interactions, environmental lifestyle factors that mainly involve with the chemicals, physical, biological and psychological. And this all affects on the epigenetic modifications. So when we talk about epigenetic modification, I think recent Nobel Prize has gone to the microRNA discovery. So I will just touch on that part, how that affects on that. The methylation in the DNA, histone modifications and non-coding, because the microRNA, mRNA, they are the non-coding regions, microRNA, the non-coding RNA, and that affects on the gene functions. So first, the unhealthy lifestyles. Bad habits, defects. In 2022, 1 in 8 people in the world were living with obesity. Worldwide net obesity has more than doubled since 1990, and adolescent obesity has quadrupled. In 2022, 2.5 million adults were overweight. Of these, 890 million were living with obesity. So, what are the reasons? If you look at sweets, junk food, unhealthy drinks, rest at home, all lifestyles play a major role in this. So, changing lifestyle cause for human health? Yes, first I will say that, but it's the most common touching I think in India, dyslipidemia and obesity, because like we said, central obesity is there. Dyslipidemia and obesity are the most common complex metabolic disorders, taking highest toll of health resources globally by its increasing incidence. This consequently leads to type 2 diabetes, mellitus, and cardiovascular. So this is one of the factors. If you look at this, when you look at the diabetes pathology, how the environmental factors, the lifestyle is linked. Why are we not able to cure the disease? We are only able to treat the symptoms. The genetic predisposition and environmental obesity, environmental factors. So the genetic predisposition, like genetic defects, that leads to the beta cell dysfunction, which leads to the impaired insulin secretion, leading to hyperglycemia, beta cell exhaustion, and type 2 diabetes. While we talk about environmental factors, mostly with the lifestyle, there's obesity, which leads to the insulin, chronic insulin resistance, due to the poor glucose utilization, hyperglycemia, and leads to hyperglycemia, and enteral beta cell exhaustion at some point, and type 2 diabetes. If we look at this study, it published in 2015, association of dyslipidemia and obesity with glycated hemoglobin and type 2 diabetes and non-diabetic subjects. If you look at this study, it clearly demonstrates here the waist and the BMI. If you look at the HbA1c, with the increasing of the waist circumference and increasing of the BMI, there was a linear correlation of the glyco-HB. So this study demonstrates the high prevalence of dyslipidemia and obesity in all subjects, irrespective of the disease status in the Western Indian population, because this was studied in Western Indian population. Dyslipidemic obese subjects had significant linear association with HbA1c type 2 diabetes. So that means the obesity plays a major role, and that is one of the causes of dyslipidemia. So are we pleased for this? Say we why? Possibly some genetic factors are there. It's not confirmed. But type 2 diabetes mellitus is driven by genetic and environmental factors. Yes, it's not only, it's environmental factors also there. So sequence variant of candidate genes are known to be exposed. So what we did is, Asian Indian phenotype is a cluster of abnormalities that describe earlier lays possible genetic proneness of India. Why India has so common diabetes? So we look at the PPR gamma gene, particularly the specific SMP, is a missense variant that is associated with improved insulin sensitivity. In nature has given to all of us. In nature some will always protect us. And that reduces the type 2 diabetes risk and adipogenesis. Similarly, the ADR beta 3 gene with a specific SMP that produces variant receptor protein with altered affinity, which is associated with the development of dyslipidemia, obesity, insulin. So this is also, you look at this. One way the nature has given us this, another way, the moment you have this polymorphism of this lips, that leads to the dyslipidemia, obesity, and insulin resistance. So, if you do not balance over here, you are going to develop type 2 diabetes. That is the root cause of the type 2 diabetes. Is very common in India. So, coexistence of reference allele PPR gamma gene and variant allele of ADR beta 3, because in India we have reference of PPR gamma, which gives us the protection from insulin resistance. But at the same time, nature has given us ADR beta 3 gene with a variant allele, which is more sensitive. The moment you become obese, the moment you change the lifestyle, or become dyslipidemia, that you are slowly, the insulin sensitivity protection that goes again, build up with the insulin resistance. And at some stage, you have the beta cell exhaustion and type 2 diabetes, which is a very chronic and progressive path. So it may be starting with your 20 years of age, and then you produce the disease by around 40 years of age. So one for the increased insulin resistance, thereby increasing susceptibility to the development of type 2 diabetes. This can be one of the contributors. We said this is not the cause, this is just one of the, because this is what we are studying. So this can be one of the contributors for type 2 diabetes that increases but need larger, because this is only ethnic, is only the Gujarati or Maharashtra, because in Mumbai and in Ahmedabad, this study was done. So it is because we have a lot of ethnicity variation there. So this is the that is different. So we need to do the multi-ethnic population study. So this study, what is done? Because in diabetes, we know that hyperglycemia. So then we have the oxidative stress. Hyperglycemic increase, oxidative stress is there. So reactive oxygen species and oxidative stress, the increased generation of the reactive oxygen species, ROS, due to hyperglycemia, that cause oxidative stress, we all know very well. This results in endothelial damage that leads to the vascular complications. That also I think we know very well. The ROS induced advanced glycation end products that damage the cellular macromolecules, including lipids, proteins, and nucleic acids. So that is the root cause why the diabetic patients are at increased risk for several diseases. Maybe we can say that the nephropathy, ophthalmopathy, cardiomyopathy, neuropathy, with the pregnant mother, with the abdominal children, this may be one of the reasons for that. So oxidative stress leading to DNA damage that predispose to age-related disease, including diabetes, atherosclerosis, osteoporosis, and cancer. If we look at our with RMS overproduction is there. Particularly, if you look from here, your lifestyle intervention, that affects particularly with hyperglycemia, what it does, because it increased reactive oxygen species that damage your DNA. You see, because I will demonstrate how we can study the DNA damage also. The damage the DNA, and as a result, what it does, makes the protein modifications and make the protein lipid penetration, which this is specifically for diabetes. It leads to the insulin resistance, and then the pancreatic beta cell apoptosis. So, what we require, antioxidant therapy, pharmacological interventions, lifestyle interventions, that is things for this. Free radical oxidative stress that affects a several part of this. Why? Because it affects everybody, not only with diabetes. It affects the brain, on heart, kidney, skin, it's multi-organ, joints, immune system, blood vessels, lung, eyes. So almost so particularly when we have the oxidative stress, it's not only with hyperglycemia. Even we have stress related to work-related stress, or we are in rat race. Nowadays, I think we are everybody in a rat race. Competitions with some colleagues. I want to do this fast, or I want to do this right now, or your temperament is so angry. So all the time, we are producing a lot of oxidative stress in the body and oxygen free radicals in the body. And that slowly, see, when I think I was looking at the discussion, all these chemicals, they slowly build up. It's not that when you have DNA damage, nature always protects us. Nature always have a mechanism to make the repairing mechanism of the DNA damage part. But then there is exhaust. At some stage, we need to get exhausted, and then no further repairing of this damaged DNA part. It goes in circulation, and that is why many diseases we get is at 40 years or 45 years, because we start at a period of 10 years or 15 or 20 years, and then slowly the stage we reach where there is no further repairing of the DNA damage which occurs, and that is results for the affecting on any part of the body. So what we did to study in diabetes, increased frequency of sister chromatin exchange. We know that the DNA constantly getting the replicates. With type 2 diabetes, this part what was done. That SE, sister chromatin exchange, involves the barricades of both DNA strands, followed by an exchange of 4 DNA duplets. It occurs normally in cells during mitosis process. Whenever genotoxic agents damage the cellular DNA, the rate of sister chromatin exchange increases. Study has further shown that diabetic patients harboring the 16189 T2C variant in mitochondrial DNA that impair the ability of a cell to respond properly to oxidative stress and oxidative damage. So this suggests that diabetic complications may be related to oxidative stress. Yeah, that is the DNA damage. Our therapy doesn't address this. Whatever therapy is done, we do not address. We just look at hyperglycemic index. We don't look at this part particularly. And this is study what we have done. We have shown that people say, I think back in 2006 perhaps, that the increased sister chromatin exchange, if you look at this is particularly a type 2 diabetes, and these are normal cells. These arrows are all the chromatin exchanges. So when the chromatin exchange is going to break in the chromosome. Particularly, we know that almost roughly around we have 21,000 genes. There were 700 to 1,000 genes in each chromosome. They are spread around. So wherever the damage occurs, like here the breakage is there. So specifically, that disrupts the gene, particular gene involved in those areas, and that is why the diabetic patients, some people may have retinopathy, some may have nephropathy. Depending on which part of the gene getting damaged in the SC exchange. If you look at the healthy control, they are very little. So compared to the diabetic patients, the SC exchange, the SC ablation is much less. So that is why there are less complications. We look at this study also. So this was a part of the CS way back in 2005. I think when Dr. Masilkar was there, and we started the new Limitly project with a technology network business development. And it's a very wonderful project with 40 centers across the country were involved. And we wanted to test all our herbal drugs through the reverse pharmacology. And I was a part of that again at VS Hospital. So we did a study. We found that
Type 2 diabetic cases, if you look at this, we did the COMET assay, we did the SE also. If you look at the COMET assay, the genoprotective effect of one of the drugs which we were just testing on that time, if you look at this normal cell with 50%, 8-hydroxydietoonoside with the DNA damage enzyme is 13 nanogram, SEs per metaphase. So this is this, I think, in the pre-treatment, before giving the herbal drugs. Look at the post-treatment. Look here, this normal cells population has increased, but no damage is still there. But now, this is after the treatment of giving for this 1 month time, 1 month only, with 250 milligram dose here of the DMSNO4 compound. I know that this compound was used was a anicostomal neutrally was used, and they did the toxicity study, they did the dosage study, interaction study. It had no interactions with any kind of insulin or any sulfonylurea. And look at the SE also. The SE results also they improve. 8-OADG, the DNA damage enzyme has decreased also. So this is how. These are the important factors I think when we do the drug investigations also. How that our the DNA, the damage protection takes place, which is important. So it is not just the suggestions, I don't know. But when we are making the drug development, we only look at the specific symptoms cure. But we do not go to the root cause, and that is what I have been saying for diabetes. I must say that for diabetes, we are not going to the root. Why I developed that? I have seen many cases, even like hypothyroidism, with the stress induced, and then suddenly they have developed autoimmunity, and the autoimmune disorder, and they develop this hypothyroidism. Same for type 2 diabetes.
How about metformin? Did you do the study with metformin?
This study we have not. This study, but we have done the metformin with interactions. We did for the interactions. We had no interaction. We only we are not this study with the metformin. Again, lifestyle. How the lifestyle effects? It's not only the drug. If you look at the lifestyle here, the polymorphism, particularly TCF7L1 gene, with the CC genotype and the TTT genotype, CT similar. The TT variant, particularly here, that was more associated with increased risk of diabetes. But you look here, this is over here, and if you look at the TT, with the which lifestyle modification with diet, exercise, this variant no longer associated with increased risk of diabetes. Here it is, there is increased risk of diabetes. Here, you look at this, it almost become at par. So this is one of the modifications. So it's not that you have a genotype, you are going to have a disease. It is just like I would say, always say, it's like a horoscope. It is a prediction. You cannot say you are going to work all the time. But gene has a lot of modifiers also. Modified genes are there. Maybe the expression effect will be there. So your lifestyle modifications, behavior change can overwhelm the genetic risk. Are you getting enough, again, vitamin D? Because why? Are we getting enough vitamin D? Sorry. Studies have found that many people in northern latitude are deficient vitamin D. The deficiency is even more pronounced for people in northern latitude with darker skin pigment. We don't know better. A study found using the supplement to correct very low vitamin D levels can lead to 70% less herpes than bacterial infections. And the darker skin that protects the sunburn and that produces the vitamin D slowly. This is what the nature has given to us, I think, because nature wants to protect. But if you look here, what we did the study in 912 subjects because we wanted to look. So there was not many people think, vitamin D deficiency is there. You just give vitamin D and diabetes will be cured because that is the cause. No, it is not the cause. It is one of the contributory factors. Because we did a study, 429 type 2 diabetes cases and 483 non-diabetic controls from Western India. The enrolled study subjects were investigated for biochemical parameters like the blood sugar, glycation, HOMA, IR, 25-hydroxyvitamin D level. Vitamin D deficiency was seen in 91% and 93% of the control and 93% type 2 diabetes. So that means if you do the regression, it is no difference. So it is, I think, accidental finding. If you look at your cancer patient and find vitamin D deficiency, doesn't mean the cancer has occurred because of this. You can say it is one of the general factor. One of the contributory factor is there. So there was no association of vitamin D deficiency on HbA1c or HOMA-IR into type 2 diabetes and in control. Means it is existing. We all have a vitamin D deficiency, very common. So we need to talk because that may be the root cause of many disease process. And this we published, I think, in late 2015 or so. So how vitamin D affects our health? Effect on human health and disease. If you look at vitamin D deficiency, it associated with disease that is causes, I think, not proper visible. But it mainly affects on our immune systems, affects on our the neural behavior. So many neurological disorders also are there. These are most common. So particularly vitamin D deficiency is a root cause for many, like for acid oxidative stress produced by the hyperglycemia, the root cause for the diabetic related complication. Same way, for vitamin D deficiency is a root cause for many of the human health and disease. It not only cause one disease, like immunocompromised. We have seen in COVID time, everybody wanted to supplement with the vitamin D because it increases your boost up your immune system. Similarly now, this vitamin B12 also, right? The vitamin B12 are followed because this we have been turning since 2007 or 8. We have seen one case of neural tube defect, the mother term defect. And she has one child with a neural tube defect. Neural tube defect means there is opening of this spinal cord here, and the meningomyelin or the spinal cord is not properly covered. Neural cord formation, deficiency of the folate deficiency is a known that leads to the neural tube defects. So she came to us, and we know that folate deficiency is because that was published that it's studied in Ireland, in UK, and that's why in UK they have seen the supplement of the folate, and they see the decrease in the incidence of the neural tube defects. That is one condition which can cure the disease. But in India, it is not only that. So based on this, because we did only single case study we published in the obstetric gynec, and we investigated because she had second child also again with a neural tube defect. We did the vitamin B12. She was a vitamin B12 deficiency. So that I think that from that onward, this idea came to know. Within India, it is not only folate, we have a vitamin B deficiency also is there. For like 80% people have vitamin D deficiency, 40-50% of vitamin B12 deficiency. We do not know the reason why. And this has resulted in the multi-centric project by DBT for 4 centers across the country. Our center from Gujarat, then Nirma, Nidam Institute from Hyderabad, the FCRC, Fitla Medical Center in Chennai, and K Hospital, Pune. So Gujarat was a vegetarian population, rest the non-vegetarian population. We found the equal level of vitamin B12 deficiency. So that means the veg and non-veg is because it's not the non-veg doesn't contain vitamin B12, but the intake of the vitamin B non-veg, it may be taking once in a week time. So there's not enough vitamin B12 they get it. So that is one of the vitamin B12 deficiency was seen across in all the subjects. But what here, more so, what we found that particularly we wanted to look why should vitamin defect occurs. So this was the largest study of 500 women who gave a birth to a child with neural tube defect. We did the study of the parents. We did the nutraceuticals, we did the genotype, and we found that B12 deficiency equally exists. At the same time, what we found here is the MTHFR, the polymorphism, this is the regulating for the vitamin B12 and folate metabolism. So it is not so if we have this polymorphism, which is not protective, so that means like in India, I have said that we have this polymorphism is very common in our population, in case and control both. So we are not protected. And we have vitamin deficiency is also there. So then we have more incidence of the birth defects. But we found that the particular TCN2 gene, you have this polymorphism 776 from C to G, which is strongly predictive for the neural tube defect. So they wanted to know which patient will have, which mother will have the child with neural tube defect. Is only the B12 deficiency or some genotype is there? Yes, we say this genotype is there. It is strongly predicted that she is at a high risk having the child with neural tube defect, and she need to supplement with vitamin B12 and folic acid. But if you have this genotype, particularly this polymorphism, then you are not protected. And if you have B12 deficiency, that is why in Gujarat, particularly in the northern side, they have a very high incidence of neural tube defect. But they never come to the attention to the health people because majority they detect it by sonography, they get about it. So we never go to the government record, they say, we don't have NCTS. No, because they're getting about it. Plastic, this is very interesting now, because I think plastics is the missiles everywhere. We cannot escape, like drinking the water. So India ranks among the top nations for plastic pollution and plastic emission account for almost 1/6 of all plastic emissions worldwide. If you look here, the plastic disruptors. So this is, I think, a very growing concern for our country. Health effect of the microplastics. If you look at this, it affects on microplastics that affects on the oxidative stress, neurotoxicity, reproductive toxicity, carcinogenicity, metabolism. So these microplastics are found in the oceans, remote islands, polar regions, and are emerging as a major threat to ecosystem due to direct and indirect potential as environmental pollutants. And that's why in Finland one study has been done. They did the study, and 90% of the Finnish population, they have microplastics in the blood. And you know that the Finnish population, they have very high risk for the neurodegenerative disease. Particularly Batten disease is very high there it's because of fungal mutations. But it's one of the cause why there are a lot of space there for the microplastics. The microplastics are associated with chemical exposure also, that they are endocrine disruptors also. So what they do? They affect on the hypothalamus, that again, like we have this, if we have the associated chemicals like mercury, bisphenol in the microplastics, DDT, you have the lead, and all that effect on the several organs in the body, reproductive organs and thyroid and the kidney and the pituitary gland, and particularly on the male and female organs. So this is the major endocrine disruptors, and that is so this toxicity slowly gradually builds up. So that is why we all take the food which is plastic which is hot. We do not know, I think we have not measured it, but perhaps this is like slow poison going on with us. So if you know that this year the Nobel Prize has gone to scientists Victor and Gary, endocrine. Why? What they have shown in the study is that endocrine disruptors characteristics, microRNA. There are out of the 21,000, we have around 1600 microRNA. Out of 1600 microRNA, they are a non-coding region of the RNA. Almost 20 or 22 nucleotides there. And what they do? They are like I would say that they are the kingmaker, not king, they are kingmaker. Because this is the gene, here the microRNA, it like it regulates, switch on and switch off. We want to function because microRNA sometimes what they do, they produce a complementary sequence with the mRNA, and then that doesn't allow the mRNA function to make the protein, or it disrupt or it destabilize the mRNA, so it doesn't allow the mRNA to produce the protein. So perhaps that may be one of the reasons. Why it is because when you have these microplastics or when you have stress conditions there, particularly the microRNA, may be one of the reasons that they become either active or they become inactive. Both like in the chronic lymphocytic leukemia, they become totally inactive. So then particularly they have produced, particularly in CCL case, the microRNA, they do not function at all. So that is why the tumorigenesis process, the oncogene, they remain uncontrolled. They have no control. And that is the reason why they have proliferation in the chronic lymphocytic leukemia. This is one of example of the microRNA. I think we are still learning because the Nobel Prize has gone, but still this year's Nobel Prize has been given to the discovery of microRNA. Like autism cases, we know the autism, 50% cases we find the answer. We know the genetic link is there. But when we do the long-range sequencing, look at this on inversion, we could, because we have done the study with long-range sequencing also with Oxford Nanopore, we could not find, I think, in one single case, one long-range sequencing cost one experiment. So it is just a research case. We could not find answer. But I say that possibility the microRNA is the answer may be lying here. So next step to study in those cases will be microRNA. We do not know because this is evolving in field now. So endocrine disruptors that role in human health. We know that they have the obesity, in the lung disease, the reproductive disorders, in diabetes, in cancers. So particularly the disruptors, I think, almost has a multiple role, and because it's like a slow poison we have been looking at in the body. Can you play this? I would like to play this very interesting with how the microplastics. इसको play करो. Little plastics big problems. So the 5-year-old point of view, look at this, how he speaks. And because one day the child, he brings the fish from in Finland, very, very you stay. Everybody, this kilometer area, you have a pond and you have a forest. He got the fish in the water.
And the thing what you have to do today is to stop all the plastic and clean up all of it. And also plastic is waste for the world. And they dig the ground and take this in oil. And then this one, you kind of black type of oil. And with the black oil, they make this kind of plastic. And the plastic is actually waste for the world. People just take plastic containers. And plastic is also waste. It's a rubbish. And we should not keep it as rubbish. All the time, if a person gives you plastic in an other box, just throw it away. Those plastic containers, you should not eat in plastic containers. It's unhealthy.
Can you tell me why?
Because, you see, when we eat in plastic containers, then these little particles of plastic goes inside your body, what you swallow. And those parts called microplastics go into your stomach, and then it causes cancer and a person can die in it.
Because he just got the fish. He said, why you got the fish? The microplastics is going to kill the fish. So he brought the fish at home. One day he got the frog at home. He made this aquarium. He made a terrarium. He said, I want to protect them. Because even though he's a small child, but this is the impact of the microplastics. I think we all will have to take care for it for the future.
And the thing what you have...
Yeah. So now this year the two important Nobel Prize. One Nobel Prize went to the microRNA. The second Nobel Prize went to machine learning and artificial intelligence in toxicology science. It has the artificial intelligence is rapidly developing. Subdisciplinary, I think the end of discussion has been gone in this meeting also. So subdiscipline of computer science with the goal of designing and creating a machine for computation models that can perform a variety of cognitive tasks at a level comparable. I think in genomics, we have been using the artificial intelligence because we cannot do genomics otherwise. You have to read the millions of letters. The artificial intelligence is to be because we feed the human data, we read the letters and see that which letters fit with which genotype. That is how we identify the disease. So artificial intelligence, machine learning in genomic area has been, I think, is rapidly using after 2015. After the discovery of the next generation sequencing, this is a very common. So we have been using this enough, but in the drug discovery, it's really good, very, very good, because you don't have to go to the human volunteer studies. You can do the in vitro study, and now with the technology available, you are able to diagnose all rare disease. So there are 7,000 rare disease. India has the highest population, 7 out of 300 million people is living with rare disease globally. India has 17 million people with rare disease. 80% have a genetic component. 5% have a disease treatment available. So 95% treatment is still there. But since it's rare, so the patient may be rare. But the era of the machine learning, the artificial intelligence, I think we will be able to make the precision, like precision medicines. So the mutation-based or genomic-based medicines can be developed. And some people do that. In US, I know the one case of Batten disease and CL2. With a single mutation, he developed the therapy and he treated the child. So it's going on. Yeah, sorry. So to create in silico models to predict toxicity for large number of chemicals with similar accuracy compared with in vivo animal. So this is the very important area of artificial intelligence and machine learning. It definitely go in pharmacology, in new drug discovery, it is really going to make the job very easy, I'm sure for that. And if you look at the timeline also, with the, particularly the application of machine learning, artificial intelligence,
physiologically based pharmacokinetic and quantitative structure-activity relationship modeling approach in the field of pharmacology and toxicology. Look here where we are in the different phase. This is physiological base, this is a quantitative structure base, and this is the machine learning. The drug development is much faster here in this era because your time cuts out with the experiments, with human volunteers, with the recruitment, lot of ethical issues are there. So this is what I think we see that the pharmacology will see the major revolution in the development of the new drugs. I know that if you test the 100 drugs, 90% of the drug will get failed. Only 10% will go. It's a lot of hard work. But still, India is a hub for the herbal drugs. So we can use for repurposing. We understand the reverse pharmacology also. Many of our drugs, we know that this is protected. So this particular at AI will make our job easier, particularly with using our own herbal compounds also, and with the new compounds also. So study reveals the gene expression change with meditation and prayer. So now what is the solution? I will say one solution. If you read the recent paper, I think 1 week back, with the Yoganindra, with IIT Kanpur have done the study. They have done the functional MRI. They found that hippocampus area, there is the activity, metabolic activity gets slowed down. So when you do the prayers, research in Wisconsin, Spain and France, first evidence of specific molecular changes in body following a period of mindfulness meditation. That is why when we say the yoga or meditation, there is science. If we say do yoga, it has no relation with the religion, no relation with the caste or creed. It is the health, one of the good health resources at the free of cost available with us. Because Patanjali Yoga with thousands of years back, India has got this, and we should now systematically, only thing we need a scientific evaluation. So it's good that IIT Kanpur had done the research study with the functional MRI. They produced the evidence. Yes, this is what it is. When you do the Yoga Nidra, you are all stressed, you get relief. Your MRI, the brain functional activity, metabolic activity gets slowed down. So this is very important for all. When we say the oxidative stress, we have constantly DNA damaging, pollution, noise, the stress. We are constantly damaging your DNA. But your lifestyle is one solution, apart from the drugs. So mind-body interventions such as meditation, yoga, they don't simply relax us, but they can reverse the molecular reaction in our DNA. Yes, I must share, we have not done the study. People have not done the study, I think. But one has to do the study that you do the pre-yoga or pre-meditation, you do the DNA damage, you do the chromatin exchanges, you do look at the pathway, and then post-meditation, you look at the people and look at the study. I'm sure that we are going to find, I have not come across the study, but one should do that study. So research published in Journal Frontiers in Immunology recently, they reviewed over a decade of studies analyzing how the behavior of our genes is affected by different particular yoga systems, including mindfulness and yoga. And that is why I think lot of now people, they say you do yoga, Kriya yoga, so many things going on. It has become a business. But it is not. I think it's because the Kriya yoga, Yoga Nidra, meditation, they're a very important part of the health. And I think it's not only for the India, for the entire world. This is one-point solutions for all of us. How to remain fresh, how to remain, the calm. Because I think today paper also came with your mind is, you have a healthy or the very silent mind, you become more productive and more thoughtfulness. So your yoga definitely will help us to protect us for the further complications of the disease when it occurs due to the damage in our DNA. The experts from the universities conclude that when examined together, 18 studies featuring 846 participants over 11 years reveal a pattern in molecular changes which happen to the body as a result of the MBIs, and how those changes benefit our mental and physical health, because that is very important for mental and physical health is very important. So when a person is exposed to a stressful event, the sympathetic system, nervous and as the system responsible for the fight or flight response is triggered, in turn increasing production of a molecule called nuclear factor kappa, NF-kappa B, which regulates how our genes are expressed. So many of the autoimmune disorders also, they are responsible because of the stress conditions. So the take-home message is respect and love nature. Nature will love and care for you. We cut the trees and they say we will grow the new tree, but you know that it takes 20 years, 30 years time.
Genomic imprinting depends on the environmental factors like nutrition. It's not only the mutation is there is going to have a disease or going to have benefit. It's the nutrition, atmosphere, prayers, thoughts, and food habits. Very important. Protect your DNA and keep it healthy by adapting a healthy life. You need to protect our DNA because nature has given us free, which is our job to protect it. Do not challenge the nature, instead try to understand the nature. Do not challenge it. Try to understand why nature has done it with some meaning. And yes, at the outset I would like to thank all my scientists, colleagues and the several agencies. And for diabetes work I would like to thank the Lalbhai group who gave us a generous money for the grant. The CSI is a part of the genoprotective effect of the study, the CSI grant, and the DBTs, ICMR, or the several grants we have receiving. So this is for the, so I just my acknowledgement to all of the granting agencies, all of my clinical call, because you cannot do the work without clinical collaboration. There has to be good dialogue between the scientists and the clinicians, because you clinicians know the problem and the scientists are there to solve the problem. You have to have a good dialogue between both of them. As a pharmacologist also, you need to have a good dialogue between the clinician also. Then you understand what exactly they demand, and accordingly you can develop the drugs also. So thank you very much for giving me an opportunity, and thank you all of you. Thank you.
Thank you so much. So what we'll do is we'll be having the question answer session. Because we are running short of time, we'll be having the question answer session after the end of this session, that is after the talk of Dr. Senthil Natesan. So thank you very much, sir. Thank you for enlightening all of us with your talk on the influence of the environment as well as the toxicants, specifically the lifestyle disorders, that is diabetes, obesity, vitamin D deficiency, vitamin B12 deficiency, and the effect of meditation and prayer. When I called him on last week, he was there in Rishikesh and he just messaged me that I am in Maun Dhyan Yoga. So whatever he has said today, he's actually practicing that. So thank you so much, sir. Thank you for being here. Now I would like to invite the next speaker, that is Dr. Senthil Natesan. We are very privileged to have Dr. Senthil Natesan with us over here. He is the co-founder of QRL Biosciences Private Limited, a biotech company focused on cell-based therapeutics for treating chronic diseases. He is also the founder of Biomake Life Sciences, which is focused on developing immunotherapies for cancers. Dr. Senthil completed his veterinary medicine and then specialized in the field of virology, cell biology and immunology. He has completed his doctoral degree from Indian Veterinary Research Institute and postdoctoral fellowship from Johns Hopkins University School of Medicine. Then he worked as an assistant professor at Indian Institute of Human Virology and University of Maryland School of Medicine in USA. He has worked on cellular tropism of human immunodeficiency virus and developmental biology of immune cells, and has discovered novel previously unknown cells in human system and exploring its use for treating different diseases. Thank you so much, sir. Again, once again, we welcome you over here, and the stage is yours. Thank you.
Thank you for the introduction. So I'm going to, the next maybe 30 minutes, talk about the cell therapy opportunities and challenges in India. It's slightly different from in all the toxicology topics that we have discussed, but I think it is going to open up the future thinking that, because this is a new emerging class of drugs, how we are going to think differently in terms of understanding the toxicology, and how do we generate the data that is acceptable to the regulators to develop this as a new drug. Traditionally, if you look at the drugs, the first class of drugs, which are small molecules, and then the large biological molecules like monoclonal antibodies, antibody drug conjugates, and now we are having a new class of drug, which are cells. And how is it different from the rest of the class of drugs? Because they are living, and so when you think of doing a toxicity study, we really need new models, new animal models, such as humanized mice models, and also we need models like 3D or alternative to animal models, also AI/ML based models, which will accurately able to predict these drugs' safety, efficacy, toxicity, so that it will be acceptable to develop with the data that can be acceptable to the regulators. Then it could become a part of the drug development. So I'll talk about more about the opportunities. First, I'll talk about all the different type of cells used as a drugs, how it is opening up new opportunities for countries like India, and then I'll talk about the challenges that are more globally and also specifically in India we are facing. And if you look at this data, it's slightly old, but it's still relevant, and there are around more than 1,200 cell therapy trials were going on globally. The above image shows the preclinical and early stage studies, and the below one shows the later stage phase 2+ studies. I can't see the old map in the background, and so if you look at it, this is the USA, where most of the studies, and here is China, and this one small dot that's the early stage studies going on in India, and the late stage study almost nothing in 2000, and even now only hardly few studies are going on in India. So why there's not much studies in countries like India and also in developing countries? Because we don't have a right model to evaluate this, to study the toxicity or safety or efficacy. We don't have acceptable models. So it's a time to think about it, and how do we come up with the acceptable model that will evaluate these drugs. So these are the different cell types are in clinical trial. As of 2023, we have around 34 cell and gene therapy products approved by the FDA that is already in use, and there are many more in pipeline that is going to be approved very soon. So as I said, like a small molecule or biologicals, now the living cells are considered as a drugs. So all the regulation that you apply for other drugs also applies to this one, but it is different because it is living, right? It's inert biological or inert small molecule. You can manufacture in batches and put it in a normal storage condition, but this is a living. You have to maintain the viability, and you have to deliver it within acceptable time without compromising the viability of those cells. So you have to think differently, and also it's used as a drug. It's used for treating different diseases, and it could be a simple cell therapy where you deliver a unmodified cell for treating a particular disease. It's also sometimes combined with the gene therapy, where you deliver the genes in a vector, like a viral vector. You will be using that particular gene to replace a defective gene, and many times there are cell-based gene therapies where you modify the cell ex vivo in the laboratory, and you put the insert gene and modify the cell, then give it back to that patient to bring the treatment, to bring the cure. So this is another level of complexity increases when you take a normal cell, just give it, and when you put a gene and give it, there's a completely different level of complexity. And if you look at all the different class of different type of cells used in the clinic. These are already in the clinic. You can classify them into either one of these two categories, stem cells or immune cells. In stem cells, it can be a hematopoietic stem cell, mesenchymal, induced pluripotent stem cells, and or tissue-specific stem cells. So embryonic stem cells, a lot of ethical issues are there, so not much work is going on that one. In the immune cells, T cells very widely used in the clinic for treating the cancers. Natural killer cells, dendritic cells, gamma delta T cells, tumor infiltrating T cells. So they are used either in the natural form or genetically modified for treating the diseases. Let's talk about the hematopoietic stem cells. It's a very old. It's been done for the last 50 years. What you call bone marrow transplantation, essentially it's a hematopoietic stem cell transplantation. And hematopoietic stem cells, they give rise to all type of blood cells. It's called hematopoiesis, and it is used for treating several malignant diseases and also non-malignant genetic disorders like thalassemia or sickle cell disease. And their number are very, very small. Normally in the body, you get it from the bone marrow. Normally nowadays, nobody goes to the bone marrow to obtain these cells. You can mobilize these cells by giving growth factors like GSF, and then you can mobilize them into blood. Then you can do a leukapheresis procedure and isolate all these cells, and then give it to the recipient. So generally, a diseased patient, bone marrow has to be destroyed before giving this donor cells, because you are wiping out the entire bone marrow using cytotoxic drugs, and then you are repopulating the bone marrow with donor hematopoietic stem cells. And so this has been done for a long time. So now the purified, characterized hematopoietic stems are also available as a commercial drugs. You can get it through a commercial source, and the challenges are, as I said, the number are very low, and so you have to go through extensive characterization, and there is a cutoff. If you have above this number, then only that donor hematopoietic stem cells can be used for the treatment. And another thing is the HLA matching. So these are allogenic cells. So you have to do HLA matching so that the recipient's body will not mount an immune response against the donor cells. It's not possible to have 100% match, but at least you have to have an acceptable level of match to minimize the development of graft versus host disease. Again, it's a life-threatening condition when the donor cells start fighting against the recipient in the recipient body. So that you have to manage. Generally, this cost very high. Cost is very high for this bone marrow transplantation, and also managing this patient, it's very difficult. You have to keep them in a very isolated environment, sterile environment. So long time hospitalization is involved. So there are many genetically modified hematopoietic stem cells. They are also available. They are also approved by the US FDA recently. I just put here these 3 drugs. Casgevy, it's used for treating sickle cell disease, and the other one is also for sickle cell disease. This is for metachromatic leukodystrophy. If you look at the cost of these drugs, so they are really, really expensive, and this Casgevy cost around $2.1 million, and this one cost around $4.5 million. If you convert in Indian rupees, it's around 30 crore for treating one patient. It's a single dose therapy, and it costs huge amount. So if you look at the affordability in India, even the richest people, it will be difficult to get these drugs. So we need to come up with a drug development process that is more cost effective in terms of developing a regulatory data that is acceptable by the regulators. So this is one of the challenge that how it's going to be affordable. Here what you do is essentially you take the hematopoietic stem cells, so you genetically engineer them to make a functional hemoglobin gene, and then you put it back so that they don't have to go for repeated blood transfusion, which they need normally when they are suffering from this disease. The mesenchymal stem cells. This is another type of stem cells where it has a limited potential to differentiate either bone or cartilage or a fat cell, and so this can be obtained from the bone marrow or adipose tissue, and it can be cultured. It has a limited expansion potential. It can be cultured, and then it can be differentiated into a cartilage cell. If you want to use it for treating a cartilage damage, osteoarthritis, you can differentiate them into a cartilage cells, and you can give it back to the patient. So it is again safer if it is autologous, but again it can be also used in the allergenic setting. But you have to take care of the rejection and graft versus host reaction. So there are many products, mesenchymal stem cell based product available in the approved by the FDA for commercial purpose. Again, the challenge with the mesenchymal based drug is when you inject these cells, 50% of the cells will die quickly because the recipient body react against these cells. So for long-term survival of these cells, HLA matching is important. Even though it is used mostly in the osteoarthritis and a cartilage damage, the results are still not highly encouraging, but yeah, it's very weak positive. So to overcome the limited availability of the stem cell, right? So any stem cell, if you go, you have to go to a bone marrow. Again, you are not getting less than 1% of the stem cells, and so to overcome that, so scientists have developed this induced pluripotent stem cell technology, where you take a adult mature cell like fibroblast or epithelial cell or a blood cell, and you put a set of transcription factors. These are the genes that you introduce into the cells, and then you reprogram it. So once these genes goes inside, this adult mature cell turn into behaves like a stem cells. So then you have access to large number of stem cells. So then you can differentiate that into whatever the cell you want. So that is very well proven now. So this is overcoming that limited availability of natural stem cell in our body. So this has, when it came, this technology, it was very promising, and but still there are challenges. Even though sometimes when you generate too much of stem cells, that's also a problem. So how do you overcome that? So by reprogramming, you can use those differentiated cell for therapy. Also, you can use that for drug screening. And it's more relevant when you are talking about the toxicity studies, and so you can avoid going to the animals. You can directly iPSC derived liver cells, neuronal cells. You can do the toxicity studies. So all these different types of cell can be obtained from the industry pluripotent stem cells, and you can use that for therapy or drug screening. But as I said, here the challenge is obtaining that pure form of the differentiated cells. So one of the biggest challenges, you never get a pure form of that differentiated cell. You always have a mixture of differentiated cells and still some stem cell. And the stem cell, because it's highly proliferative, there is always the risk of producing a tumor. So you can't. That's one of the factors that is inhibiting this technology translated into the human use. So far, only one small trial was done in Japan using the iPSC-derived retinal cells for treating the macular degeneration. It's an eye disease. For treating that, they have tried. The first patient, they injected it, and it went smooth. And then the second patient, when they tried to inject, they found there was a mutation in that iPSC-derived retinal cells. So they have to abort that because the stem cells, when they proliferate very fast, they accumulate certain mutations not acceptable, which is which has higher risk of developing cancers. So again, to overcome this issue of tumor generations, highly proliferative nature of these cells, the new technology has come up, something called a transdifferentiation. So you take a mature adult cell and differentiate directly into a cell you want. For example, you take a skin cell and differentiate that into a brain cell or liver cell or a pancreatic cell. So that way you are not reprogramming that. So here the risk of developing a tumor is very less. So this technology is having many advantages and people are working on it. It's relatively new. And there are tissue-specific stem cells. If you take liver, brain, cardiac, and eye, there are tissue-specific stem cells. So they don't have potential to differentiate any kind of cell, but they can differentiate into that local particular type of tissue where they are located. For example, in the eye, there is a limbal stem cell at the corneoscleral junction. So when you have those cells can differentiate into corneal epithelium and to replace that wear and tear normally happens in the corneal epithelium. So if there is a bone or if there is an injury in the eye cornea where the replacement is not enough. So there is a limbal stem cell deficiency because of this injury or a burn. So in that condition, you can actually take a biopsy of that limbal cell tissue, small biopsy, 2 mm by 2 mm from your healthy eye, and you can culture that cells onto a matrix, which is amniotic membrane, and then you can transplant it back into the damaged eye. And the data shows that it can restore the damaged cornea and vision can be restored. And there's one product in Europe, Holoclar. It is based on this technology. It's available. Even in India, there are in LV Prasad in Hyderabad, they have done a lot of work on this. But again, when it comes to as a product approval for commercialization, because as a research, they have done a lot of work. But a commercial development, there were a lot of challenges because they had to produce all the animal data, safety data, toxicity data, and eventually, they didn't progress much, I think.
They're using now.
Sorry?
They're using now.
They have done extensive study a few years back, but now I'm not seeing it because I think the regulatory come into the picture. That's what I mean. Yeah. They published a lot of work on that. Same with the myocardium has the cardiac stem cells, and they are very well characterized. And during the heart attack, myocardial infarction, these resident stem cells, they get activated. They can differentiate into cardiomyocyte or smooth muscle cells or endothelial cells and try to restore that. And so these kind of tissue-specific stem cells are also can be isolated and they can be used as a drug. The other category, immune cells, as I said, different immune cells are also used mainly for treating the cancers. The T cells, when I said that 1,200 trials, more than that it is going on. If you see, more than 50% of the trials are on the T cells. Out of that, the CAR T cell contributes a lot. The chimeric antigen receptor T cells, it become a miracle drug when they tested in some of the children with suffering from acute leukemia. It's a deadly disease. Once they fail on certain drugs or a stem cell therapy, there is no cure. When they put them onto this CAR T cell therapy, almost 80% of the children, they completely cured from this very deadly leukemia. Then they tried in lymphoma. They had a fantastic result, and so there was a lot of excitement about curing a cancer using this technology. And again, it's very complex to develop this technology because you have to take the patient's own T cells and you introduce the chimeric antigen receptor, which is a synthetic gene that gives the specificity to this T cell to go and bind to the cancer cells, so that it specifically target that cancer cells and eliminate them. So by this way, so it worked very beautifully for certain type of B cell, type of acute leukemia and lymphoma, and now they are extending that to putting the natural T cell receptor and engineering the T cells and using them for the treatment. So again, for all these things, how do we do acceptable toxicity studies, and how do we generate the data that will be acceptable by the regulators? So we had to come up a new way of generating data that is not different from the small molecules and biologicals. So there are lists just keep on increasing. So initial set of CAR T cells were targeted against the CD19 molecules, and now the BCMA targeted for the multiple myeloma also got recently approved. And so as I said, these are really completely curing more than approximately 80% of the patients who are about to, who don't have any option, who was about to. So again, the dendritic cell is another living drug, which are very good for targeting the solid cancers. And as you know, dendritic cells are most potent antigen presenting cells in our body. So if you want a T cell to recognize the cancer cell and kill them, the T cell has to be educated by the dendritic cell. So the dendritic cell picks up the antigen, cancer antigen, and then present it to the T cell, and that's how the T cell get to know that, okay, this is an antigen I have to target and kill. So for that education, the dendritic cell is most critical. So if you wanna, so this can, how it works, you isolate the dendritic cell from the blood. It could be from the hematopoietic stem cell or monocyte or natural disease, and you give them certain growth factors like GM-CSF and IL-4, and you can generate an immature dendritic cell. Then you give the antigen and educate the dendritic cells to present the antigen to the T cells. Then you put them back into the body. So when you do that, one dendritic cell, when it goes into your body, it can educate hundreds of T cells. So then the T cells, they proliferate and go act against your cancer cells. So again, this is very well studied, and there was one product approved, Provenge, for treating the prostate cancer, and so a lot of trial has been done, and it's a good technology for treating the solid cancers. The natural killer cells. The advantage of natural killer cells is they can recognize the antigen independent of antigen presenting cells. So as I said, T cell need the antigen presenting cells to recognize the cancer cell and then to mount an immune response. So many cases in cancer cells, they downregulate that MSC expression so that they don't get detected by these T cells. So in those conditions, when the cancer cells don't express the MSC molecule on the surface, NK cells can recognize them. So another level of innate immunity. So these NK cells, without any antigen presentation, they can recognize the cancer cells and they can mount an immune response. So you can isolate these cells from the patient's blood, and you can, in the presence of certain cytokines, you can expand them and you can give it back to them. So how these novel drugs, in terms of process flow for the treatment, it can be either one of the way, depending on whether this is an autologous or allogenic. If it's autologous, you have to collect the cells from the patient in the hospital, and you have to bring it to the processing lab, manufacturing lab, and then you manufacture the product and then send it back to the hospital where the patients get treated. If it's allogenic, you get the cells from a donor, and then you make the product and store it under the liquid nitrogen condition. Then when the patient comes to the hospital when he needs the therapy, you just request it and it will be sent to the hospital where he will be administered. So one of this model they had worked out depending on autologous or allogenic. So now I talked about all these new drugs, living drugs, and there are challenges in terms of testing them and bringing them to the market. So in the next few minutes, I'll just talk about what are the common challenges, how is it different from the classical small molecule drugs. So first challenge is from discovery to preclinical, right? So you have to have a proof of concept, and you have to generate a lot of data that is eventually acceptable by the regulators. So one of the most important thing before even entering into the preclinical stage is testing is determine the product profile. So your product in the small molecule, you know that, right? This is your chemical structure, this is your characters, physical characters, this is your toxicity profile and all those things. But here, yeah, you have to similarly, you have to define your product profile. Okay, this is the cell, and then this is the characters. These are the markers of the cells. This is the identity of the cells. This is the characters of the cells. So that, and this is the kind of dose I am going to put in the patients. So all this product profile has to be defined even before entering into the preclinical testing. So you have to determine the mechanism of action, like any small molecule, right? Any biologicals, and you have to tell that how this drug is going to work. How if you are going to target curing a particular type of cancer, so you need to know how it is going to work. Is it a direct link, or is it through secretion of certain cytokines or cytotoxic chemicals? So you need to do extensive research work on that, and it requires you have to develop a lot of specific assays and use models. So you have to determine the mechanism of action at the discovery level. So when it comes to the toxicity study, this is much more becoming difficult for these living drugs, because you have to determine a suitable animal model. And so here, because it's a living cell, it's a human cell, you cannot simply just put it in a mice model and do the testing, right? So mice will definitely reject it. So to overcome that, there are immunodeficient mice, and even though some of the early versions of the immunodeficient mice doesn't mean that it's completely devoid of any mice immune cells. They do have a certain type of their own immune cells, even though they are deficient in major immune cells like T cells and B cells, but still they may have NK cells and monocyte macrophages. They can alter your cells' behavior when you inject them. So there are some advanced immunodeficient mice models like NOG skids, which are known to be completely not having any of its own immune system, but they are not available here in India. So if you want, you have to import it. It's very expensive, and again, it's limiting all the studies that what these kind of drugs may need to generate the data that is acceptable by the regulators. So you have to come up with some artificial intelligence or machine learning or alternative to animal testing, and to generate those data. Also, whatever the data you are trying to generate with the preclinical studies, and it has to be match with your proposed clinical trial design. So how, if you are going to study the drug in a model, and you need to have a relevant model in animal, and so that it's not completely different. It should mimic your clinical trial design. And also you need to mitigate the risk that what you would expect in the human, and also you have to understand after administration of your product in the animal, what is its fate, or is it how long it's surviving, and is it differentiating, or how the distribution happens, or is it causing any tumor. So all this preclinical toxicity data you need to still generate it, but how, or what kind of acceptable models you are going to use it. So in our case, where we were studying the wound, so we were trying to test some human cells for wound, and we cannot put our cells in the animals. So we were trying to develop the model that is whether we're using the same process what we are using with the human, whether we will be able to generate a homologous cells in a particular animal, so that we could test them, and we screened few of them, and we found that in chicken we were able to generate that particular homologous cell that is comparable to human, but not in the mice and rabbits. So another challenge facing this kind of cell therapy development is they're sourcing the raw material. So here most of the raw materials are non-conventional. They could be a cell culture media or a serum or enzyme, cytokines, growth factors. So all these raw materials are not like defined chemicals, right? So you have a lot of variation in that. Their supply is inconsistent because sometimes if you look at the serum, you are not going to get the exact same composition because every animal and the composition is going to be undefined. So you have to deal with that. And also the low temperature storage and shipping. And throughout the shipping, the sample has to be maintained. Otherwise, your growth factor activity will go down. And some of the components in your raw material, they are temperature sensitive. So you need to keep that all in mind. So when you come to the manufacturing facility, it has to meet the regulatory requirement. It's expensive to build, and it requires expensive equipments, bioreactors, clean rooms. Of all this, the difficult part is you need to train the people to work in that environment the way it's supposed to be done. So they require extensive training, and so currently there is a huge gap in the manufacturing of cell therapies, and we don't have enough manufacturing capacity. Again, the manufacturing facility should support your manufacturing process, and when you're talking about the autologous cell therapy manufacturing process, you have to work within a very limited timeline, right? Sometimes, when the blood is collected or cell is collected, and it has to go back to the patient within the timeline. Generally, the vein-to-vein time for a CAR-T or most of the therapies, it's less than 21 days. So in that 21 days, you have to optimize your manufacturing process before the first dose is even sent to the patients. So it requires a lot of planning and execution, so that your facility has to support that. And again, that depends. The complexity increases when it comes to what kind of cell therapy you are manufacturing. So if it is your simple mesenchymal stem cells, you just have to seed them and expand them, characterize them, and you can send it. But when it comes to the CAR-T cells, you also take care of the cells, but also you are taking care of your viral vector, because you're going to introduce that gene, and then you make the viral vector, then you add it to your cell manufacturing process. So the facility and manufacturing complexity, all this increases, and this all has to be again validated before you go into the human trial. So again, the another complexity is the regulatory side. So because each product is very unique, and one guideline or one regulation can't solve all the problems. The regulatory agencies, they are also facing these challenges, and so the evolution, it's an evolving process. Right now, I think even the FDA, DCGI, all of them look at the cell and gene therapy as a unique. Each product is unique, and so there may be a slightly different for each product to get into this clinic, and so that because of a lot of these uncertainties, it may take a very long time for the entire regulatory process to go through. Many times it will take up to a year even to get a simple test license, and it will eventually lead to a significant delay in the commercial manufacturing. So you have to be aware of that. So when you go to clinical clinical studies, again, these are even though autologous and living cell products, and they can cause toxicities, and the clinician has to be aware of it, and they need to be trained, and the toxicity could be a cytokine storm or a neurotoxicity or a off-target on-site or on-target, off-site toxicities. So to deal with these patients initially in the trials, later on for the routine treatment, the centers has to be trained. There should be a specialized centers. They are, after administering these drugs, what kind of toxicity they may expect it. How do we predict it even before that, and then take care of, how do we manage that toxicities. Again, there's a lot of opportunities for artificial intelligence and machine learning, and how we can predict based on certain biomarkers. For example, in CAR T cells, before somebody is going into the cytokine storm, we know these are the markers, they have to be monitored. So they had to be 2 weeks, they had to be admitted. They are admitted in the hospital once in every few days. They have to be monitored for certain biomarkers in their blood. And if so now for certain treatment, it is well known that before somebody going into that toxicity, we can predict them and then put an intervention so that the toxicity can be managed well. And in bone marrow transplantation, which has been done for a long time in India, still we have less than the actual requirement, less than 10% of the actual requirement in terms of managing those bone marrow transplant in the patients going through the bone marrow transplantation. So again, this process also involves a lot of funding, and when you have some resources, you spend it in R&D, then you do manufacturing, and you go clinical trial, and then you run out of the fund, then you may not be able to generate the commercial product. So you continuously you have to also generate the resources, and that's why if you have a good testing model or something to support your development process in terms of generating acceptable data, you may be able to save the resources and able to take your product to the market. Otherwise, without in the uncertainty, if you go and test a number of animal models and still if it's not acceptable, you're losing your resources, and then you will not be able to successfully develop the product. So you have to be very careful about that. Again, these are the living products. Either you have to transport them in a cryogenic condition in the liquid nitrogen or in a cold refrigerator conditions, and otherwise you will you have viability issues and you will lose the potency of the cells. So in this process, the chain of custody is very important. So there are multiple people involved in this one. Either the one part is the lab manufacturing it, then the courier service, and then the hospital. So all of them has to ensure that the quality and efficacy of the product is maintained and it's delivered to the right patients. And some products have a very constrained timeline. Some of the products you have to deliver it within 48 hours. So if you are sitting in somewhere in tier 2 or 3 cities, and sometimes you may not be able to deliver your product because of these complexities. And again, if you are shipping your product across countries, there is a lot of bureaucratic delays. You have to keep that in mind. So when it comes to the patients finally who is going to use it, it has a very high price tag, and almost 90 to 95% of the patients can't afford the currently available cell therapies. So we need a unique way of thinking and developing these drugs that is more affordable for these patients. So countries like in India, we don't have any insurance coverage or government coverage. Government coverage is there, but still no way that is going to be closer to the cost of these products. And again, when it comes to allergenic product development, the HLA matching becomes very challenging because Indian population is very diverse and it's a huge population. Picking a HLA donor, matching donor, again, it's a very, very big challenge. So I think, I'll stop here. I think, so that's where to overcome these challenges, to develop acceptable toxicity data, where if we could have a novel alternative to animal model and using the artificial intelligence or machine learning, I think it will be a great boon for us to develop these drugs and make it to come to the market and make it more affordable for the Indian patients. Right, I'll stop it here. Thank you.
Wonderful talk. Really enjoyed it. My first question to you is, before I ask real scientific questions, why did you come back to India if you have all these problems you're presenting that it will never happen in India? For all these things that you're talking about, the logistics, patient recruitment, costing, affordability, and the preclinical research, we can't do anything here. Why in India you should go back and start a company in the US where you have all these facilities?
No, but we have a huge population in India. Somebody has
No.
to
You can bring the product back to India. So my question, what I'm planning to do is go and work as a postdoc in Miller's lab and do a better job, because from there I can bring the products back to India. But
no, I think it's always the first product when you set up the stage. I think they're always the first person who into that go through that challenge. I think, and that is in Indian regulatory system, or in India, that is the thing. There is hundreds of people waiting on the line to just follow it, but always the first person or first company, first people who carve the path. I think that's going to be the.
But the first thing is you become the Prime Minister of India and then start laying out the. No, I'm just joking.
He
But
is open to that, I think.
yeah, real scientific question for you is that when you talk about, I'm not talking about cell therapies right now. I'm talking about using drug screening, right? These cells, even if you develop them to neuronal cells or cardiac cells and everything, they still grow in cell culture. Okay, my primary cells that I take from liver or neuronal cells from human bodies, they don't grow in culture. That's the fundamental difference people have ignored for a long time. So even hepatocytes, I actually develop them from the iPSCs or MSCs. They have the fetal cytochrome P50 expression, not the adult cytochrome P50 expression. People have to characterize them so deeply, and that is a fundamental fault that people are using these for drug discovery. I'll get a neuronal cell from stem cell and do it. That's one question for me. How do you manage that? Number two, it's not a question. Let's collaborate because I need your help.
Sure.
Thank you so much, sir. I would like to interrupt the discussion in between because I would really like to thank Dr. Jayesh Sheth because he is having another meeting and would like to leave the forum. So I really would like to continue the discussion after we thank him for his presence over here. Thank you so much. Before that, I would also like to thank Dr. Senthil Natarajan for his wonderful insights regarding the cell therapies, the challenges, and the opportunities for AI and ML. With that, I invite Dr. Miller to hand over the memento to Dr. Jayesh Sheth. I also request him to hand over the memento to Dr. Senthil Natarajan. Thank you so much. Now, if the students have got any questions, we can continue while we are having our lunch. The experts are already available over there. Thank you. The lunch break will be only for 30 minutes, so please be soon. We'll be meeting soon, so please come back at around 2 o'clock.
Oh, okay. Oh, okay, it's here, right?
Actually, I did my BPharm from Sri Ram Murthy Smarak College of Engineering and Technology.
Okay.
Park Davey Center Research Center, that is in the Minnesota. Then after that he joined Bombay College of Pharmacy as an assistant professor in Department of Pharmaceutical Sciences. Further to now he is a professor at the same Bombay College of Pharmacy, and he is also the chairman for the Board of Studies at University of Mumbai. He is also a member for the ad hoc Board of Studies of Pharmacy of Mumbai University, and his research area broadly include the mechanistic drug metabolism, development of in vitro metabolism, methodology, population phenotyping and genotyping, drug interaction prediction, modeling, simulation, and many more. So with this short, brief introduction about this, sir, I'll request sir to kindly deliver the talk. Welcome, sir.
Thank you. Can you hear me at the back? Can you hear me? Way at the back? So इसमें slide ये है आगे पीछे.
And this is the laser, sir.
Okay. Okay. Deepak always does this to me. He either gives me the last talk before lunch, or he gives me the first talk after lunch. And I have no idea why he does that. And more importantly, as I came into the room, I realized that there are a lot of first year PharmD students, and they very graciously said that they have no idea what's happening in this room because they have just started their journey in pharmacy. So what I'm going to do is kind of go away from what I plan to do and make sure they understand something, because this is the first conference of ACS TOXI, and I feel that when we begin for the first time talking about toxicology and all these things, it's good to let all the people know some of the basic concepts which are necessary for one to know before we go on to some of the advanced topics. Okay, and the other thing is, the other thing I do is every morning I get up, the first thing I do is I take a shower, okay, and make sure I put a bunch of deo so that I don't smell bad. So I have no idea why people are sitting so far back, okay. I'm not that unclean and that you have to stay away from me. Just come forward a little bit so that you feel included in all those things. Come. Just come, move forward. Okay, it's a class, okay. So there's no need for you to like go way back and kind of be away from the action, as they say. So, આગળ આવી જાઓ, હા? ગુજરાતમાં એમ જ કહે ને? હા, જરા આગળ આવી જાઓ ને. અહીંયા આવજો. કેટલા બેન્ચ ખાલી છે અહીંયા? હા, just move a little bit. All those last benches, just so that you feel part of the thing, okay, rather than being so far away from everything. There we go. Thank you. So nice of you. My target is that row there, which is the first year PharmD. Okay. So we are going to have a little bit of a discussion. You must have heard about a lot of chemicals which are dangerous to you, and that's why we are talking about toxicology. Just to ask you, if I were to ask you to guess, from the time you got up in the morning to now, how many chemicals do you think have entered your system? If you were to take a guess, anyone, take a guess. And when you guess, you can guess anything and you will not be wrong. So take a guess. First year, come on, PharmD. How many chemicals do you think have entered your system without you knowing or with you knowing? With you knowing means if you smoked and all, okay? Without you knowing means you didn't know what is going in. How many chemicals do you think entered your body? Just take a guess. Take a guess. Put a number. Ketla? Number, ketla. Kaya nahi, ketla. 10,000. Anyone? Anyone else? And if I were to ask you, Sukam 10,000? Kadu, sprayed perfume. Kayu perfume atu? Just ask. She's actually very right. The number of chemicals which typically would have entered your system from morning to now will be close to around 10,000. And many of them have gotten without you ever intending for them to come in. Okay, for example, when you had chai, no, what you wanted was caffeine, so that you feel stimulated. But इधर का चाय में खाली कैफीन नहीं रहता है ना, वो मसाला चाय, तो थोड़ा जिंजर, थोड़ा अदरक, थोड़ा दालचीनी, ये वो डाल के they make, and all this is for flavor, and they are going to enter your body without you wanting them. Then you have lunch. Lunch actually है ना, खाना है तो क्या है ना, थोड़ा starch powder ऐसा डालना चाहिए, एक वाटी तेल, थोड़ा soya protein. If I put that on your plate, no, you will never eat it. So what do? We put again lot of spices to make it flavorful, and all of these chemicals have no nutritive value, but they only make your food palatable, and you take it in. और वो सब करने के बाद 4 लेक्चर के बाद हेडेक हुआ ना तो एक पैरासिटामोल लेते हो, and that is intentional. Okay, but whatever happens, no, you are consuming lot of chemicals are entering your system. Not only chemicals, from the time you got up in the morning till now, it has not been a sterile environment. So as you walk around, no, lot of bacteria, lot of fungi, lot of viruses, as you would say, are kind of coming in, and somehow after all that it appears as nothing has happened, and you are still what you were in the morning, which means that we have systems to take care of all of these things which are coming into our body and potentially vying to do something to it. So the two systems that we have to kind of defend ourselves, one from chemicals and another from all of these viruses and bacteria, are the two defense systems that we have. He talked a little bit about the other system, which is antibodies. Okay, if you remember, he said CAR T cell therapy, antigenic receptor, targeting, etc. How many antibodies do you think you are able to produce? Anyone? Take a guess. How many different types of antibodies can you potentially make as a human? Anyone? First year, Ketla? Aim nahi, variety. That means what? How many different antigens you can recognize which come into your body. So if I make 5 antibodies, does it mean I am able to attack only 5 organisms? No, no. So within those 5 types of antibodies are antibodies whose structures are so different that they recognize different antigens. Okay, and we just took on a vaccine, right? COVID, Moderna vaccine or the Indian-made vaccine. They are against that spike protein. Okay, so that is one type of antibody. But how many different types of antibodies can you potentially make in terms of variety, in terms of recognizing different antigens? Anyone want to take a guess? How many that is? 1,000, 300, 500, 10,000? We have the capacity to make close to 1 trillion different types of antibody. How many? Trillion. That is 10 raised to 12 almost. Which means any organism which comes in and your T cells are able to break it down and present that antigen to your antibody producing cells, our antibody producing cells can potentially make 1 trillion different types of antibodies. So actually no foreign organism can kind of escape an immune response. Okay, in a similar manner, 10,000 chemicals you have been exposed to today, right? How many chemicals in your lifetime till today? Variety wise? Millions. But amazingly, your body is able to handle many of these chemicals without a problem. But there, the system is very different. We have only about 300 enzymes or so which do all the metabolism to take these foreign compounds and make sure they are thrown out of your body. And how do they do it? They do it very simply. They take the chemical compound and convert it to something which is water soluble, and the minute they become water soluble, you can throw it out in your urine, in your sweat, in your tears, in your breast milk, in your any aqueous secretion that you have. So it's very interesting, right? On one hand, the number of antibodies you make is 1 trillion or so, and the number of enzymes that you have is only around 300, but still they are able to handle billions of compounds. In fact, we are not even worried that companies are making new chemicals, because we should be worried, no? When I was born, this chemical never existed in this world. Will I be able to handle it? But we never worry. Our enzymes are amazing that they are able to handle these chemicals even though they have never seen it before. Okay? So we have these two defense systems which work to protect us. Today I am going to talk about the second system, that is the enzymes which are able to do. And how do we do that? So let me say. Okay. How do we do that? We do a few different types of reactions using these enzymes. The first set of reactions, which are called as type 1 reactions, are simply, from a chemistry perspective, oxidations, reductions, or hydrolytic reactions. Okay? And the main aim of these reactions is to introduce a polar functional group. What do we mean by polar functional group? A group like a hydroxy group, or an amino group, or an acid group, all of which have a tendency to interact with water and make the compound water soluble. And we have a second set of reactions which are called as type 2 reactions, where what your body does is adds an entity which is very, very water soluble to your drug. For example, something like glucuronic acid, which looks like glucose, or a sulfate which has got a lot of oxygens, and the end product, which is a conjugate, is very, very water soluble, and that allows you to eliminate the chemical from your system. Okay. All this is done using these enzymes as far as the names are concerned. So the first two enzymes, which is the cytochrome P450 and flavin monooxygenases, they do only oxidation. The second enzyme, xanthine oxidase and aldehyde oxidase, also do oxidation but slightly differently. The third enzyme, which is alcohol aldehyde dehydrogenase, can do oxidation or reduction. The fourth one, which are the esterases, amidases and epoxide hydrolase, they all do what is called as hydrolysis. Okay? And as far as the second group is concerned, they all belong to this class of enzymes which are called as transferases, and they transfer different groups like glucuronic acid or glutathione or sulfate or an acetyl group or a methyl group to the drug to try and make it more water soluble. Collectively, the thing you have to remember is they add up to only around 250 or so. So you don't need to look at this slide, but this lists all the enzymes and the number of those enzymes that we have. And if you add them up, it's around 250. But what is it about those enzymes which is different from all the other enzymes that you know? One is that they all exist as families or superfamilies. So when I say cytochrome P450, in humans we have about 10 of them which do drug metabolism. When we say something like glucuronyl transferases, again we might have about 10 to 12 of them. So there are a number of these enzymes which collectively add up to around 250. And what is it about them that is different from other enzymes? They all tend to have what are called as broad and overlapping substrate specificity. What does that mean? Broad and overlapping substrate. So let us say I am an enzyme and I am designed to recognize everything which is wearing a blue shirt. Okay. So I'll go in and I'll see Mani, madam, gentleman there, him, all are wearing blue shirts and I'm going to metabolize them. That is the only feature I'm looking at. Okay. Then there is another enzyme which is recognizing only people who wear glasses. So that enzyme is going to recognize Dr. Miller, madam, Gupta ma'am, that gentleman again, blue and glasses. So you see what is happening? Two enzymes are going to attack him. The one which recognizes blue and the other one which recognizes glasses. So you see what is happening? Each enzyme is able to recognize a number of entities because the requirements are very general, like glasses or color or height or hair or no hair, curly hair, yellow. And the important thing is many times they work together. So two enzymes are able to recognize the same fellow. So collectively what happens is with a few enzymes we are able to metabolize lot of compounds, and therefore 250 is enough to do metabolism of millions of compounds which come in. Okay. The other thing is, because these enzymes are designed to be such that they recognize many substrates, none of the substrates binds very specifically to them. And because substrates are not binding very specifically, their catalytic rates are slow. So they tend to be much slower than many of your enzymes. For example, in your earlier lecture, somebody talked about acetylcholinesterase. Remember that? Acetylcholinesterase? That enzyme is one of the fastest enzymes known in nature. You know how fast it is? It can metabolize 4 million molecules of acetylcholine per second. How many? 4 million molecules of acetylcholine per second, and that is one individual enzyme. Single fellow can do that much. Relative to that, cytochromes are able to metabolize about 15, 20. But see, the trade-off is what? Do I want to be a hare or do I want to be a tortoise? Okay, one will reach faster, other is more sure. It is able to recognize lot more things. So the trade-off is, I am going to give away speed so that I can recognize more fellows, and I am able to do that metabolism slowly but surely. And that is why one of the things he said was, when you do microdosing, many of the P450s don't do metabolism because their KMs are very high. When you give a higher dose, then they start doing metabolism. That is indicating of the fact that these P450s are very slow in terms of metabolizing, but they do metabolism. Okay, and all of these enzymes are very interestingly set up. Okay, so now look at this next slide. If you look at P450, the way it does its oxidation is by producing oxine in the active site. Oxine, from your basic chemistry, is what you call as nascent oxygen. Remember the nascent oxygen? That is the same oxygen which is generated when you put bleach to whiten your clothes. That oxine is produced inside the enzyme active site, and it is one of the strongest known biooxidants. So these enzymes are able to do oxidation because of oxine, and because oxine is electron deficient, substrates have to be electron rich so that they can react. If you want to know what is about oxine, you must have done biochemistry, right? Glycolysis, TCA cycle. Remember that in your 11th and 12th? Glycolysis, TCA cycle. और उसके बाद third क्या है? ETC. ETC, if you remember the picture, ETC, oxidize, reduce, ISA bracket, oxidize, reduce, bracket, oxidize, reduce, bracket, oxidize, reduce, bracket. But what is there at the end? Remember what is there at the end? It says half O2 going to H2O. What is half O2? Half O2 means O, and that is oxine. So even your electron transport chain uses that oxine because it is such a good oxidizing agent, and it can be used to oxidize everything. If you look at FMO, it also does oxidation, but it uses a weaker oxidant like peroxide, and therefore it is able to do far less oxidations than cytochrome P450. Now you look at xanthine oxidase, it also does oxidation, but it uses hydroxyanions, OH minus. So here the oxygen is electron rich, so substrate has to be electron deficient. Then you have aldehyde alcohol dehydrogenases, they use NAD and NADH to do oxidation and reduction. So you see, if you throw any chemical in your body, one of them will be able to accept it, and they are able to do the reaction. So they are beautifully designed to work together. Not only that, they have broad specificity, and therefore we are able to handle so many chemicals without a problem. Okay. Now, if you look at the transferases also, that is the second group of reactions, they are also interesting. Half of them are ones which require substrates to be nucleophilic, and the cofactor is electrophilic, while the others require the substrate to be electrophilic and the cofactor is nucleophilic. So any compound you throw at you itself, when it is lipophilic, your body converts it either to an electrophile or a nucleophile, and then it does this type 2 reaction to generate something which is very, very water soluble and throws it out of your system. Okay, so here is aspirin, acetyl salicylic acid, dispirin. You consume it, and these are all the metabolites which are formed. Okay, salicylic acid, esterase, then glucuronidation, amino acid conjugation, another oxidation, and all of these are much more water soluble than aspirin, and they are all found in your urine. If you have another compound like say indinavir, you get lot more metabolites, again because you have so many enzymes. Here is valdecoxib, which is a COX inhibitor. It produces so many different metabolites because of the enzymes that you have. So any chemical that you consume, your body is able to convert it to something which is water soluble and throw it out of your system. And because it throws it out of your system, what happens when you take a compound? After a while, there is no effect. So if you want to get more effect, you have to take another dose. So if I have a headache today and I take paracetamol, headache goes away. But 5 days later, if I have a headache, I have to take paracetamol again because the original paracetamol is gone from my system. Okay? So that's how we develop drugs, to make sure they work for a little while and then they are thrown out of your system as your body returns to normal. Okay? But the problem is that just like your immune system, which sometimes will make a mistake and generate antibodies against your own proteins, what you call as autoimmune diseases, our chemical systems also make a mistake. Instead of taking a foreign compound and converting it into something water soluble so that it goes out of your system, it converts it to something which is toxic, reactive. It makes a mistake, and that can be very dangerous. Okay. For example, here is halothane. Okay, and halothane, if for first year PharmDs, is a volatile anesthetic. It is used as anesthesia when you undergo surgery. So if you are a patient and you are going to undergo surgery, the one question the doctor will ask is, have you taken halothane before? Have you taken halothane before? And if you have taken halothane before, then they do a little test. What they do is they take a little bit of halothane and inject it under your skin to make sure you don't show any allergic reaction or anaphylactic reaction. And the reason is that when halothane is given to people, one of the things that happens is that it gets converted by metabolism to this acyl chloride. And this acyl chloride can undergo two fates. It will either react with water to form that acid, or it can react with protein and generate what are called as haptens, which are recognized by your immune system as foreign proteins, and your body starts making antibodies against your own proteins. If that has happened in your case, then if you are not careful and you take halothane again, you will undergo an anaphylactic reaction. You might die even before the surgery. Okay. But the interesting story is there are other anesthetics also which are similar, isoflurane and desflurane, and all of them have the same potential. Okay. And here's the interesting story. All of you have refrigerators at home, no? What is it that is used to cause cooling in a refrigerator? They put a little gas. What is that? Su? Chlorofluorocarbon. If your refrigerator still has chlorofluorocarbon, no, you are using an illegal refrigerator. Those refrigerators are no longer sold. If you look carefully at your refrigerator now, no, they don't have CFC. They have HCFC, hydrochlorofluorocarbons. You know why they do that? Chlorofluorocarbons do not get metabolized. And when your refrigerator is thrown out in the junkyard, that gas escapes, it goes into the environment, it never gets metabolized, it goes up, collects in the atmosphere, and then the ozone which is present in the upper atmosphere and sunlight collectively work together to degrade that CFC. And because ozone is used up, over time there has been a hole in the ozone layer, as they say. So what the companies did, they said this is very unsafe, why don't we use HCFCs? And when you use HCFCs, see what happens? Hydrochlorofluorocarbon, it can get metabolized, convert to acid, and then it's very, very safe. Okay, so it's very interesting. Similar compounds are used as anesthetics. Similar compounds are also used as refrigerants nowadays to make it safe. But it is all based on kind of metabolism. Okay, here is another example. This is an aromatic amine. Okay, and where do you get aromatic amines? Sometime in March, Holi aata hai na, Holi. Holi, sabko pasand hai Holi. And what do? Just one day before that, go out and get colors. Huh? Huh? Who? Color. Holi dance who karo? Main thing is dancing and colors, no? So अपन क्या करते हैं? उधर जाते and you can buy two types of colors. One, which are very costly and safe. And there are other colors which are stole, ऐसा. 50 पैसे में इतना. Okay? And you know what these colors are? They are all waste from dye industry. And they are rich in these type of compounds, aromatic amines. You use those colors and put it on your skin will do metabolism to generate this hydroxide, then this acetyl. It is very, very unstable and will generate this reactive nitrinium ion which can cause carcinogenic DNA adducts and cause skin cancer. All because of metabolism. The aromatic amine itself is very safe till it is metabolized. Okay, so tomorrow, next year when you play Holi, no, buy that दूसरा वाला color, वो कोडाक का या कोरेस का ना, जो 25 रुपया का है और उसमें आटा है. That is much safer than those cheap colors that you get. But the problem is the cheap colors are nice colors. They really give good color. These other fellows are pastel colors. वो ऐसा काला, लाल, dark blue होना चाहिए. But all of these are rich in aromatic amines and they can potentially cause cancer if you are not careful. Here is another example, tolbutamide. Tolbutamide is metabolized to this sulfonamide and this very interesting compound called an isocyanate. Okay, and this isocyanate is the same isocyanate which is a variant of methyl isocyanate which was in the Bhopal gas tragedy. What does that do? It reacts with proteins and DNA and again can cause cancer. So see, tolbutamide itself is fine, but the minute you do metabolism and you generate this isocyanate, all the problems begin. So metabolism can make mistakes. Okay. Then here are the other very interesting fellows, what are called as quinones, quinoneamines, etc. And your paracetamol, which is supposed to be very, very safe, generates this type of imine, okay, what is called as paraquinoneamine. So here is acetaminophen. Normally you will get sulfate and glucuronide, but if you are not careful, you can get this iminoquinone, and iminoquinone can react with DNA and can cause our proteins and cause hepatotoxicity. At higher doses, it is very, very dangerous. That's why nowadays if you look, paracetamol dosage has been changed. In children, what used to be like 200 milligrams, they have brought it down to close to less than 100 milligrams. And even in adults, they say paracetamol doses should be not taken very carefully. However, in India, we use Dolo 650, okay, as if वो chocolate है, okay. एक नहीं लो, दो लो, that's why they call Dolo. But be very careful. Dolo is 650 milligram acetaminophen is not very good for you, okay. So be very careful and don't take it like chocolate.
Yeah, a lot of people drink alcohol and the next day they have an hangover and they don't take Dolo. Dolo is CYP1A2.
Yeah, same enzyme.
It's the same enzyme metabolizes alcohol and paracetamol. The problem is CYP1A2 gets induced by alcohol.
And you produce more of 2 even. Okay. And here is something even more interesting. Lot of people like to eat that biryani and all, no? Tandoori chicken, tandoor mein, that smoke which is present, no, on the meats, it is very rich in benzopyrines. And benzopyrines, if you are not careful, are also metabolized to something which can potentially react with DNA, again through metabolism. Okay, so you have to be very, very careful. What I am saying is not everybody who eats tandoori will get cancer, because remember we have repair systems also. Okay, but if you are genetically predisposed, then there is a chance that a few times you eat biryani, you might come down with cancer. So metabolism, which is good for you, can also create problems. Okay, and here is another very interesting compound, especially for somebody in Gujarat. This is aflatoxin, and every time somebody comes to Gujarat, what do? Baruch, Singdana, भर के लेके जाते हैं. But if you are not careful and these peanuts are infected with a fungus, they will contain what are called as aflatoxins. And aflatoxins are very, very dangerous liver toxicants. And that is because again they are metabolized to this epoxide, which is very electrophilic and can react with your DNA. Okay. So now you are seeing how important toxicology is. Okay. Because this system which is supposed to protect you can also create potential issues. Okay, so this is metabolism based toxicity, not overt toxicity. There are other chemicals which are toxic as is without doing any metabolism, but sometimes metabolism can also cause problems. Okay, so what companies have been doing, and if you notice in all the cases many of the first steps are done by P450s or cytochrome P450s. So pharmaceutical companies said P450s are potential problems, no? So why don't we make drugs which are not metabolized by P450? And you know how they do it? It's very simple. Let us say we look at naphthalene. Naphthalene is purely metabolized by P450. If I want to shift metabolism, no, I introduce some nitrogens and I generate this quinazoline, and quinazoline is metabolized both by P450 and xanthine oxidase. See the difference. P450 uses oxine, xanthine oxidase uses hydroxide. So in this thing, this ring is metabolized by P450 while this ring is metabolized by xanthine oxidase. Then I put more nitrogens and I generate pteridine. Now there are no sites which are metabolized by P450, everything is metabolized by xanthine oxidase. So I think I have sorted the problem, no? But the problem is we understand P450 very, very well, but we don't understand XOAO that well. So by making those compounds, we have created another problem. Now an enzyme which you really don't know what it's going to do and how it behaves is the main player now, and therefore from the frying pan to the fire. Okay, so as of today we have companies making both the type of drugs. Some people are comfortable still with P450. Somebody have said I am going to go away from P450, and they have created a whole new set of problems because these new enzymes, xanthine oxidase and aldehyde oxidase, have started to play a major role. So a few years ago, most of the drug metabolism used to be done using systems to study P450 reactions, but as of today people do routinely P450 as well as non-P450. And we'll stop here for the day. Okay? So I just thought I'll give you a feel for it, what is toxicology and what is drug metabolism. My main talk was supposed to be after this, but since we are running late and we are trying to catch up, I thought I'll educate the new students who are probably hearing about this for the first time. And hopefully you have taken home something new which you didn't know, but which is happening around you all the time. So first year, समझी गए कि नहीं? बस. Thank you.
Metabolism and the different enzymes for the same. Thank you so much, sir. And with the interest of the time, we'll take up the question answer session at the end of the second talk also. So now I'm inviting our second speaker for the particular session, Dr. Poonam Giri, General Manager, Zydus Life Sciences, Ahmedabad, India. Dr. Giri is PhD in chemistry and has over 25 years of experience in a leading cross-functional team in cross-cultural environment in the field of new drug discovery and developmental research. She has published more than 37 articles in the reputed and peer journals. Her experience is spread across multiple pharma companies and CROs, including Cadila Pharmaceuticals, Jubilant, Zydus Life Sciences, where she worked on NCE for ADME, PKPD, PI, PKKD values and all. Dr. Poonam has a lead on DMPK and contributed to more than 30 non-clinical programs in the various therapeutic areas such as metabolic disorder, pain, inflammation, CNS, oncology, and many more. She has created the drug discovery and the development process for 2 newly marketed NCE, that is Sezagitajol and Deciduate itself. And she has delivered many of the presentations and the talk at the various scientific and clinical forum. So with this short, brief introduction about ma'am, I would like to invite ma'am for delivering that expert talk. Please come, ma'am. Thank you.
So good afternoon, everyone. Thanks for being present here after the lunch. So today we are going to discuss one of the most critical. This is working, no? Keep it. So today we are going to discuss one of the most critical challenge in the drug discovery and development, that is the DILI, drug-induced liver injury. So before we deep dive into the content mitigation strategy, let's have the overlook what the DILI. So we will discuss about the mechanism, risk assessment tools, de-risking strategies, regulatory perspectives and case studies to wrap up and talk about the future trends. So drug-induced liver injury refers to the liver damage that occurs because of the exposure of pharmaceutical agent. It encompasses a spectrum of liver injury ranging from the mild liver enzyme elevation to severe liver failure. And if you talk about the scope, it manifests as a hepatocellular injury, cholestatic injury, or a combination of both, leading to various clinical presentation and outcomes. The incidence rate of the DILI is 1 in 10,000 or 1 in million exposure, but that may differ very significantly, depends on the drug class and population. So if you talk about the statistics, so 10 to 20% of the acute liver failure cases are responsible for the drug withdrawal from the market, and the different drugs which are in the market which may cause the DILI are the NSAIDs like acetaminophen and diclofenac, antibiotics such as amoxicillin, cloranate, isoniazid, fluofloxacin, anti-seizure medicines like phenytoin and valproic acid. and some herbal supplements that surprise us like kahwa and green tea extract may also cause delay. So mechanism of delay, it can cause from the direct hepatocyte effect of the drug or idiosyncratic reaction or immune-mediated damage. Factors such as metabolism, reactive metabolite, intermediates, and immune response contribute to the complexity of the delay. Histological examination of the liver biopsies may reveal the necrosis, cholestasis, steatosis, and fibrosis depending on the type of the delay. Symptoms include the fatigue, nausea, jaundice, vomiting, abdominal pain, and dark urine. And elevated liver enzyme like ALT, AST, and ALP and bilirubin level in the plasma is the indication of the liver injury. So based on this, the clinical score, like there are the three classes of the delay, that is the mild, moderate, and severe based on the symptoms. So what the consequence of the delay? Why we are here talking about the delays? It depends on the it may have introduce the high attrition rate in the drug discovery and development, increased cost of the discovery and development, extend timeline from the discovery to market launch, and potential market withdrawal. Approximately 30% of the drug withdrawal are attributed due to liver toxicity. Patient with the delay may face serious complications including the transplantation and acute liver failure and even death of the patient. So healthcare provider must be vigilant and recognizing the sign of the delay as early as possible. In the US FDA, 13% of acute liver failure is because of the delay. And because of all this seriousness, regulatory agencies are also monitoring very stringently the safety of molecules in the clinical development and post-marketing associated with the delay risk. So as already I discussed, like US FDA and EMA, they are monitoring the delay symptoms. They have already have the guidance for the industry, and based on that, companies are following how their molecule is getting discovered and developed in the clinical trials. So based on the risk-benefit ratio, if some signals are there, so decisions should be taken very genuinely, like this molecule may go ahead in the clinical trial or not, because failure in the late clinical trial or in the market may give the very huge financial loss, reputation loss of the company, and patient problem or compensation. For example, troglitazone, one of the antibiotic drug, when it withdraw from the market, it cost about $1 billion to the company. This is one pie chart. This talk about different drugs are there in the market and which class of the drugs is causing the delay most. Like NSAID, they are around 39% of the contribution from NSAID, 20% from the antibiotic, 9% from the immunosuppressant, 7% from the antiplatelet agent, 4% from the antibiotic drug, and 21% from the other class of the drugs. The risk factor and incidence which involved in the delay are the two types, drug-related and patient-related. In drug-related, what is the daily dose? It is very high or less than 100 mg. For the lipophilicity of the compound, is the drug is forming any reactive metabolite or any drug-drug interaction, because in today's scenario, polypharmacy is a very common thing. Not a single pill will work. So the patient is taking so many medicine at the same time. So what is the drug interaction potential of a drug in that scenario? And hepatobiliary transport inhibition. Herbal dietary supplements, we think like it's the safest one. We are consuming so many herbal and dietary supplements, but they may also cause the hepatocyte toxicity because of the erroneous plant substitution or some exogenous contamination, alteration while harvesting or processing. If we talk about the factors like host-related factors, so non-genetic and genetic, in non-genetic factors like age, sex, alcohol, pregnancy states, or smoking, comorbidities, all these things already before me, all the speakers had taken care of very widely, so I don't want to throw much light on this. In the genetic, like metabolism enzyme, their abundance is very different. HLA polymorphism, drug transporters variability, and mitochondrial DNA mutations, these are the risk factors of the DILI. There are two types of the DILI, that is the intrinsic DILI and idiosyncratic DILI. Intrinsic DILI is the dose dependent. They typically occurs when the drug or its metabolite reach the toxic level in the liver. It usually has a short latency period. It means like immediate after the exposure of the high quantity or amount of the drug, the DILI symptoms shown. For example, acetaminophen, phenophen, just Dr. Iyer has talked about that, like one of the most common example. Methotrexate, one of the chemotherapy agent which lead cumulative liver damage, often detected by the elevated liver enzyme. Idiosyncratic is the non-dependent. They occur at the therapeutic dose and may found in the very subset of the patient. Examples are the amoxicillin and cloalinate and isoniazid for the idiosyncratic DILI. So differences is here. For intrinsic, it is predictable. Idiosyncratic, it is non-predictable. Dosage for the intrinsic is the super therapeutic. Because of the high dose exposure, this may occur. And idiosyncratic, on the therapeutic dose, the symptoms of the DILI appear. Latency period is very short for the intrinsic DILI, while for the idiosyncratic, it is long and variable. The risk factor is high dose. For the idiosyncratic, it is the patient specific. And mechanism is the intrinsic hepatotoxicity, while for the idiosyncratic, it is very complex, very sophisticated understanding and investigation required to understand the mechanism of the idiosyncratic DILI. So immunological and metabolic is the region, mechanistic region for the idiosyncratic DILI. So while liver is the only soft target of the drug-induced toxicity, so liver is the primary organ where all the drug metabolizing activity is happening. It has the all the combination of the liver enzymes like superfamily cytochrome P450, then conjugative metabolizing enzyme like gluconide, glutathione, then non-CYP enzymes. All the area of the drug metabolizing enzyme are there, and drugs are getting metabolized there, breaking down into the metabolites, which is much more polar and getting clear from the body. Dr. Iyer already mentioned very detailed, like there are the two kinds of the drug metabolizing reaction, phase 1 and phase 2. So I will talk about what is the different mechanism of the DILI, like mitochondrial impairment. Mitochondria is understood as the powerhouse of the cell. Because of the stress, cell death occurred there. Inhibition of biliary efflux. Liver is forming the bile, and with the help of the bile B-cell transporters, it is throwing bile into the bile duct, which release in the gut and performing the digestion activity. If biliary B-cell inhibition happen, the drug accumulated in the liver, causing the inflammation and death of the liver cells, and ultimately DILI. Similarly, lysozyme impairment, reactive metabolite, which will cause chemical stress, oxidative stress, protein modification, endoplasmic reticulum stress, and immune system. So these are the different factors which may cause the DILI in human. And in the right hand side, there are different clinical presentation of the DILI in the human patient population. So what the challenge is in the prediction of the DILI? DILI is very complex, asymptomatic, very limited models are available for the prediction of the DILI. In the patient, huge variability is there, like comorbidities are there, genetic differences are there, polypharmacy is there, age and sex are there. And the translation of the model which are present to the clinic is very poor. So early identification of drug-induced liver injury, it includes the in silico models. So we have the DILI-SIM, we have in industry the ADMET metasite. By putting the structure or putting the in vitro in vivo data, we will have the prediction of the DILI liability of that molecule. We have the in vitro tool where 2D cell culture using hepatocyte, 3D cell culture, liver on the chip, organoids. So many different models are there which can be used to predict the DILI possibility in the clinic. Traditional in vivo animal models are there, like humanized mice are there, knockout mouse are there. So preclinically we can use these animal models and develop the data, interpret that data, and can predict the DILI possibility in the clinic. We can check the presence of the bilirubin or bile salt in the plasma. We can check the ALT, AST elevation in the liver. So those are the some indications which can use for the DILI prediction using the animal model. Then as I told you, like organ on a chip is the newer emerging technology. Biomarker discovery. So ALT, AST are considered as a biomarker for the DILI. But some newer biomarkers are also there, like microRNA 122. So these are more sensitive, can be detected at much earlier when the detection of ALT, AST happens. So that can also be utilized for the identification of the DILI in the patient population or in the preclinical setup. And multi-omics approach are also getting now the attraction of the scientific population, like proteomics, genomics, metabolomics. These are the things. Cumulative analysis of this data can give us the indication like DILI may be possible while developing the drug further. So this is the sum of the models we have talked about, where by iPSC, hepatocyte-like cells developed and can be formed as a organoids. Similarly, for the precision medicine, a host cell can be taken and can be cultured to get the personalized medicine. And in vitro models like co-culture and mixed culture, in vivo animal model can be developed, but still there is a need to develop some more model to predict confidently DILI possibility in clinical trials. So how to risk mitigation can be attempted in non-clinical development. So early identification and screening methods includes the in vitro testing, in silico predictive model, and QSAR. Medicinal chemists can take also the SAR analysis, can modify the chemical scaffold, make the much safer molecule. They can optimize the pharmacophore. Prodrug strategy can be also followed. They can use the soft drug approach to avoid the reactive metabolite formation, and this cycle can be repeatedly employed to get the safer molecule. Nowadays, AI/ML is also catching attention. In each and every area, AI/ML is doing good job. But again, here limitation is like whatever data quality we are feeding in the AI/ML model development, that should be of the quality data. As much as quality data we will feed, we will have the good model, validate that model, and implement that for the prediction of the severity of the DILI and getting the information, and which will help in designing our clinical trial and having the good faith of a molecule. So as before me, many speakers had talked about the reactive metabolite. So reactive metabolite burden. So many molecules get metabolized in the liver, they forming a transient metabolite that is electrophilic in nature, that is very short span, having a very short lifespan, and they are forming the adduct with the protein present in the liver. In that way, they are either stopping the function of that protein and producing some toxicity, either the cell death or some kind of the malfunction of the liver. So this reactive metabolite identification must be done. In simple metabolite identification study, it's difficult to catch such reactive metabolite. So we have the approach which all company follow, like trapping study. So we incubate compound or drug with the trapping agent in the presence and absence of the cofactor NADPH, and if there is the identification of the adduct of that drug, which indicate like there is the reactive metabolite formation. Similarly, when we move ahead toward the more mature program in the discovery and clinical development, initial clinical development, we can do the covalent binding study in vitro, in vivo, with the help of the C14C radio-labeled compound or tritiated compound. If our drug is having the carboxylic acid in their group, which is required for some of the pharmacological activity, so such carboxylic acid can conjugate with a gluconide, making it acyl gluconide that is also reactive in nature and which may cause the toxicity and liver injury. So this is the simple protocol and chromatogram of the detection of reactive metabolite by the trapping agent. So here the nucleophiles glutathione, cysteine and semicarbazide is in the practice. We incubate our drug. After the completion of the reaction, we quench to precipitate protein and cell debris and supernatant injected on the LCMS-MS or HRMS. Presence of the adduct indicate the reactive metabolite formation. So in the upper, there is no NADPH, it means metabolic reaction is not happening there. You can see the simple parent peak is there. In the lower chromatogram, there are the three metabolite peak, M1, M2, M3. M3 formed by the hydration and glutathione, and M1, M2 and M3 formed by the glutathione adduct of the phase 1 metabolites. As I talked about earlier, like some of the molecules have the carboxylic acid in their structure. Such drug can form the acyl gluconide or acetyl coenzyme thioester. Both reactive species have the potential to modify proteins. Acyl gluconide can undergo direct addition with a protein nucleophile by displacement of glucuronic acid, that is called as the transacylation, or can undergo rearrangement by exposing the aldehyde moiety, and which can subsequently condense on the protein NH2 sites, which is called as the glycation. So there is the chemical stability method or assay which can identify like this acyl gluconide is reactive in nature or not. So for this, acyl gluconide is incubated in potassium phosphate buffer, human serum, albumin solution or human plasma for hours, 6 hours, 10 hours like that. And if the half-life is less than 3.6 hours, which indicate like acyl gluconide is the reactive in nature, which may cause the liver injury, while we will go ahead with this molecule. One alternative approach is the use of the 35 sulfur-labeled cysteine also for trapping much strong or much hard electrophiles. So this is one of the industry approach. My voice is clear? Going? Yeah. This is one of the industry approach. Actually, every company has the different approach to have the daily mitigation. But this is one of the simple approach where this is the mitigation factors like dose is low or not. If it is less than 100 mg, life-threatening indication. If drug is developing for the life-threatening indication, or it is first in class, or here the topical administration of drug is happening. So these are the factors taking into consideration. And risk-benefit ratio. Any company can bypass the initial reactive metabolite formation and can jump to evaluation of the reactive metabolite burden in the clinical candidate selection stage. So in silico prediction and in vitro reactive metabolite screening. So these assays if we perform and we found like metabolism dependent inhibition is there or GSH product identified, then we investigate our scaffold by SAR. It's possible to make the safer molecule. If that is possible, then we repeat the cycle. If that is not safer, it means there is the MDI, there is the GSH attack, and there is no chance to modify the structure. Then what we do here the investigation. What is the cause of the reactive metabolite formation? What is the cause of the MDI? Again here, do the risk assessment. Like is there specific difference in mouse and rat? We are getting the high exposure. In human, detected exposure is low. Kind of the things, there is the differences. So those are the things. So what we do here? We do here the allometry, human PK prediction and simulation to have the predicted dose. After getting the predicted dose, if it is less than 100 mg per day, then we consider with the development with the caution. If it is more than 100%, then we terminate the that compound and will start the again designing and synthesis of the molecule. Similarly for the BSEP, as I told you, like BSEP is the bile salt export pump. Inhibition of this transporter may cause the accumulation of the bile in the liver and inflammation and toxicity. So we perform the BSEP vesicle assay in the early discovery. If the IC50 value is equal or more than less than 25 micromolar, then what we do the predicted human steady state concentration and BSEP ratio. If it is more than 0.1, then we further investigate and validate this finding with the in vivo animal model, like rat dosed with the drug and bile salt check in the plasma. If bile salt is present in the plasma of the rat, then we take the decision based on the outcomes. If if the ratio is less than 0.1, then there is a low BSEP risk and low DILI risk. We can consider it for the further development. This is a depiction of the AI/ML role in the DILI mitigation. So as good as data set input will be provided through the in vitro, in vivo, clinical trial, post-marketing, real-time data. So if the sources or data input is good, we can develop a good model, validate that model with the marketed drug, and the interpretation of the outcome is important to take the decision while this molecule will be taken further for the development or not. So we have taken here some case studies. Where we work on the SAR, like this is the BMS molecule. In the voluntary terminated from the phase 2 clinical trials. If you look at the data, the BSEP IC50 is 4.8 micromolar, MRP3 and MRP4 IC50 is 6.2, 7.4 micromolar, and maximum daily dose is 600 mg BID. As I talk about, like if it is dose is less than 100 mg per day, it is safer and may not cause the DILI in the human patient. But here 600 mg is the dose. So after the withdrawal, chemistry worked on the SAR optimization. They made the second compound, this one. Here the C log P is getting down. Here the MDD is getting down from 600 to 60 mg. If you look at the BSEP IC50 value, MRP3, MRP4 values, it is more than 100 micromolar, 47 micromolar and 100 micromolar respectively. and this molecule is not have any hepatobiliary toxicity. So low risk of DILI require preferably low dose and balanced lipophilicity. This is the second example where J&J molecule. So the J&J molecule like 972, that is the third structure, this one, which is the derived from the this one. Here they remove 1,3-thiazine from here and make the molecule number 5. This molecule, when performed the trapping study in presence of potassium cyanide, it shows the positive result. It means it is forming the reactive metabolite. So they changed this structure and made this one is structure 3, and this is having no reactive metabolite formation and no DILI risk formation of any molecule. We should go back, we should investigate which structure is responsible for the reactive metabolite, work on that and perform the SAR and change the structure. So third case study is the benzobromazone. It is launched in 1970s in the Asia, South America and Europe for the gout. But in the clinical trial, it was having very rare, only 0.1% of the patient has shown the elevated liver enzyme ALT/AST. So it was considered as a safe molecule. But later on, there was found in the post-marketing serious adverse liver reaction, and Sanofi has voluntarily withdrawn this molecule from the market. Still it is present in some of the countries, but in the United States it never got approved. So here if you see, like BBR, the short form is in the presence of CYP2C9, it is forming the 6-hydroxy-BBR, which again getting metabolized in the 5,6-hydroxy-BBR and the reactive intermediate quinoline metabolite, which is the region for the liver toxicity. In the troglitazone case, this is the approved in the 1990 for the type 2 diabetes. In March 2000, after 3 years of the market launch, it got withdrawal because severe cases, 100 cases reported in the patient of the hepatotoxicity. So what happened here? Though there is a sign of the liver toxicity, mild liver toxicity in the preclinical and clinical, but this drug got approval. But later on the patient population, very severe liver toxicity observed, and drug is observed after the launching of the 3 years. So here the lesson learned is that the importance of the continuous post-marketing surveillance and need for the rigorous monitoring of the liver function during trials. It also pushed regulators to adopt a stricter safety threshold for the liver enzyme elevation in the clinical trials. In another example, that is the trovafloxacin, that is one of the antibiotic. In 1999, trovafloxacin was severely restricted due to case of the severe liver damage. So FDA imposed severe restriction of the trovafloxacin and limiting its use to life-threatening infection and only when there is no alternative antibiotics available. Still it is available in some of the market, but the lesson learned from here is that there needed the long-term safety trials. It is antibiotic, its exposure needed vary for few days, week and so more. So it's not like if the drug is for the short duration of the treatment, there is no need to long-term safety assessment. So long-term safety assessment needed for it. And if there is a black box warning, then that should be clearly communicated with the practitioner. So this is the last case study where anafazolone It is one of the antidepressant withdrawn in 2004 from the US market. And look here, the structure. It is forming multiple reactive metabolites. But in the normal metabolite identification studies, it is difficult to identify. So after getting the withdrawal from the market, retrospectively the studies have been happened, and by posing the alternative glutathione trapping and cysteine trapping assay, the multiple reactive metabolite identified in the case. So what lesson learned in this case, like the monitoring of adverse effect is important, and ensuring that potential hypotoxicity is clearly communicated to healthcare provider and patients through warning and labeling. So in summary, because we are in the industry, we know like each and every company have their own strategy to deal with the liver toxicity. So here I just summarize the approach of the different industry. Like one of the association is there, European Federation of Pharmaceutical Industries and Association. They have proposed 3-tiered approach for the identification of the dealing with the data and interpretation. GSK, they have the multi-assay approach, and they consider into account the major CYP-MDI. They have considered 1A2, 2C8, 2C19, 2D6, 3A4 isoforms, metabolism-dependent inhibition, glutathione adduct trapping assay, 14C radio-labeled drug protein covalent binding, along with the predicted human steady-state human exposure. Roche, they have studied 81 drug data, and based on that they come with the approach where they consider CYP3A4 TDI, GSS trapping, human BCEP inhibition, mitochondrial toxicity and cytotoxicity in the hepatocyte and fibroblast. Similarly, by study of the 32 drug, AstraZeneca, they have the approach of the steady toxicity in the thalate, CYP3A4 transcripted thalate cells, mitochondrial toxicity, human BCEP inhibition, MRP2 inhibition, and covalent binding of the reactive metabolites, along with the again steady-state human plasma concentration predicted based on the efficacy study and preclinical PK data. Pfizer, they have studied 200 compounds, and they come up with the HRM approach where rules of the 2SA and partition model, they taking into consideration dose, ionization state, lipophilicity, and fraction carbon sp3 hybridization, mitochondrial toxicity, cytotoxicity, and human BCEP inhibition. So in summary, I can say the DILI is so complex, it's difficult to understand, difficult to predict. So there are so many factors, environmental, genetic, metabolism, bile. So they may cause the DILI. So it's difficult to understand, difficult to predict, but some sort of the precautions they can take in the preclinical and clinical. Like if you see here the correlation, like predicted human dose can play with the reactive metabolite formation. So as low reactive metabolite and as low drug, you will have the safer molecule from the DILI perspective. As you go beyond the right hand side or go beyond up, the risk of DILI will be increased. So taking into the approach of the different pharmaceutical company and practices, we come to the conclusion like if we want to avoid the DILI, the dose should be less than 100 mg per day, lipophilicity should be less than 3, the sp3 hybridizing carbon should be higher, and then we should be avoid the structure again. Regulatory agencies, US FDA and EMA, they have put their effort to giving guidance to the industry to monitor the hepatotoxicity in the development. So US FDA has focused on the early identification of potential hepatotoxicity during drug development as well as the inclusion of specific safety measures during clinical trials, while EMA emphasized risk evaluation, classification of hepatotoxicity and measures to mitigate liver injury risk based on the non-clinical and clinical findings. So thank you.
So thank you so much, ma'am, for giving a detailed insight about Delhi and related case studies. Thank you so much, ma'am. Now the session is open for the discussion and the question answers.
So there are many little rocks with Grover, so I don't want him to carry any of it back home. So please feel free to ask any questions. So maybe I think I'll have to, I will learn maximum of them, I guess. So great talk. Poonam. Okay, yeah, please.
Regulatory acceptance of in vitro model for in toxicity. Any models?
Yeah. Regulatory agencies, whatever in vitro data we generate to predict the DILI properties, that is acceptable to regulatory agencies. It's not like that depends. You have validated your assay, you have put there the positive and negative control, and all your quality control data are matching with the literature references. If that is there, regulatory will accept your data and you can use for the information in the clinical design.
Thank you, ma'am.
Yeah, any other question? Yes, please.
कॉज करती है हेपेटोटॉक्सिसिटी, तो उसको कितने परसेंट ड्रग को बैक किया गया है मार्केट से, क्योंकि जो टॉक्सिसिटी है वो तो इंड्यूस हो ही रही है और वो नोन है, फिर भी जस्ट बिकॉज ऑफ हेपेटोटॉक्सिसिटी वो ड्रग्स मार्केट से नहीं आ रहे और लोग इतने ले भी रहे हैं, जरा सा इंफ्लेमेशन हुआ तुरंत NSAID ले ली.
I agree with you. Without prescription, we used to buy medicine. So there is always in label claim it is mentioned like higher dose may cause toxicity. So in the label it is mentioned it's responsibility of the patient and doctors to educate patient like higher dose may cause the toxicity. Withdrawal as such at the therapeutic dose, withdrawal is not too much, but this is the high dose consequences which may cause the delay. So high dose should be avoided. That is already mentioned in every drug. If you read there in the label, it is mentioned there. So it's our own responsibility to have the safe practice, purchasing drug, consuming drug.
केवल पता होना चाहिए कि विदाउट प्रिस्क्रिप्शन नहीं लेनी चाहिए ना, जो ड्रग मिल रही है तो कोई
In paracetamol 3 mg is considered as a beyond 3 mg there is a liver toxicity.
Yeah.
$650 we used to take it every 5 to 6 hours. So maximum dose we consume maximum this permissible dose.
Krishna, it was a wonderful presentation. I became a student in front of you. Probably I'll have to take more drug metabolism courses from you in the future. Very nicely presented. The question is, it is too complicated. At the end of the day, it's a case by case. You can never predict anything. And I mean, that's my opinion for the last 40 years being in the industry. I think that prediction is not possible, but as I said, we are moving into the human systems. But we are slow to develop them. And with the war against the animals, saying that animals are not predictive, how would you approach this prediction thing for a human thing that happens post-marketing or at a phase 2 trial? I mean, which is already you've spent a lot of money in the process.
Yeah, see, my approach is we know that animal models and animal systems or even human in vitro systems will not allow you to get complete prediction of what is going to happen in the clinic. There are too many variables. But that doesn't mean you shouldn't do those studies. Okay, the way I look at it is if you spot something in the in vitro system or in the human in vitro animal, then at least those compounds can be thrown off immediately. Okay, you take that risk of a false positive, but that saves you time a little later. Okay, there are other compounds which might appear to be safe in an animal model or a human in vitro model, but they turn out to be toxic later. You go with that risk. Okay, but that is an acceptable risk. Okay, the main thing is you can discard compounds which are really, really bad. So you still need to do those things so that you don't take bad fellows up and then shout at a little later. So you still need those systems for you to weed out things which are bad. And that is where their role is. Not to make sure the prediction is 100%, but to help you remove things which are potentially problematic. Okay? And that's where I come from. For me, they are not useless systems. It is just that you are asking too much from the system to give you 100% predictability. We are a complicated system. We have kind of cut it down, bought liver microsomes, hepatocytes, things on a chip, but they are not the real thing. So they'll never predict the real thing. So what you are trying to do is get information so that you don't end up taking too much risks when you go into the clinic. And that helps you bring down the costs of drug development.
Yeah.
So they have a place according to.
Regarding the delay, back in 1980s and 1990s, we used to see this with environmental pollutants quite a lot. There were labs most of it is considered immunotoxicity, like what is the carbon tetrachloride, halothane. They're all considered to be immunotoxins, not considered real hepatotoxins as is. So the problem came is that these guys, there were several laboratories, academic laboratories, went into fishing expedition, trying to hydrolyze the proteins and see what is bound covalently to the protein, they did all the proteomic analysis in those days. They couldn't figure it out. Now we are shifting the gear to the drugs. We are into the same board. Basically, a delay is something, if I am a patient with some problem in myself, a genetic problem, you can never predict it because I'm an isolated case. So these are the things that are happening in the, both of you can answer this question.
So for the audience now, I'm going to close it. Since we ended with talking about toxic metabolites and problems to the liver, what I didn't mention in my talk is almost all of your drug metabolism, 90% is done by the liver. And therefore, if toxicity occurs at the level of the liver, you have much more problems than what you start with. And therefore, if you look at our culture, if you really, really like somebody, you would say either of one or two things. तुम मेरे जिगर के टुकड़े हो या तुम मेरे कलेजे के टुकड़े हो. So you know how important the liver is. That's why Delhi is so important.
Thank you.
I agree. This liver, because this is the main organ, and toxicity, it's something which may cause the mortality or even much things there. If you talk about the delay in the liver, so there are the comorbidity conditions. Today, like 40-45 years of the age, we generally face like all the diabetes, cardiovascular disease. So 10 to 15 drugs in a day, generally people are taking. Each and every have the different interaction. They can inhibit or by self, or they can inhibit the enzymes. So either their exposure will increase or their concomitant medications exposure will increase. They may have some pre-existing like cirrhosis or hepatitis, those conditions also. DILI may also occur like if the elderly people are there, their liver function impaired. We generally predict by 1 or 2 experiment, like what will be the implication of this drug in the elderly person if the liver impairment is there, but not exactly what, because every individual is different at some or different level. So those are the things. We are taking the help from the software, but again, you know, like software prediction is how much reliable. So we need to have in our hand the experimental data, and because of all this complexity, studying and having the close monitoring on the daily incidences is important, and I think we need to take care of that while developing the any molecule as a drug discoverer scientist, or when we going ahead with the development of that molecule. It's our moral responsibility not only look for the business but also look for the patient population, because this is a very novel cause. We are developing a drug for the patient population, human being, from us only.
Okay, thank you so much, ma'am. Now I would like to request Dr. Senthil to kindly present memento to Dr. Krishna. I would also request sir to please stay back and present memento to Dr. Giri. Thank you. Okay, so I am handing over to Dr. Deepak again. Okay, so now we are starting with our next session, the oral session. So for which I'll request the participant to please be attentive, and we'll start with Dr. Kashish. The presentation time is 5 minutes and the question answer round is for 2 minutes. So please stick with the time. Okay, so please note, after 5 minutes there will be a buzzer, and then in 1 minute you need to wrap up. Please stick with the time.
Yes.
Hello everyone, myself Kashish Patel, and I'm on first year M.Pharm Pharmacology in Nirma University itself. So I'll be starting with a question first. Can you recall any anti-aging drug approved by FDA? Can anyone say that? No? There are no anti-aging drugs approved by FDA. So it is concerning, because aging, as we know, that our grandparents' lifespan is probably higher than our parents, and talking about us, it will be lesser than our parents. So here we will be focusing on aging. So talking about aging, there are so many disorders like Alzheimer's, Parkinson, they are related with aging. So my project is investigating the anti-aging mechanism of AMLA using network pharmacology and molecular docking. So we'll skip on to that. So these all are the chemical constituent of AMLA. There are probably 27 constituent in AMLA, and like vitamins, polyphenols, gallic acid, amino acids, carbohydrates, flavonoids, etc. And we don't know which bioactives are responsible for anti-aging. So network pharmacology and docking approach will be help to identify which bioactives will be responsible for anti-aging. So I've used plenty of databases like PubMed, PubChem, BindingDB, DisGenet, and KegMapper. First, a selection of bioactives. I've selected the bioactives on the basis of pathways that are related to anti-agings. Then this is the PubMed software where we can fetch the 2D and 3D structure of particular bioactive. Identification of target. So the targets were identified on the basis of bioactive. These are the targets of chabulinic acid. I would took it as an example. So amyloid beta precursor and etc. etc. Further, this also shows the uniprot ID of particular protein and it and a particular gene related to that protein. Screening of receptor. Further screening of receptor was also on the basis of pathways, and I have used the KegMapper for that. These were the pathways related to that particular bioactive. So gene ID and collection. So this was probably be done with help of BindingDB database, from where we can fetch the gene disease association. So basically, summary of gene disease association will give us the disease that are related to that bioactives. Further, I have filtered the anti-aging related disease, which those who are connected to anti-aging. So those were the disease which I took: Alzheimer's, Parkinson, age-related neurodegenerations, degenerative disorders, arteriosclerosis, network construction. Then I constructed a network of AMLA. Those are the bioactives that are associated with AMLA. Those are the proteins that were associated with that particular bioactive. And those were the diseases that were connected with those proteins. Further, I've done the molecular docking using Autodoc Vena, Autodoc, and Pyrex software. Then these are the docking software. Discovery Studio is basically a visualization software for proteins. Pyrex, I've used mainly this software for molecular docking because it involves because it is a molecular docking tool, virtual screening tool, visualization tool, and it was a great software. Selection of receptors. So I have selected receptors on the basis of high number of disease associated related to anti-aging. So those were the potential receptors who are connected with aging. Those were the 4 protein. Selection of ligand were also based on the highest number of disease association. Those are the 8 bioactives are selected, and the results were.
No, I mean, you've got 1 minute to wind up. Just conclude in 1 minute. Yeah.
Okay. So the docking results were very good. -9 point in -8, -9.1, -9.2. So in conclusion, I have extracted the pathways like AMPK, mTOR, signaling pathway, SIRT1, which are related to anti-aging. Generally, metformin and rapamycin acts through this pathway, and they are connected with anti-aging. So, targeted intervention for the age-related disorders like Alzheimer and Parkinson provide insight into broader mechanism of aging. And further, we can also convert that bioactive to synthetic molecules further.
Yeah, any questions from the panel?
Are these softwares you bought them or open source or proprietary? What are they?
No, actually it was my BPharm project, so there weren't any resources, so I've used free softwares.
Free softwares only. Okay, fine. The other question is that, I mean, it's just a comment that in 1940s, 1950s, lifespan was only 45 to 55. Now it is average lifespan is about 75. So your grandparents didn't live too long. Okay, just want to correct you on that. Okay.
But research has said that there is a shortening of telomere, and which is leading to the...
yeah, but we are older now because we are living into 75, 85, our telomere will get shorter. Those guys didn't live to more than 55 average span. So that's what happens. Now, the antibiotics made a difference in life. With antibiotics, we've increased the lifespan to 75 now.
Okay, so if we are majorly focusing on metabolic disorders and chronic diseases. So
right. What I'm saying is aging has actually improved from 1950s to today. We have other problems today. Okay. Yeah.
Any treatment is required or directly also you upload into the Pyrex?
As I said, I filtered those bioactive. As we know that amla is an anti-aging drug. So we don't know which bioactives works as an anti-aging. So basically, we extracted the pathways, and based on the pathways, we predicted that those will be the bioactives which will be working on anti-aging.
Do you require to remove the water molecules and all these things before?
Yes.
That's what I wanted.
Yes.
So how would you approach proving these bioactives are really active for anti-aging? What is your approach would be in the future if you are given this project tomorrow? How would you do it?
Okay. So I don't know if they will work or not, but here further I'm taking my project towards the converting the herbal bioactive to synthetic material. So further I can study on that.
Okay.
I can say that.
Thank you.
Okay, so next is Akash Kumar.
Okay, good evening everyone. We have done a research on efficacy and safety assessment of probiotic preparation of Bacillus coagulans BCP 92 for treatment of diarrhea. Actually, this is a probiotic done by Pellucid company. We did a collaboration study and we did the safety testing and antidiarrheal activity testing. Okay. So probiotics are living microorganisms which benefits the for the health of human being. They are useful in different parameters like in bowel disease and in immunity, they help in improving them. So the variant we have chosen is bacillus coagulans. This bacillus coagulans has already been studied for increasing the digestive potential of human beings, and this bacillus coagulans bacteria has wide susceptibility of temperature and pH, so they can survive in gastric pH and temperatures, human body temperatures. So we were testing this for its safety and antidiarrheal activity. So objective of this study is first to do the in vitro study using Vero cell line, which is the MTT assay, and next will be your acute toxicity study using the OECD guideline 420, and next followed by your subacute toxicity studies using OECD guideline 407, and at last we will be doing the diarrheal study. First we did the in vitro MTT assay using Vero cell line, and the doses were ranged from, we did the dose ranging study for this bacillus coagulans, and we started from 60 to 0.5 nanomolar to 1000 nanomolar. We did a ranging study, and we found out that the cell viability is almost at 100%, so it is safer in cellular side. Next we did acute toxicity studies, in which we gave 2000 mg per kg bacillus coagulans for as a pilot study for 2 groups only, 6 animals we did. In that we checked for the survivability of the animals. In that acute toxicity studies, all the animals survived, so we carried out the next study, which is the subacute repeated dose toxicity study. In this we had actually we had 6 groups, like normal control, low dose group, medium dose group, high dose group, and recovery 2 groups we had. Then in that we measured different parameters, which means first we dosed it for repeated dose toxicity, 28 days we dosed the bacillus coagulans, then we started the parameters. We throughoutly monitored the food intake of the animals, which is gradually increasing as per the weeks increases. And next, the body weight of the animals. Body weight of the animals also gradually increased as weeks passed by, and there is no sudden drop of weight or anything in the while after the treatment of or during the course of the treatment of the animals. So next will be your urine analysis. After the 28 days treatment, we collected the urine of the animals and we checked the urine analysis. We did parameters like specific gravity, pH, glucose, creatinine, all the protein, and all the urine contents were within the range, safety range actually, normal control safety range. They didn't cross any limits or drop down. Next, hematological parameters. We collected blood and we checked the whole blood parameters, which is total WBC, RBC, clotting time, APTT, PTT. We checked, everything was similar to normal control, and we checked for the recovery group also. The recovery group is 28 days after, we will wait for 2 weeks, and we will check for the post-treatment damages and all. So that is recovery group. In that also there is no toxicity was found in or any adverse changes in the hematological parameters were seen. And biochemical parameters. Biochemical parameters also, everything was in normal range, and we took the organs out. We took the major organs out, which are the heart, lungs, liver and kidney. We weighed the organs, and the organ weights were not changed compared to normal control. Then we did the histopathology using the H&E staining, and all the liver, kidney and heart, they were all in normal. They don't have there was no damage shown in the slides. Next, antidiarrheal study was done. In the antidiarrheal study, castor oil was given, and the positive control was low pyramid, and our drug was given in low dose and high dose, which is 17 mg per kg and 34 mg per kg. And we checked the percentage inhibition of the diarrheal frequency by checking the weight of the feces. So this concludes that the bacillus coagulans which we used was safer and causes antidiarrheal effect. And these are the references which I used. Thank you.
Thank you, Akash.
Oh, it is on. Thanks for talking. I have a question, and I might have missed it. And then, when you're doing the low and high treatment, how is that normalized? What is a low and high dose to think of how they could be used in actual treatment?
Okay. Depending upon the weight of the person or age of the person, we can change it.
But so for the round as a low dose, how is that?
No. In this, we have just chosen one separate group for low dose and one separate group for high dose.
But what is a low and a high dose? How is it? What is actually units of a low and a high dose?
Actually, we used 2 billion colony forming unit, 2 billion CFU unit as a normal, and the dose were like 250 mg, 500 mg, and 1000 mg for the acute subacute toxicity studies. And for the diarrheal studies, we used 17 mg per kg and 34 mg per kg actually as low and high dose. Okay. We did a dose ranging study and we chose.
So my question to you is that, probiotics may not absorb into the systemic circulation. Yeah. They just form the probiotics are supposed to help toxins from the gut to prevent to go inside the body.
Yeah.
If the rats are already healthy, how would you anticipate probiotic is good or not? Or we didn't take care, of course, you took an anti-diarrheal whatever model, but the problem is you don't have any data that these bacteria or toxins are actually pharmacokinetic analysis you've not done.
Yeah.
So I'm not sure, is this just an effect that you're seeing it? Did you measure the liver toxicity enzymes like ALT, AST?
No.
It did not measure. So in the absence of the data, I cannot really conclude that it is actually, you've not done 100% tox study. 100% tox study, you need to have clinical pathology data. You have to have ALT, AST, GLT, all kinds of enzymes, plus the bilirubin, albumin, all these parameters need to be measured in
Actually, bilirubin, albumin and all we have done. Neurotoxicity studies and other things we didn't do.
I'm not worried about neurotoxicity.
Yeah. General toxicity, yeah.
General toxicity I'm worried about.
Yeah.
So, the conclusion is not warranted, but you need more data, more detailed investigation like a toxicology study I do in my own lab. We do. You don't even need to analyze the recovery group because you're not showing any data in the normal doses with control. You don't really need to spend time and analyze the recovery group for is there any toxicity or not, right? Recovery group, you're just leaving them for another 2 weeks.
For another 2 weeks and we
but what do you need the data when you're saying all these parameters are not changing? So my question is in the design of the studies a little bit.
Actually, if the company allows, we can do further. Actually.
Yeah, the company allows means that has to be a GLP study, not like this.
Yeah.
Okay? And it cannot do just a non-GLP study like this, and a lot of things need to be looked at. I don't know what regulations are there to accept these kind of studies for probiotics. Maybe that's acceptable for regulatory agencies. I'm not sure.
Yes.
Okay?
Okay. Thank you, sir. Thank you, Akash.
Castor oil for inducing diarrhea actually. Diarrhea inducing agent as castor oil we are given 0.5 ml for each animal.
Basically the castor itself is not a diarrheal agent, it is converted into the ricinoleic acid. This ricinoleic acid is an irritant and it
Yeah.
There may be inter-individual variation. Is this model is validated or?
It is Indian classical model. It is there actually.
In-house?
That's why I use the diagonal model is in mice and rats.
All right, thank you. Thanks.
Thank you, Akash. Next we have Bhavna Bora. We can interact later on.
नमक नहीं चाहिए मैं डायरेक्ट यहाँ पे साइड मोड पर डाल दो थोड़ा नीचे कर दो थोड़ा ऊपर करना आ नहीं रहा
हिल गया क्या देखो तो हटते भी
Good evening, everyone. Myself Bhavna Bora, a student of PhD research scholar from Nirma University Institute of Pharmacy. Today my poster presentation is on the topic unraveling the toxicity of one lotion from Bambusa arundinacea, integrating Protox to AI analysis with acute and subacute in vivo study. The content of the slide is introduction, rationale, aim and objective, material and method, result and conclusion. So let's have a description about the Vansh lotion. Vansh lotion is nothing but a tabashir or bamboo manna, a siliceous secretion collected from the internode of Bambusa arundinacea. It has been widely used in the Ayurvedic and traditional medicinal system across India and Southeast Asia for centuries. Vansh lotion is often employed as a natural remedy for a variety of ailments like respiratory and digestive disorders such as cough, bronchitis, asthma and dyspepsia. Its fine white powder is known for its cooling, demulcent and expectorant property. Rationale is, as it is a siliceous secretion traditionally used in Ayurvedic medicine for treating various ailments, despite its widespread use, there is no scientific data on the toxicity and the safety profile, raising a concern about its long-term usage. With the growing incorporation of Vansh lotion in modern herbal formulation, there is a precise need to scientifically evaluate its safety. This study combined its in silico prediction using the Protox2 AI tool and in vivo toxicity study to provide a comprehensive assessment. Aim was to evaluate the safety and the toxicity profile of Vansh lotion through a combination of in silico prediction using the Protox2 AI tool and in vivo acute and subacute toxicity study. Objective was to predict the toxicity using AI tool and to do acute toxicity using OECD guideline 420 and to perform subacute toxicity as per the OECD guideline 407. The Vansh lotion was initially identified with the help of the elements were identified with the help of the instrument called inductive coupled plasma optical emission spectroscopy, followed by a Protox2 analysis was done and then acute and subacute analysis was conducted. Here is the predicted element from ICP-OES where silicon was determined in the higher range, followed by aluminum, iron, magnesium, calcium, phosphorus and potassium. Thereafter a Protox2 tool was applied and here is the summary of the Protox2 tool. LD50 was identified with the with this a toxicity class was also predicted along with the molecular weight and log P value. Key toxicity target was also identified with the help of this tool. Then the in vivo study was carried out. Acute toxicity study was carried out with the help of guideline 420 and subacute toxicity was carried out with the help of guideline 407. In acute toxicity, five rats were in each group were taken, and the group were divided into two: control group and treatment group. Initially, for one animal was given a dose of 2000 mg per kg. Then it was observed for 48 hours, followed by, after 48 hours, 4 animals were taken, and then one single dose of 2000 mg per kg was administered and was then observed for 14 days for its mortality. Then the subacute toxicity was carried out, where it was the groups were divided into 3: satellite group, treatment group, and control group. Administration of the dose was done, observed for 14 days in case of mortality. At the end, they were sacrificed and the endpoint evaluation was done. Here is the result. No change in the body weight. Significant change was found in the body weight. This is the histo slide of acute toxicity. Histology of every vital organ was carried out, such as brain, heart, kidney, liver, lung, ovary, spleen, and stomach. No significant changes were seen. And this is the histopathology study of female red group of subacute range, where no difference was seen. No alteration in heart, brain, kidney, liver, lung, spleen, stomach, ovary was observed even after the treatment was given at the dose of 250, 500 and 1000 mg per kg. And same with the male group. Conclusion: at the end, the study concluded that Wunsch lotion, a siliceous secretion from Bambusa arundinacea, exhibit no mortality or significant treatment-related toxicity at the dose up to 1000 mg per kg. And subacute toxicity assessment, the Protox2 AI tool analysis confirmed the safety of its chemical constituent. Both in silico prediction and in vivo result indicated no observed adverse effect level greater than 2000 mg per kg, supporting the safe use of Wunsch lotion in traditional medicine. This finding underscores the potential of Wunsch lotion as safe therapeutic agent, warranting further exploration in its medical benefit. Thank you.
Thank you, Bhavna. Sir, the question is?
Interesting study, but what was the dose that people are taking Wunsch lotion normally when they purchase it outside?
2 gram is the maximum dose.
2 gram for a 70 kilogram human average, right?
Yes.
And you're here dosing 2000 milligram dose to the animal, right? Per kg or 2000 milligram as such?
Per kg.
Right. So, the 2000 milligram per kg means 200 gram rats. It's about at least 400 to 500 milligrams dose, if I can back calculate it. The one thing I don't see in all these experiments is that most herbal agents on a chronic usage cause liver toxicity. Here, there's no chronic data here. Okay, this is only acute and subacute single dose studies. You left for 14 years. Typically, if I look at all the other herbal agents, people take on a chronic basis. How do they take this? Do they take every day, or do they take the patients who were getting treated?
In human, it is like every day they can consume.
Every day they consume. Yes. Yeah. So you need to do a multi-dose study.
Yes, but in subacute was like a monthly 14-day dose, followed by the satellite group was observed for more 14 days.
No, what I'm saying is you have to dose every day for 14 days,
yes,
not 15 days,
yes.
And then look at the parameter.
Yes.
You're only looking at one dose and observed after 14 days.
No, that was an acute toxicity. That one single dose was given on first day and then observed for 14 days. That was an acute toxicity. And in subacute toxicity, a dose was given for 14 days, like 250 gram, 500 gram, 1000 gram.
Okay.
For 14 days. And after 14 days, animal was sacrificed. But the satellite group was further observed if any changes or like there is any physical changes or any other changes observed. So they were kept as a satellite group for further observation.
These are given orally, right?
Yes.
Orally. So did you measure any of the contents of these agents and the blood samples? Or
Yes, yes, I have measured
what
it.
kind of toxicokinetic data you have, or pharmacokinetic data you have?
As such, there was only minute difference in the ALP level and total protein level was observed in the female group, but that was not significant enough. And histopathology slide observed no alteration in any organs.
Yeah, so my question is different. The actual vasculation has some components, right?
Yes.
Did you at least measure one component in the blood plasma and see we have 500, 100, 2,000 doses? Is there any difference in that content?
Individual elements were not observed. Like you are, are you speaking about the individual element observation?
No. Any drug if I give to a patient or to animal, I take blood samples.
Yes.
In a satellite group.
Yes.
And I measure the pharmacokinetics of it.
Okay.
That pharmacokinetics tells me the actual exposure. If I'm giving 3 doses, the 3 doses pharmacokinetics I need to see if the lower dose and the higher dose have actually proportional increase of the drug concentration in the animals. Without that data, I don't know if 500 milligram versus 2000 milligram there's a dose dependence in pharmacokinetics of the actual components. So that is missing in the. What is your plan next? What do you want to do with this?
I wanted to check whether this is helpful for bone health or not.
Yeah,
because as per the literature, it is good for digestive and respiratory, and also for bone health. But the data was not so much on it.
Okay, thank you.
Thank you.
Thank you, Bhavna. Next, we have Pareen Patel with us.
Should I start? So, good afternoon, everyone. Myself, Pareen Patel. Currently, I'm doing PhD in Department of Pharmacology in Institute of Pharmacy, Nirma University, under the guidance of Dr. Snehal Patel. So, in relation to conference's theme, I'm presenting one in silico work titled as in silico molecular docking and pharmacokinetic prediction of gallic acid derivatives as PPR alpha and gamma agonists. So, as we all know, gallic acid is the major phytoconstituent found in tannin-containing plants like amla and others. And in our laboratory previously, the gallic acid and amla fruit itself has been widely studied. We have checked its activity as antidyslipidemic, diabetic in various in vitro and in vivo animal models as well. So the main aim of this study was to come up with bioactive molecules which are better than gallic acid. So we took gallic acid as a parent molecule and we did some conformational changes in functional groups, and we created a library of derivatives, and we screened those compounds with using various in silico tools. So as we PPAR receptors are nuclear receptors is very crucial in lipid and carbohydrate metabolism, and it plays a very crucial role in diabetes, hyperlipidemia and other metabolic disorders. So the major rationale of this study was to create an bioactive molecule which act as a dual agonist on PPAR alpha and gamma, so that it not only just reduces the glucose and fatty acids from the system, but also helps with weight gain. So to do so, we used various in silico tools like Gold, Chemtro and others to screen the library of derivatives of gallic acid on both PPAR alpha and gamma. To do so, we started with the preparation of targets. So we took PPR alpha and gamma 3D crystal structures from the PDB with good resolution. We removed all the water molecules and the standard ligand bound to it. Further, we for the ligand preparation, we took gallic acid as a parent molecule. We did some functional group changes and we created library. After preparing both ligand library and proteins, we did the docking using Gold software, which is available in our in silico laboratory. So, and from the for each molecule, we took into account 10 different conformations, and the software gave us the binding scores. And based on binding scores, the top 5 molecules were taken further for the analysis of pharmacokinetic and various bioactivity parameters. So this is the ligand library we generated by the chemical modification of gallic acid moiety. So starting from the docking studies, the Gold software gave the Gold fitness score based on the affinity binding of ligand with the target proteins, which are both PPR alpha and PPR gamma. So those binding scores were comparable with the standard drugs mentioned here. Besides that, the software also predicted the binding of molecule with the active amino acid moieties in the binding pocket of these target proteins. Apart from that, all the Lipinski parameters like hydrogen bond donors, acceptors, molecular weight, polarity, etc. Were also evaluated by the tool. Further, for the pharmacokinetic evaluation, tools like mole inspiration and ADMET STAR were used, which predicted the pharmacokinetic parameters like the ability of conformer to cross the blood-brain barrier, to cross CACO2 cells, also the AMIS toxicity, which is very crucial for the genotoxic compounds, and its biodegradation profile. So in line with the the physicochemical properties of the compound, we can see the least polar drug, which was the last one, is showing the higher blood-brain barrier permeability and decreased renal cation transporter activity. So it was all in line with the physicochemical properties. And upon next, using the mole inspiration tool, we predicted the binding affinity of these molecules on various receptor family types and enzymes. So it included the G protein coupled receptors, ion channels, kinase inhibitors, nuclear receptors, protease inhibitors, and various metabolic enzymes like cytochrome P450 family. It also gives prediction about of the molecules to inhibit the ethylgogor family receptors, which is very crucial for the cardiotoxicity profile, as these family proteins creates the potassium channels, and so if it inhibits that protein, it causes the arrhythmias. So for the cardiotoxicity profile, it is very crucial. Further, for the toxicity evaluation, software also predicted the molecule's ability to act as a carcinogen or to cause any acute oral toxicity, or it also predicted the LD50 or the toxic levels for the rat models, and tetrahymena pyrimiforous toxicity, which is an organism generally used in the toxicity study to evaluate its toxic doses on that LD50 levels. So to conclude this work is provided a starting point to come up with a bioactive molecule which has dual activity on PPR alpha and gamma as well, so that we can screen certain compounds and come up with certain drug candidate which can further be evaluated in vitro and in vivo models to develop a drug candidate which can be used for dyslipidemia, diabetes, weight gain, and other metabolic disorders. So these are the references, and as I mentioned, these molecules can further be evaluated in vitro in vivo models. These are the key publications which we have got from the previous studies, in which we have screened the gallic acid and amla fruit as such for its various animals and in vitro models. And lastly, I would like to acknowledge the SUB DST for their financial support to carry out this research work, and also the Institute of Pharmacy, Nirma University, for the great infrastructure.
Okay, thank you, Parin. So we are open up for the question answers.
Do you know if there's any actual drug marketed for PPAR alpha dual agonist?
So there are drugs like rosiglitazone and others.
What is it?
Rosiglitazone.
Rosiglitazone is for dual?
So these are mentioned here. So the rosiglitazone and aliglitazar is a non-selective which acts on both PPR alpha and gamma, while rosiglitazone acts on PPR gamma.
So what were the problems with those drugs?
So those drugs are actives and is used in clinical right now. But we aim to develop for further more potent bioactive molecules. So we screen the gallic acid derivatives for it. So we while comparing the scores with the standard class, we can see that some of the molecules have better score than aliglitazar itself. So it might give better effect than aliglitazar.
So there's no
itself.
marketed molecule for dual agonists. Am I correct?
Yes, sir.
There's no marketed molecule.
Yes, sir.
So do you know that many companies actually withdrawn the drugs from the phase 2, phase 3 trials?
Yes, sir. I have read it. I don't know the exact name of those drugs,
So
but I have read it.
some of them do cause cancers.
Yes, sir.
In animals.
Yes, sir.
So after that, nobody's touching that because
Yes, sir.
it's a pharmacology effect.
Yes, sir.
It's not a toxicology effect of the drug itself.
Yes, sir.
It's an extension of pharmacology, toxicology.
Yes, sir.
Then in that sense, why are you pursuing the dual agonists now? It's already data out there. Dual agonists can cause cancer.
So
why are you pursuing that?
So taking into that account that those drugs has some drawbacks, we can screen those things in taking these molecules into account, whether these drugs behaving the same as those we have withdrawn. So ideally it should not do the same thing as the drug which have withdrawn from the market. So yes, sir. Yes, sir. Yes, sir.
When you have something pharmacology, they're going to be very narrow.
So for the pharmacological evaluation, these molecules needs to be screened in vitro and in vivo so that we can come up with the exact how in the system these molecules will work. The in silico tools we can predict that these will be the activity when actually we perform these things. So further evaluation in animal models and clinical trials needs to be done.
So what is the IP potential, intellectual property potential for these?
So
products?
if these molecules passes through in vitro or in vivo studies and clinical trials,
You consider them as NCs or?
Definitely, sir. Because these are semi-synthetic derivatives of
Have
gallic
you done
acid.
patent search? Because gallic acid derivatives have been there for a long time.
Yes, sir.
Have you done any patent search?
No, sir, not yet.
So you should do that because
Yes, sir.
you
Sure.
probably may not have a patent value for it.
Yes, sir.
Okay?
Yeah, sure.
My question is that you have given the SC9, 11, 33 and 37.
Yes, sir.
List of the molecules.
Yes, sir.
And on this side there is a value obtained from the screening.
Screening,
So
yes, sir.
out of these 4 or 5, which one is the best for as per your?
So if we compare amongst these 5 molecules, the gold fitness scores were best for the SC37 as we know, as it gives the best score for both PPR alpha and gamma. But at the same time, it is highly hydrophobic in nature. So it will cross blood-brain barrier and any other. So it has high potential of causing adverse effects. So all 5 of them needs to be screened on in vitro and vivo to come up with which is the better amongst these 5. So from the 40 compounds, we have come up with the 5 compounds with in silico tools. And from the 5 compounds, for the further screening, we have to do the in vitro and vivo studies.
Is there any limitation of this ADMET server?
Yeah, as yesterday also sir discussed that all these in silico tools will give generalized results. So and when we actually perform it in vivo and other models, we have population variability. So we don't know each molecule how it will behave in one individual subject.
Are you giving dose or concentration as an input for this screening anywhere in ADMET?
That I am not aware of about. Yeah.
Thank you.
Yeah.
Okay, thank you, Pareen. And the last one with us is Srishti Varma. Please come.
Shall I start? Very good afternoon, everyone. My name is Srishti Verma, and I'm here to present work on efficacy and safety assessment of novel probiotic preparation of Bacillus clausii PBC 429 for the treatment of diarrhea. These are the table of contents which I'm presenting here. So, probiotics are the live microorganisms which, when we administer in adequate amounts, it will provide health benefits. But insufficient safety assessment of these probiotics can lead to serious health issues, which we have already seen as Bacillus cereus in China, and that's why the safety assessment of these probiotics are necessary. So, if I talk about Bacillus clausii, so Bacillus clausii is a gram-positive bacteria with which is non-pathogenic, and it is also believed that it secretes some types of antibiotics which will eliminate the bad bacteria from the gut. So for this study was carried out in 3 steps. First, we have evaluated the acute toxicity, then we have proceeded with the subacute toxicity, and then we have evaluated the antidiarrheal effect of the preventive antidiarrheal effect of the probiotic. For acute oral toxicity studies, we have observed no mortality, and we have seen an increase in weight of the rats when we compared it with the normal control. For repeated dose subacute toxicity studies, we have observed similar patterns in the body weight. There was no significant decrease, but there was an increase in body weight for the further days throughout the studies, both in males and the females. We have also evaluated the blood parameters, hematological parameters, because as I have mentioned, Bacillus cereus outbreak was there in China. So for that, we have evaluated the WBC counts. WBC counts were almost normal. They were in the safety range, both in male and the females. We have also analyzed the serum biochemistry, functional test for the toxicity for liver, kidney, everything. Glucose, triglyceride, cholesterol, SGOT, SGPT, total protein, bilirubin, albumin, alkaline phosphatase, urea, creatinine, sodium chloride, and potassium as well. We have not observed any significant difference between the serum biochemistry, and there was a significant decrease in the triglyceride group. So I hope we can study further this strain for cholesterol studies or dyslipidemia or something. We have also evaluated the urine parameters. In urine parameters, we have evaluated specific gravity, pH, glucose, protein, albumin, and creatinine. Similarly, there was no significant difference between the normal control and the treatment groups. We have also dissected out the organ weight at the end of the study, both in males and females. There was no significant difference between the organ weights of the animals. This was the histopathological results of the these are the representative images of lungs, heart, liver, and kidney. There was no change. There was no macrophageal filtration. No lesions were observed in this histopathological image. In lungs, there was a little bit congestion was there, but there was no infiltration or the disruption of the wall in the lung images at the right side of the top. So we have also performed antidiarrheal studies. For this study, we have taken 5 groups, and we have randomized mice into 5 groups. Each group consists of 6 animals. We have evaluated the frequency of defecation and the percentage inhibition. So what we have done, because probiotics are majorly used as for preventive effects. So we have given treatment to the mice for 3 days, 2 times a day, and after that we have induced the diarrhea, 0.5 ml of castor oil, and then we have measured the frequency of defecation and the percentage inhibition. So as you can see it on the board, that frequency of defecation was comparable of high dose treatment group with the positive control group. Positive control group was loperamide, 3 mg per kg. For each and every dose, we have confirmed it from the previous studies, previous research papers we have preferred. If I see the percent inhibition, so the percentage inhibition of high dose treatment and the positive control was comparable. In the conclusion, I want to conclude that the probiotic strain, what I have studied, it was safe and it can be further studied, and it was showing preventive effects on the diarrhea. At last, I want to acknowledge the Pellucide and Nirma University for supporting for this research. These are the references. Thank you so much.
Thank you, Srishti. Sir,
So,
the session.
yeah, I mean, how much diarrhea you see with castor oil?
How much diarrhea? Can I have a mic? The frequency of the defecation will increase. Means the stools will be liquidy.
Right.
They will be not in the normal shape or size, or the liquid content will increase in the stools.
So your probiotic brings to normal, that to normal, the liquid stools to solid stools?
Sorry,
No, you giving probiotic along with the castor oil.
Yeah.
Does your stools become normal?
It doesn't become normal. It was the percentage inhibition was the weight of the stools, but the weight of the stools, there was it didn't become normal, but the stools visualization, I can say you, and the weight what I have measured, it was that.
And this is a novel probiotic, you say, right?
Novel probiotic preparation, sir. Sorry, it's not novel probiotic. It's a preparation.
Preparation is novel. I mean, method of preparation.
Yeah, method of preparation is novel. Yeah.
And the method of preparation didn't change any pathogenic properties of the.
No, sir. So actually, Bacillus group of bacteria are very stable. They are known to be very stable throughout the processing process.
So did you do any genomic analysis to see if that?
That was done by the Pellucide Life Sciences.
Okay.
I have not shown the data here because everything is there in publication process, and it's there patenting and whatever the stuff is.
Yeah,
there.
I mean,
this is what I have done here.
Yeah, it's interesting, but typically you use another pathogenic bacteria rather than castor oil. I mean, that would
Totally
be the ideal
agree.
situation.
Yeah, totally agree. For comparing it, yeah, we should use some pathogenic bacteria, but we have actually reviewed, we have searched for the research papers, and we have found some research papers of probiotics with castor oil induced diarrhea, so that's why we have progressed with that.
Okay, thank you.
Thank you so much.
So I might have missed it. So have you seen, or you have any tests that have shown that actually these treatments change the microbiota of the GI tract that could actually be efficacious?
No, so that study is pending. No, we have not seen that.
Okay.
Okay, thank you, Srishti. So, thank you everyone, and congratulations to all the participants.
It takes a lot of courage to come to the stage and give a presentation among all the experts here. So a big round of applause for everyone. Great job.
Okay, so within a few minutes, we are starting with the valedictory session, and I am handing over the mic to Dr. Bhagwati section.
Total of divide by T. All the marks. Whosoever comes, and we'll need a calculator because we forgot math. We can't. Earlier days we used to just count. First that when you asked, we also had, but I forgot. These metrology data was there. Hello. Hello. Hello.
Hello.
That's the third prize.
Agree it has to go to men because he asked the maximum number of questions. So that's what is for you.
Hello.
फॉर्मल है इतना बड़ा तो स्टेज लगा है
Good afternoon, everyone. Respected dignitaries, honorable guests, esteemed colleagues, and dear participants. On behalf of Institute of Pharmacy, Nirma University, myself, Dr. Bhagwati Saxena, and it's my privilege to anchor this valedictory section of ACS TOXI India 2024. Organized by Scientific Educational Conferences International Forum and the American Chemical Society Division of Chemical Toxicology India chapter in collaboration with Institute of Pharmacy, Nirma University. After a series of engaging discussion, insightful sessions, talks, and moment of learning and inspiration, we now gather here to formally conclude this event. Today, we celebrate not just the end of this journey, but the beginning of new opportunity, collaboration, linkages, and lasting memories. Now I would like to invite Honorable Chief Guest, Professor Grover P. Miller, Dr. Gopal Natesan sir, Dr. Deepak Barot sir, Dr. Jigna Shah, Dr. Snehal Patel to occupy the dais. Welcome you all, sir. Thank you all. Now, over the past 2 days and 7 sessions of scientific talks, we have witnessed enriching session on environmental toxicology and impact of heavy metal as well as trace metal on the human health. Application of artificial intelligence and machine learning tools in toxicology, AI modeling in bioactivation risks, and physiological-based toxicokinetic modeling. Sessions also covers other tools for toxicology, prediction, and testing, as well as novel therapies. This event has truly been a learning experience. We believe these insights will surely inspire us and drive innovations in this field. So without further delay, I would like to request Dr. Deepak Barut sir to share their closing remark with us.
All right, so very good evening to all of you, and I think what a day and what couple of days we had. So a big round of applause for all of you guys. Thank you. I mean, at a validatory function, if I'm seeing so many people in the audience, means I'm sure the agenda was really interesting enough for you guys to stay back till the end. And I know you are really waiting for the top 3 poster winners, but that's okay. I mean, that's also a part of the conference. So I think great show put up together by all the committee members. And if I had to take the names, it's going to take another couple of hours, and I don't think we have that much time. So I would just like to thank the core committee members led by Ujjwal and Natalia for their vision, which actually, because of that, the meeting happened today. And all the other committee members, including Michael Stone, Grover Miller, Mike, Sarah, I think I'm thankful to all of them. And all the organizing committee members led by Dr. Gopal and Dr. Snehal, Dr. Jigna, Dr. Richa, and all the other organizing committee members. I'm so thankful to all of you guys for your efforts. And I think 2 days we have just covered whatever we could in terms of toxicology, AI and ML tools for prediction of toxicity from xenobiotics and health hazards. So throughout the sessions, starting from tools of AI and ML plus 3D prediction models. Then we also touched based on environmental toxicology as well. And then we had a couple of interesting talks, like a plenary talks. So all in all, we tried to cover important facets of toxicology. And more than that, I think what we achieved is this initiative. And then like the whole focus is learning to provide a platform of knowledge sharing. And then to have such an option available in India, and I'm so happy that ACS TOXI US they could start this India chapter. So by attending this conference, I think all of you guys have become a member, and we already had a discussion internally. So all those people who have attended this conference as per registration, they all will be at least 1 year free membership would be there for ACS Talks India. So big round of applause for all of you guys. So by default, first year membership is free. Next year you got to pay for that. Okay, so be ready for that. And then apart from that, we had a great poster session because we always encourage students to participate and at least get exposure of sharing your research at such a prestigious platform of an international conference. And I'm glad that we had 31 posters. So all of you did great. Once again, a big round of applause for 31 poster presenters. And finally, all the moderators, I think they did a great job. I know we were running late, but all of them really did great. And the only reason why we were behind the schedule because talks were so interesting and so interactive. There were plenty of questions, and I had to thank Grover because today his little rocks did the trick. And a lot of questions were there, and people wanted to earn as many rocks as they could. So anyway, jokes apart, but thank you for making this session so lively. And lastly, I would like to thank the Institute of Pharmacy, Nirma University. So a big round of applause for your own institute. And thank you to Dr. Gopal and his entire team, all the faculty members. You guys did great. I think without your support and help and passion and such a dedicated involvement in this, I don't think it was possible to do such an international conference, that to an inaugural ACS TOXI India chapter meeting. So once again, a big round of applause for all of you, and thank you. Thanks a lot.
So now we have arrived at most of the waiting movement prize distribution. Now I request Professor Miller to kindly give prize to the students. So third prize for the poster presentation goes to Bhavna Bora. Hello. Second prize goes to Pareen Patel. And lastly, the first prize goes. Lastly, the first prize goes to Shrishti Verma. Sir, I request you to stay here for memento presentation to the organizing committee members. Huh? Okay, so first I would like to invite Sir Dr. H.B. Patel, sir.
So thank you. And then I think I would request Dr. Grover to be there. And the first prize poster winner, if she can come back again. We have another award because we thought, we discussed about it. And from this year onwards, there is another award which will be given every year for the best poster. The first prize poster winner will also get Dr. Ashwin M. Thakur Award. So that is for the poster winner. So congratulations to the winner, and this winner, so the winner will also get free registration for the next year conference wherever it happens, ACS TOXI India. Plus, she will also get a cash reward of 7,500 rupees. So, congratulations. And it's not only for her, but the second poster winner will get 5,000 rupees cash reward. And the third prize winner will get 2,500 cash reward. And finally, once you receive that cash, all of you need to give it back to me. So, thank you. Please go
ahead. Sir, so first memento, Dr. H.B. Patel, sir. Secondly, Dr. Deepak Barot, sir. Dr. Prerna Barot. Then Professor Gopal Natesan, sir. Professor Jigna Shah. Dr. Snehal Patel. Dr. Sheetal Panchal.
Dr. Bhagwati Saxena. Dr. Richa Gupta. Dr. Mithun Singh Rajput. Anjali Menon.
So next segment of this session is feedback. So we invite participants to share their feedback that is very valuable, and it helps us to improve and create even better experience in future. So anyone from the participant, come here and just share your feedback.
I profile.
It's fine.
Yes, I am
fine. Hello, good evening, everyone. I want to share the feedback regarding this ceremony, this conference about ATC toxic. So we have a very good experience in this. So we get a good opportunity to learn about the toxicity of medications, and in turn we can produce new drugs to AI or ML systems rather than animal testing. So we can protect our environment. So this is a very that I can't tell the words that we really enjoyed this conference. Thank you so much.
Aram se bata.
Big round of applause for Veena.
I profound grateful to 2 days conference. I learned lots of lessons and fundamental knowledge about the toxicology, and thank you all the experts for sharing their knowledge with us and giving us a precious time of yours. Thank you so much.
Thanks, Vedant and Winner. Anyone else to share or communicate their feedback? Okay, we will proceed for the next segment. So I would request Professor Gopal Natesan sir to say a few words.
Okay, good evening all. First of all, I would thank the core committee who trusted on us to give this opportunity to the Institute of Pharmacy. They have trusted us that we can do it and we will deliver better, and we did it, I think so. Yes or no from your side, students? So give claps on for yourself, yourselves. You put a lot of effort. Especially, I always support the students, so I will say start from the students. I wholeheartedly have to say thank you to all the student volunteers, especially the PhD students and my MPharm students, who I have seen last 2-3 days you are dedicatedly working. Even Sunday you came, you did all the work. So from my bottom of my heart, I say thank you to you all for supporting me. And this is not supporting to me, this is support to Institute of Pharmacy. Okay, next I thank Dr. Grover and the total team, Dr. Patel sir, everyone trusting us, and we hope we did our best. If any mistakes happen in these 2 days, please apologize us, we will improve next time. Hope the next second meeting also should happen in Nirma University itself. That is our request. And I thank all my team, pharmacology team, teaching faculties, non-teaching faculties, everyone, those who helped us to get this program a great success. I thank all the supporters, all the speakers, students who have come from another universities, everyone, thank you so much. There's one request to Dr. Grover and Dr. Deepak, because when you say next year there's a free for the students, I'm just thinking of why can't I can start a student chapter here, ACS TOXI. So I'm keeping a proposal, you just discuss with your team and let us know it. Okay, so we want to start the student chapter here, so that the student, because we are talks about our own research and all, but that has to be inculcated from the students. So the students should involve in this, and students should take up these things. So I request Dr. Grover and Dr. Deepak and even Dr. Ujjwal also, all the team core members, to think of this agenda so that we can have a India student chapter from Nirma University where we hold the hand. Thank you so much. Thanks.
Now I request Dr. Snehal Patel, ma'am, to present vote of thanks.
So good evening, one and all present here. So moving towards the end of this 2 days conference, so indeed it is indeed a great pleasure for me to propose this vote of thanks. So we are thankful to have with us chief guest Dr. Mila Grover, who has spent 2 days entirely for this conference. So I'm thankful to you, sir, for being in this conference. On this occasion, I sincere and heartful thank to our university officials, Padma Shri Karsan Bhai Patel, President Nirma University, K.K. Patel sir, Vice President Nirma University, Dr. Anup Singh sir, Director General Nirma University, and all other official staff who has given a great motivation in all the venture at the Institute of Pharmacy. I am highly thankful to our director sir, Jigna madam, and other faculty members of Department of Pharmacology for the cooperation for conducting this conference. I'm also thankful to all the speakers who have spared their valuable time, Dr. Gnanendra Singh, Dr. Subramaniam, Dr. Utsav Gandhi, Dr. Shailendra Bhavsar, Dr. Shailendra Pratap Singh, Dr. Jay Sheth, Dr. Senthil Nattisan, Dr. Krishna Iyer, and Dr. Poonam Giri. So all came from different parts, and they have shared their research and valuable talks they have delivered to this program. So I'm also thankful to the American Chemical Society. So under the wages of which this conference has been held. So I'm also thankful to Dr. Deepak Barot, who has given the support throughout this the conference. So I'm also thankful to the other volunteers who have worked very hard on Saturdays and Sundays. They have worked all together, and I'm also thankful to the participant who has also contributed a lot and has shared their research work. So thank you one and all present here.
As we bring this valedictory session to close, thank you once again for being a part of this event. Lastly, before concluding this valedictory function, I request everyone to present here to raise for the national anthem.
तव शुभ आशीष मांगे, गाहे तव जय गाथा। जन गण मंगलदायक जय हे भारत भाग्य विधाता। जय हे जय हे जय हे जय 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 हे।
So all of you just come at the main gate of this Institute of Pharmacy. We have a photo session. Group photo. Okay. All the participants who has presented their poster, just collect your posters from the pole.